Guys, there is some glitch. I don't know why the video got ended. Just wait. Okay, I'm creating a new stream. Just wait. हेलो। नहीं नहीं, आज कहाँ 2 सेशन थे? आज तो एक सेशन था, अभी जो मैं ले रहा था। नहीं, 300 क्वेश्चन वाला मेरा कल का था। हाँ, इससे पहले मेरा चल रहा था, वो एंड हो गया। अब मैं दूसरे पे ऑटोमेटिकली लाइव हो गया, दूसरे सेशन पे। हाँ, इसका नाम चेंज कर दो। अभी जो टॉप 300 वाला है ना, इसका नाम चेंज कर दो। इसको कंटिन्यू इसी सेशन में करते हैं। Guys, can you hear me now? Is it audible now? Am I audible, visible? So I think we'll continue in this stream only, huh? Just a second, just a second, just a second. Is everyone back or not? I think it's fine now. Let's continue. Let's continue. We'll continue in this stream only, okay? We'll continue in this stream only. Okay, is it completely fine now? Is it completely fine now? I'll get all this changed. This top 300 questions of physical chemistry 12th, it'll get changed, don't worry. Don't worry, I'll get the title changed. Okay, let's move on. So what I was telling this law of mass section is basically one more way of calculating the rate of the reaction. It is one more way of calculating the rate of the reaction, okay? Just a second, the team is calling. Hello? अरे वो स्ट्रीम ऑटोमेटिकली एंड होगी और दूसरे वाले लाइव स्ट्रीम में चला गया, वो टॉप 300 क्वेश्चंस वाले में. उसका बस उसका ये नाम वाम चेंज कर दो, जो टॉप 300 वाला है ना. आई एम राइट नाउ लाइव, मैं अभी क्लास में हूँ, ठीक है. उसका वो वाला लगा दो, थंबनेल एज वेल एज टाइटल, ठीक है. ओके. Okay, let's move on now. So, law of mass section, it gives me one more way of calculating the rate of the reaction. And as per law of mass section, rate of reaction is directly proportional to the product of active masses of reactants raised to the powers of their respective stoichiometric coefficients. Okay. So, I wrote rate of the reaction is directly proportional to active mass of A multiplied by active mass of B raised power N1 raised power N2. Now, as I told you, whenever you see any reactant or product in aqueous phase, that particular reactant or product which will be in aqueous phase, its active mass is nothing but its concentration. So what I wrote here, instead of active mass of A, I wrote concentration of A. Instead of active mass of B, I wrote concentration of B. Why is that? Because this A and B was present in aqueous phase. Perfect? Perfect, guys? So basically, when I talk about the law of mass section gives me the idea about the rate of the reaction. Nothing else. Now let's talk about this a bit more in detail. For example, my dear students, you have got the reaction like this. 2 times A aqueous plus B aqueous, it gives, for example, C. Let's say this is a balanced chemical equation. Now, as per law of mass section, I can say rate of the reaction is equal to A. Since A is in aqueous phase, so I'll write concentration of A raised power stoichiometric coefficient, that's 2. Similarly, I can write concentration of B raised power stoichiometric coefficient, that is 1. So this is basically one more way of calculating the rate of the reaction as per your law of mass section. As per your law of mass section. Okay? Perfect. Now, my dear students, let's try to understand few important things here. Let me tell you, for a reaction basically, for a reaction, there are two ways to calculate rate. For a reaction, there are two ways to calculate the rate. There are two ways to calculate the rate of the reaction. Number one, we can calculate rate of the reaction theoretically. We can also calculate rate of the reaction experimentally. We can calculate rate of the reaction theoretically, and we can calculate rate of the reaction experimentally. Theoretically, we calculate rate of the reaction with the help of law of mass section. So basically, for any reaction, if I use this equation, to calculate the rate, you call that rate as the theoretical rate of reaction. Now you can calculate rate of the reaction experimentally as well. You can calculate rate of the reaction experimentally as well. You can calculate rate of the reaction experimentally as well. My dear students, let me tell you one thing. There are two ways to calculate rate of reaction. Either I calculate rate of reaction theoretically or I calculate rate of the reaction experimentally. And this experimental rate is your actual rate of the reaction. This experimental rate is your actual rate of the reaction. Now let me tell you, there are some reactions for which theoretical rate and experimentally determined rate would be equal. But there are some reactions for which theoretical rate and experimentally determined rate, they come out to be different. Okay, they come out to be different. Do you understand? what I'm trying to say is there are two ways to calculate rate of reaction. Either you calculate rate of reaction with the help of law of mass section, or you can calculate rate of the reaction experimentally. When you calculate rate of the reaction with the help of law of mass section, what do you get? You get theoretical rate of reaction. And when you calculate rate of the reaction experimentally, that is your experimental rate or actual rate of the reaction, there will be some reactions for which theoretical rate and experimental rate would come out to be equal. But there would be some reactions for which theoretical rate, which you calculate with the help of law of mass section, that would be different from the actual rate of the reaction. Okay, what does that mean? We can conclude one thing. That means this particular law of mass section, does it always give me the correct results? This law of mass section does not always give me the correct results. This law of mass section does not always give me the correct results. This law of mass section does not always give me the correct results. It does not always give me the correct results. This law of mass section does not always give me the correct results. Okay? So my dear students, what we need to do here, since we got to know that the law of mass section does not always give me the correct results, so what we are supposed to do is, we are supposed to modify this equation. We are supposed to modify this equation so that the new equation which we get, that always gives the correct results. What we are supposed to do is, we are supposed to modify this particular equation so that the new equation which we get, that always gives us the correct results. So now what we are going to do, we are going to modify the law of mass section. We are going to modify the law of mass section. And my dear students, the modified law of mass section is what you call as a rate law. The modified law of mass section is what you call as a rate law. Okay. So first of all, what was the need to introduce the rate law? What was the need to introduce the rate law? Can you tell me that? What was the need to introduce the rate law? Quickly. Because I can say, law of mass section does not always gives me the correct results. Law of mass section does not always gives me the correct results, right? So I had to modify the law of mass section, and that modified law of mass section is what you call as the rate law. So let's talk about this rate law over here. Okay, let's talk about the rate law over here. So first of all, if I talk about the rate law, rate law says that rate of the reaction. Rate law says that rate of the reaction is directly proportional. Rate of the reaction is directly proportional to the product of. Rate of the reaction is directly proportional to the product of. Active masses of reactants raised to the powers which are calculated experimentally. Which are calculated experimentally. What does it mean? Try to understand properly. For example, you have got the reaction. The reaction is N1A plus N2B. It gives, for example, product. Let's say this A is in aqueous phase and B is also in aqueous phase. A and B, for example, both are in aqueous phase. Okay. Is it lagging? I don't know what's wrong. Is it still lagging? Is it okay now? I think it's okay. Now it's fine, huh? Okay, listen now. Okay, listen now. So basically, for example, you have got the reaction N1A plus N2B. It gives what? It gives, for example, product. How do I write rate law for this particular equation? Rate law says that rate of the reaction is directly proportional to product of active masses of reactants. Now, active mass of this reactant, I'll write as concentration of A. Active mass of this reactant, I'll write concentration of B. Raised to power, the stoichiometric coefficients. Raised to the power, the stoichiometric coefficient. Is it raised to power the stoichiometric coefficient? No. It is raised to the powers which are calculated experimentally. Raised to the powers which are calculated experimentally. So in law of mass section, the powers used to be stoichiometric coefficients. Here the powers are going to be what? Here the powers are going to be x and y. Here the powers are going to be x and y. What is the difference between law of mass section and rate law? In law of mass section, the powers are always the stoichiometric coefficients. But here, the powers are going to be x and y, and this x and y we calculate experimentally. This x and y we calculate experimentally. So my dear students, let me tell you, R will be equal to, this is going to be constant K, concentration of A raised power x, concentration of B raised power y. This particular equation is what you call as rate law. This particular equation is what you call as rate law. Okay? And if this is the rate law, let me tell you this x over here. This x is called as order of the reaction with respect to A. Y is called as order of the reaction with respect to B. And if I add the two, x plus y, this is what you call as the overall order of the reaction. This is what you call as the overall order of the reaction. My dear students, it's important to understand the difference between law of mass section and rate law. So let me give you the quick recap of the things which I told you right now. I told you I've got two ways to calculate rate of the reaction. I've got two ways to calculate the rate of the reaction. Till now, whatever we discussed, as per that, I've got two ways to calculate rate of reaction. I can calculate rate of reaction either with respect to law of mass section, or I can calculate rate of the reaction with respect to rate law, with the help of rate law. Now, as per law of mass section is concerned, for example, you have got the reaction like this, N1A plus N2B. It gives product. Let's say this is the reaction. As per law of mass section, rate of the reaction is equal to K is the rate constant, concentration of A raised power N1, concentration of B raised power N2. But as per the rate law, rate of the reaction will be equal to K, concentration of A raised power X, concentration of B raised power Y. Okay, and this X and Y, it is calculated experimentally. If X and Y is calculated experimentally, I'll be calling this as the experimentally determined rate. I'll be calling it as the actual rate of the reaction. And this is what I call as the theoretical rate of the reaction. So what is the difference? What is the difference? What is the difference? There is a lot of glitch. Wait. There is a glitch. Just a second, guys. There's a glitch. There's a glitch. हेलो, आपने वो वाला वीडियो डिलीट किया? यार मैं तो उस पे तो 50 मिनट ऑलरेडी में पढ़ा चुका था ना, तो मैं वहां से कंटिन्यू कर रहा हूँ. नहीं, अभी वापस इसको पब्लिक कर दो क्योंकि बच्चे पीछे थे ना अभी, तो अभी आधे बच्चे वही देख रहे हैं, उसके बाद वो ये ज्वाइन करेंगे ये वाला. वो पब्लिक कर दो वापस. ओके. Oh my God. Can you see the other video? Can you see the other video, guys? Okay, now we'll continue. Now it's completely fine. Now it's completely fine. So now, my dear students, what I was trying to say is, if you will have to calculate rate of reaction can be calculated either with the help of law of mass action, or we can calculate rate of the reaction with the help of rate law. What is the difference? The equations are similar. The equations of law of mass action and rate law, they are similar. Where are the changes? The changes are in the powers. Here the powers are your stoichiometric coefficients, and here the powers are x and y, which are calculated experimentally. Okay, my dear students, as I told you already, there are some reactions for which theoretical rate of reaction and experimentally determined rate of reaction, they are equal. So when can be theoretical rate of reaction and experimentally determined rate of reaction equal? They can be equal only if x value comes out to be equal to N1 and y value comes out to be equal to what? Y value comes out to be equal to N2. Okay? Y value comes out to be N2. But there are some reactions for which theoretical rate and experimentally determined rate, they are not equal. So in such cases, I would say x value, when you calculate experimentally, it won't be equal to N1, and y value, when you calculate experimentally, it won't be equal to N2. So these are the two things, my dear students, which you need to remember from now onwards. So whenever you want to calculate rate of the reaction, you can calculate rate of the reaction either with the help of law of mass action, or you can calculate rate of the reaction with the help of what? With the help of rate law. With the help of rate law. Okay? With the help of rate law. My dear students, whenever you use law of mass action to calculate the rate of the reaction, that's what you call as theoretical rate. And when you use rate law to calculate rate of the reaction, you call it as the experimentally determined rate. What is the difference between the two equations? The difference is in the powers. Here the powers are your stoichiometric coefficients. Here the powers are x and y. There are some reactions for which theoretical rate and experimentally determined rate will be equal. So in such cases, your x will be equal to N1. Your y will be equal to N2. And there are some reactions for which theoretical rate and experimentally determined rate, they won't be equal. So in such reactions, x value, when you calculate experimentally, it won't be equal to N1, and y value won't be equal to N2. Is this particular point clear now? Can you tell me once in the chats quickly? Can you tell me once in the chats quickly if all this is clear till now? I know there were some glitches, but I think the glitches are fixed now. There is only one thing that is problem, that is the camera adjustment. Now it would be fine. Okay. Perfect. Now, my dear students, comes a point. What is that? What is that? This K over here. This K over here. What is this K called? This K is called as the rate constant of the reaction. This K is called as the rate constant of the reaction. And how do we define this rate constant? What kind of information this rate constant gives us? Let's try to understand this in detail now. My dear students, for example, I am taking the reaction N1A plus N2B. It gives, for example, product. If I use the rate law, rate law says that rate of the reaction is equal to K, concentration of A raised power X, concentration of B raised power Y. This is your rate law. This is your rate law. And I use the stoichiometric coefficients as X and Y. And this X and Y, they are calculated experimentally. We know that already. Now, my dear students, if, for example, the concentration of A and the concentration of B, if both are equal to 1, if I keep the concentration of A and B equal to what? Equal to 1. At that point of time, remember, your R value is equal to K. At that point of time, R is equal to K. So I can say rate constant is nothing but rate constant is basically the rate of the reaction. Rate constant is basically the rate of the reaction when the concentration of all the reactants is taken as 1 molar. So whenever in a reaction, the concentration of all the reactants is taken as 1 molar, at that point of time, whatever will be the rate of the reaction, that's what you call as the rate constant of the reaction. So rate constant is nothing but rate constant is the rate of the reaction when the concentration of reactants is taken as 1 molar. Now the point is, what kind of information this rate constant gives us? My dear students, let me tell you, rate constant gives me the idea about the speed of the reaction. Number one, it gives me the idea about the speed of the reaction. Okay. Remember, more the value of rate constant, faster will be the reaction. More the value of the rate constant, faster will be the reaction. Point number one. Rate constant gives me the idea about the speed of the reaction. That particular reaction whose rate constant is more, its rate will be more, its speed will be more. Point number one. Rate constant does not depend. It does not depend on the initial concentration of reactants. Rate constant, it does not depend upon the initial concentrations of reactants. Why is that? Because as per definition, how do we define the rate constant? Rate constant is defined as the rate of the reaction. But when? When the concentration of all the reactants is taken as 1 molar. So we have got nothing to do. We have got nothing to do with the initial concentrations of reactants. Rate constant is defined only and only when the concentration of all the reactants is taken as 1 molar. Okay. Similarly, my dear students, the third point. What is that? Rate constant depends upon the temperature of the reaction. Rate constant depends upon the temperature of the reaction, which I'll teach you at the end of this chapter. When I'll teach you Arrhenius equation, you'll understand this particular point there. Rate constant is directly proportional to temperature. So basically, when you increase the temperature of the reaction, rate constant increases. And if rate constant increases, rate of the reaction automatically increases. Rate of the reaction automatically increases. So remember, your rate constant, it is directly proportional to temperature. On increasing the temperature, rate constant of the reaction increases. Hence, I would say rate of the reaction increases. Perfect. One more important point which you need to remember. Similarly, my dear students, similarly, what are the other things? What are the other things about this particular rate constant? What are the other things about this particular rate constant? Those are something which we'll be talking about in some time. First of all, these 3 points is something which I want you guys to remember for now. Number one, rate constant, it gives me the idea about the speed of the reaction. More the value of rate constant, more is the speed of the reaction. Lesser the value of rate constant, lesser is the speed of the reaction, right? Similarly, my dear students, rate constant, it does not depend upon the initial concentrations of reactant. Third, rate constant of a particular reaction depends on temperature. When you increase the temperature of the reaction, rate constant increases. And when rate constant increases, I would say rate of the reaction automatically increases, right? Is it clear till here? Can you tell me once in the chats? Is it clear till here, people? Is it clear till here? And remember, one more important point. Every reaction has a particular value of rate constant. Every reaction has a particular value of rate constant at a particular temperature. Every reaction has a particular value of rate constant at a particular temperature. Remember that as well. So, all the reactions, they'll be having their fixed value of rate constants at a particular temperature. For example, you have got the reaction like this. A gives B, this one reaction. One more reaction, C gives D. Let's say temperature of this reaction is 25 degrees centigrade. Even temperature of this reaction is 25 degrees centigrade, for example. So, every reaction has a particular value of rate constant at a particular temperature. So, let's say this reaction will have the rate constant K. This reaction will have the rate constant K dash. And by comparing the value of K and K dash, you can check, you can say which reaction is faster, which reaction is slower. Because you know, more the rate constant, faster the reaction. Lesser the rate constant, slower the reaction. As simple as that. Okay. Now, my dear students, let's talk about few more important things. What are few more important things? Let's try to understand what are few more important things. First of all, if I talk about the types of the reactions, let me tell you, reactions are classified into two types: simple or elementary, and the second one is complex reactions. Simple or elementary, second one is complex reactions. What are simple reactions exactly? Simple reactions are the ones which are completed. Simple reactions are the ones which are completed in a single step. So those particular reactions which are completed in a single step, you call those reactions as the elementary reactions or simple reactions. And those reactions which are completed in more than one step, those reactions which are completed in more than one step, you call those reactions as the complex reactions. Okay. Now, in case of elementary reactions, in case of simple reactions, remember, law of mass action is truly valid. Law of mass action is truly valid. What does that mean? That means, for example, you have got the reaction of this format, N1A plus N2B. Let's say it gives product. I told you a few minutes back, I can calculate rate of the reaction by two ways. Either I'll be using law of mass action to calculate rate of the reaction, or I'll be using rate law to calculate rate of the reaction. What is the difference? When I use law of mass action, I'll say R is equal to K, concentration of A raised power N1, concentration of B raised power N2. Now, when I use the rate law, I can say R is equal to K, concentration of A raised power X, concentration of B raised power Y. And we know this X and Y, they are calculated experimentally. Now, my dear students, when we use law of mass action to calculate rate, we call this rate as the theoretical rate. When we use rate law to calculate rate, this is going to be your experimentally determined rate or actual rate. Now, people, as I told you already, there are some reactions for which theoretical rate and actual rate, they'll be equal. There are some reactions for which theoretical rate and actual rate will be equal. In those reactions, this X, when you calculate experimentally, its value would come out to be same as the value of N1. And when you calculate the value of Y experimentally, it will come out to be same as the value of N2. So those reactions for which theoretical rate and experimental rate will be always equal. So those reactions for which, when you calculate rate with the help of law of mass action and when you calculate rate with the help of rate law, you get same value from both the equations. Those are basically your elementary reactions. So when you have the elementary reaction, when you talk about the elementary reactions, in case of elementary reactions, if you want to calculate rate with the help of law of mass action, or if you want to calculate rate with the help of rate law, both these equations are going to give the same results. That means the value of X which you calculate experimentally, it will come out to be same as the value of N1. The value of Y which you calculate experimentally, it will come out to be same as the value of N2. Got it? Did you understand? That's why I wrote law of mass action is truly valid for elementary reactions. Law of mass action is truly valid for elementary reactions. If this is clear, let me know once in the chats. Quickly. Everyone. Let me know quickly in the chats if this is super clear to everyone, guys. Yeah? Perfect. I believe this particular point is clear. Now, when it comes to complex reactions, what are complex reactions? Complex reactions are completed in more than one steps. And my dear students, let me tell you one thing. The steps involved in the complex reaction. The steps involved in the complex reactions are elementary. The steps involved in the complex reactions are elementary. For example, let me take a reaction which will make you understand it properly. Let's say I'm taking the reaction NO plus Br2. It gives what? It gives NOBr2. It gives NOBr2. Now this NOBr2 which we have here, let's say this NOBr2 reacts with NO and it makes it as 2 times NOBr. So I wrote 2 reactions. My dear students, if I add these 2 reactions, NOBr2 cancels out. So NO plus NO makes it 2 times NO. Plus what? Plus Br2. Gives what? Gives 2 times NOBr. If you look at this particular reaction, is this reaction getting completed in one step? No. This reaction is getting completed in more than one step. This reaction is getting completed in more than one step. And any reaction which gets completed in more than one step, you call that particular reaction as the complex reaction. So this is your complex reaction right now. This is your complex reaction. Now, my dear students, since this complex reaction has 2 steps and both these steps are single step, right? So this is your elementary reaction. This is also your elementary reaction. So remember, the steps which are involved in the complex reaction, they are always elementary. They're always elementary. Okay? They're always elementary. I believe this particular slide is clear. We have got 2 types of reactions, simple reactions or elementary. Another one is complex. Elementary reactions are the ones which are completed in single step. Elementary reactions are the ones which are completed in single step. Law of mass section is truly valid for them. Law of mass section is truly valid for them, for elementary reactions. That means when you want to calculate rate of the reaction with the help of rate law or law of mass section, both the equations are going to give you the same results. That means X value will be always equal to N1 and Y value will be always equal to N2 for elementary reactions. When it comes to your complex reactions, they are completed in more than one step. Right? The steps involved in the complex reaction, they're always going to be elementary. So if you look at this particular reaction is completed in 2 steps. So it's a complex reaction, but its steps will be always elementary. I hope this is clear to everyone. Now, if this is clear to everyone, let's talk about one more point. What is that? That is your molecularity. First of all, my dear students, when you talk about molecularity is again a theoretical concept. It does not have any experimental background. It's a complete theoretical concept. It does not have any experimental background. Okay? And this molecularity term, which I'm going to define now, it is defined only for which reactions? It is defined only for elementary reaction. The concept molecularity, it is defined for what? It is defined for elementary reactions. The concept of molecularity was basically given for elementary reactions only. Now the point is, how do we define this molecularity? Simple. There is a theory called as collision theory, which I'm going to teach you afterwards. Collision theory tells us one thing. Whenever a reaction has to happen, whenever reactants have to form the products, whenever reactants are supposed to form the products, the reacting species, which can be either atoms, molecules or ions, the reacting species, they must collide first. Whenever reactants are going to form the products, the reacting species, they must collide first. And my dear students, let me tell you, the number of reacting species which would be colliding to form the products, the number of reacting species which would be simultaneously colliding to form the products, that's something which we call as molecularity of the reaction. What does it mean exactly? Try to understand. For example, you have got the reaction like this, H2 plus I2. You know H2 plus I2 gives you 2 times HI. Look at the reacting species. Are the reacting species here atoms or molecules? I would say the reacting species are molecules. So, the stoichiometric coefficient here is 1. The stoichiometric coefficient here also is 1. So, I would say 2 molecules here are colliding and forming a product. And the number of reacting species, which can be atoms, molecules or ions, which must collide simultaneously to form the products. I would say 2 molecules are colliding right now to form the products. So, molecularity of this reaction is nothing but that's 2. Okay. For example, I've got the reaction like this, 2 times NO plus O2 makes it 2 times NO2. Again, your reacting species here are molecules. So here I can say 2 plus 1. 3 molecules are simultaneously colliding to form the products. So molecularity of this reaction is 3. Right? For example, I'm taking the reaction calcium carbonate gives calcium oxide plus carbon dioxide. What is the stoichiometric coefficient here? 1. You will directly say molecularity of this reaction is 1. What is molecularity basically? Molecularity is nothing but the number of reacting species, which can be atoms, ions, or molecules, colliding simultaneously to form the products. Colliding simultaneously to form the products. That defines molecularity. And based on molecularity, reactions are classified into certain types. That reaction whose molecularity is 1, you call the reaction as unimolecular reaction. That reaction whose molecularity is 2, you call it as bimolecular reaction. And that reaction whose molecularity is 3, you call it as trimolecular reaction. You call it as trimolecular reaction. Perfect. So based on molecularity, we can classify reactions into certain types. Unimolecular, bimolecular, or even trimolecular. Okay. My dear students, one more thing. For example, you have got the reaction like this. Half of H2 plus half of I2 gives HI. If I ask you what is the molecularity of this reaction, can you tell me? If I ask you what is the molecularity of this reaction, can you tell me quick? Can you tell me quick? What is the molecularity of this reaction? Everyone, quickly, give it a try. I want to say what you think about this. So you're saying 1, huh? You're just doing one thing, you are doing 1 by 2 plus 1 by 2 makes it 1. So as per you, the molecularity has to be 1, right? But that's not the case. See, you're saying technically half H2 molecule, you're technically saying half H2 molecule and half H2 molecule. You're technically saying half H2 molecule and half H2 molecule have collided, right? But can the molecule be half? Half molecule does not make any significance. Molecule can be 1, 2, 3, 4, like that, right? So what you have to do in such cases? In such cases, my dear students, whenever the stoichiometric coefficients are fractions, when the stoichiometric coefficients are fractions, what you are supposed to do is just convert them into their nearest natural numbers. Just convert them into their nearest natural numbers. How you are going to convert them into the nearest natural numbers? Just multiply this reaction with number 2. When you multiply this reaction with number 2, so 2 gets cancelled, I'll be getting H2. 2 and 2 gets cancelled, I'll be getting I2. It gives what? It gives 2 times HI. It gives 2 times HI. Now tell me one thing. What is the molecularity of this reaction now? I would say molecularity of this reaction now is 2. Molecularity of this reaction is 2. And whatever is going to be the molecularity of this reaction, same is going to be the molecularity of this reaction. So whenever the stoichiometric coefficients are fractions, convert those fractions into the nearest natural numbers first. Whatever reaction you get, whatever is its molecularity, same is going to be the molecularity of the old reaction. Okay? Remember this particular point, this is important. Now tell me one thing, can molecularity of the reaction be 0? Can molecularity of the reaction be 0? Molecularity 0, what does that mean? That means 0 molecules have collided. Does it make any significance? No. Can I say minus 5 molecules have collided? Does not make any significance. Can I say 2.43 molecules have collided? No. So can I say molecularity of the reaction? It can never be 0, it can never be negative, it can never be fractional. Molecularity of the reaction can never be 0, can never be negative, can never be fractional. Those reactions, my dear students, which have molecularity greater than 3, those reactions which have molecularity greater than 3, they are rarely found. They are rarely found. Because the probability of more than 3 molecules to collide simultaneously, the probability of more than 3 molecules to collide simultaneously is very rare, is very less. So remember, those sort of reactions whose molecularity is greater than 3, they are rarely found. Okay, they are rarely found. If in the examination it comes, you can directly say reactions with molecularity greater than 3 are not found as per your syllabus, as per your NCERT. Okay, as per your NCERT. You can say it directly like that. You can say molecularity cannot be greater than 3. Okay, but in reality, if you see in the higher classes, there are certain reactions which have got molecularity greater than 3, but those reactions are very rare. But if it comes in your examination, right, you are saying you're going to say that molecularity cannot be greater than 3. Okay. Now guys, one more thing. As I told you already, molecularity is always defined for which reactions? Molecularity concept is defined for elementary reactions. It is not defined for complex reactions. It is not defined for complex reactions. Okay. So, as I told you, since when you talk about the complex reaction, in the complex reaction, the steps involved are elementary. In the complex reaction, the steps involved are elementary. For example, understand, you have got the reaction NO plus Br2. It gives what? It gives NOBr2. It gives NOBr2. Now this NOBr2 plus NO makes it 2 times NOBr. Makes it 2 times NOBr. If I add these two, NOBr2 cancels out. NO plus NO makes it 2 times NO. Plus what? Plus Br2. It gives me what? It gives me 2 times NOBr. It gives me 2 times NOBr. Now this particular reaction is complex. This particular reaction is complex. And for complex reactions, molecularity does not have any significance. Molecularity is not defined. Molecularity concept is defined only for elementary reactions. But remember, when you talk about the complex reaction, the steps involved in the complex reaction, they are elementary. The steps involved in the complex reaction, they are elementary. And for elementary reactions, molecularity is defined. So I would say molecularity of this step is defined, molecularity of this step is defined, but molecularity of this overall reaction is not defined. So tell me, what is the molecularity of this reaction? This first step, 1 plus 1 makes it 2. What is the molecularity of this particular step? 1 plus 1 makes it 2, right? What is the molecularity of this particular reaction? It does not have any significance because it's a complex reaction, and molecularity term is not given for complex reaction. It is given for elementary reactions. I hope this is clear. I hope this is clear to everyone. Okay. Now, my dear students, after discussing molecularity, if you quickly summarize it, what is molecularity? It's a theoretical concept. It is given for elementary reactions, right? Now, as per collision theory, whenever reaction has to happen, reacting species must collide first. Now, the number of reacting species which collide simultaneously to form the products, that defines the molecularity, right? Molecularity can be 1, molecularity can be 2, molecularity can be 3. It cannot be 0, it cannot be negative, it cannot be fractional. Reactions with molecularity greater than 3, they are rarely observed. But in your case, you can remember it. Reactions cannot have molecularity greater than 3, right? In a complex reaction, molecularity does not make any significance. But the steps involved in the complex reaction, since they are elementary, so their molecularity is defined. Okay? Perfect, guys. Am I clear to everyone? Am I clear? Now, my dear students, there is something called as order of the reaction. There is something called as order of the reaction. If you talk about the order of the reaction, what is order? What is order? Order is basically the sum of powers. See, for example, understand. Let's say you have got the reaction N1A plus N2B. It gives, for example, product. This is the reaction. Now, for example, if I want to write the rate law says that R is equal to K, concentration of A raised power X, concentration of B raised power Y. This is your rate law. This is your rate law. My dear students, in the rate law, these powers, this X and Y. Let me tell you, this X is called as order with respect to A, and Y is called as order with respect to B. And if you take the sum of these two, X plus Y gives me the overall order of the reaction. It gives me the overall order of the reaction. So what is order basically? Let me tell you, order is nothing but, it is the sum of these powers in the rate law. Sum of the powers in the rate law is what you call as order, nothing else. Yeah? Perfect? Now this order, in order to write the order, in order to calculate the order, what do we need to write? We need to write law of mass action. In order to calculate the order, we need to write law of mass action. This law of mass action, what is it? It is experimentally determined. It is experimentally determined. Therefore, your order is also what? Order will be also experimentally determined. Order will be also experimentally determined. Now, there are few things about order, my dear students, which you are going to remember and which have been seen experimentally. There are some things which have been observed experimentally about order, which you are going to remember. Order of the reaction can be order of the reaction can be, it can be 0, it can be positive, it can be fractional, it can be even negative. Order of the reaction, it can be 0, positive, fractional, even negative, right? Unlike molecularity, molecularity cannot be 0, right? Molecularity cannot be fractional. Perfect. Molecularity cannot be fractional. But order can be 0, order can be fractional, order can be even negative. Okay. Is order theoretical or experimental? Order is experimentally determined term. Order is experimentally determined term. There is one very, very, very important point about order. What is that? For elementary reactions, remember, order and molecularity both are same. For elementary reactions, order and molecularity both are same. Both are same. Try to understand what it means. See, for example, you have got the reaction 2A plus B. It gives C. Let's say this reaction is elementary. Let's say this reaction is elementary. If this reaction is elementary, whether you want to calculate its rate with the help of rate law, or you can calculate its rate with the help of law of mass section, both are going to give you the same results. Because for elementary reactions, law of mass section is truly valid. We know that already. Okay. So I would say its rate would be equal to R is equal to K, concentration of A. It was supposed to be raised per X, but X value, when you calculate experimentally, it will come out to be same as the value of this particular stoichiometric coefficient. That's 2. Similarly, concentration of B raised per 1. So this is what? This is your rate law. This is your rate law. This is your rate law basically for this elementary reaction. Perfect. So as per this rate law, what should be the order of this reaction? Order of this reaction should be 2 plus 1, 3. If I ask you what is its molecularity, since the reaction is elementary, and for elementary reactions, molecularity is defined. So molecularity of this reaction is 2 plus 1 also 3. Molecularity is also 3. So remember, whenever you see an elementary reaction, for elementary reactions, law of mass section, for elementary reactions, I would say order and molecularity, they're always going to be same. They're always going to be same. Point number 1. Right? Perfect. Am I clear, guys? Law of mass section is theoretical, rate law is experimental. Okay, I have written it mistakenly as this is rate law. Okay, now it's clear. Right? So this is one more point which I would want every one of you to remember. For elementary reactions, remember order and molecularity, they are always same. Now guys, there is one more thing which I would want to tell you. What is that thing? A zero order reaction can never be elementary. Can never be elementary. It is always complex. A zero order reaction, it can never be elementary. It's always complex. Okay? A zero order reaction is never elementary. It's always complex. What does it mean? What does it mean? A zero order reaction can never be elementary. Zero order reaction is the one whose order is 0. Whose order is 0. A zero order reaction is the one whose order is 0, right? But dear students, a zero order reaction can never be elementary. If the zero order reaction was elementary, then its molecularity should have been 0 too. Because for elementary reactions, order and molecularity are same. But molecularity is equal to 0. Does it have any significance? It does not have any significance. Molecularity cannot be 0. Molecularity cannot be 0. You know that already. So, a zero order reaction, it can never be elementary. It's always complex. Because if the zero order reaction is elementary, then its molecularity should be 0. Molecularity is equal to 0 does not have any significance, people. Okay? I believe this particular point is also clear to you. So, for elementary reactions, order is equal to what? For elementary reactions, order is equal to molecularity, and when it comes to your zero order reactions, zero order reaction can never be elementary. It's always complex. Okay. Now, one more important thing which you should know: what are the units of rate constant? What are the units of rate constant? My dear students, general unit of rate constant unit. Let's say you have got the reaction A gives B. This is the reaction. I'm assuming that order of this particular reaction is n. This n can be anything, 0, 1, 2, 3, whatever. I've got a reaction whose order is equal to, for example, n. Now, first of all, rate constant units are simply going to be moles liter inverse raised power 1 minus n into second inverse or minute inverse or hour inverse, depending on the units of time. Or it's going to have one more unit. What is that? Rate constant can have unit as ATM raised power 1 minus n second inverse. If pressure is in ATM, time is in seconds. As simple as that. Directly you are going to remember mole per liter raised power 1 minus n into second inverse, ATM raised power 1 minus n into second inverse. Now what is this n over here? N represents order of the reaction. So my dear students, if you have a zero order reaction is the one whose n value is 0. So if n value is 0, what are going to be the units of rate constant? Put the value of n as 0. 1 minus 0 is 1. So it's going to be mole per liter per second, or it's going to be ATM raised power 1 minus 0. So it's going to be ATM second inverse. Simple. For example, you have got the first order reaction. For first order reaction, put the value of n as 1. So 1 minus 1, 0. Anything raised power 0 is 1. So I'll be left with second inverse. Right? 1 minus 1, 0. Anything raised power 0 is 1. That means second inverse. For example, you are given with the second order reaction. N value is 2. If n value is 2, put the value of n as 2 here. 1 minus 2 is minus 1. So the units of K would be mole liter inverse raised power 1 minus 2 is minus 1 and second inverse. Or you can write units of K as ATM raised power 1 minus n. 1 minus 2 is minus 1 and second inverse. Perfect. Perfect, guys. So these are the units of rate constant which you are going to remember. So I would say rate constant units, they depend on what? They depend on the order of the reaction. They depend on the order of the reaction. Perfect. For example, this is the sort of question. Let's say this is the sort of the question. The question is, for a chemical reaction A gives B, it is found that the rate doubles when the concentration of A is increased 4 times. Find the order of the reaction. These sort of questions, how do we deal with them? For example, you have got the reaction A gives B. I'm assuming that order of this particular reaction is n. Now, I want to calculate order as per the question. I want to calculate order as per the question. So, in order to calculate order, what do we need to write? We need to write the rate law. So, can you write rate law here? I'll say R is equal to K, concentration of A raised power n, right? Raised power n. Now, in the question, they have mentioned that it is found that the rate doubles. Rate doubles. So, earlier it was R, now it is 2R. Rate doubles. When? When the concentration of A is increased 4 times. Earlier it was A, now it is 4 times A. Perfect. Call this equation 1. Call this equation 2. Divide the two equations. 2 divided by 1. 2 divided by 1. R cancels out. So, this is 2. K and K cancels out. A raised power n cancels out. This is 4 raised power n. So, what should be the power of 4? So that it comes equal to 2. Power of 4 should be equal to 1 by 2. So n value is equal to 1 by 2. N is what? N is the order of the reaction which I was supposed to calculate. Done and dusted. So these sort of simple questions you should be able to solve, guys. For example, this is the question. The rate of the reaction becomes half when the volume of the vessel is doubled. So first of all, this is the reaction. Let its order be equal to n. So first of all, in order to calculate order, what do I need to write? I need to write rate law. So write the rate law. R is equal to K, concentration of A, raised power order. Order is n. Order is n, right? Order is n. Now, as per the question, they are saying that the volume of the vessel is doubled. In this expression, do you see volume anywhere? No. But I can convert this expression in the form of volume. I can convert this expression in the form of volume. Okay. I can say R is equal to K. Instead of concentration of A, I can write moles of A divided by V raised power n. This equation number 1. Now, as per the question, the rate of the reaction becomes half. So, earlier it was R. Now, it's R by 2. Rate of the reaction becomes half when the volume of the vessel is doubled. So, earlier the volume was V. Now, it's 2V. Raised power what? Raised power n. This equation number 2. So, I got 2 equations. I got 2 equations, people. So, if I divide the 2 equations, for example, if I'm dividing equation 1 with equation 2, what do I get? Equation 1 by equation 2, RR gets cancelled. 1 by 1 by 2 comes out be 2 is equal. K and K cancelled, NA by V cancelled. So, it becomes 2 raised power n. So, which is only possible if n value is equal to what? N value is equal to 1. And what was this n? N was the order of the reaction. N was the order of the reaction. I believe this particular point is also clear. I believe this particular point is also clear. Look at this reaction, for example. The reaction is A plus B gives C. Rate is doubled when the concentration of B is doubled. and rate increases by the factor of 8 when the concentration of A and B both are doubled. Calculate the order. Calculate the order. Try to understand. First of all, in order to calculate the order, people, what do I need to write? I need to write the rate law. Rate law says that R is equal to K, concentration of A, raised power X, concentration of B, raised power Y. This is rate law. This is rate law. Now the question says, the rate is doubled. So if it was R, now it is 2R. When is rate doubled? Rate is doubled when the concentration of B is doubled. So K, concentration of A raised power X. This is going to be, instead of B, I'll write 2B raised power Y. So rate is doubled when the concentration of B is doubled. And rate increases by the factor of 8. So if the rate earlier was R, now it is 8R. When is it 8R? When the concentration of A and B both are doubled. So K, this is going to be 2A raised power X and this is 2B raised power Y. So how many equations I got? I got 3 equations. Now I just have to solve these 3 equations. I just have to solve these 3 equations, guys. I just have to solve these 3 equations. So let's do one thing. Let's divide equation 2 with equation 1. When you divide 2 with 1, R gets cancelled. I'm left with 2 is equal. K and K cancelled. A power X cancelled. BY cancelled. So it's going to be 2 raised power Y. So 2 raised power Y is equal to 1. So Y value is equal to what? Y value is equal to 1. Y value is equal to 1. Similarly, if I divide equation 3 with equation 2, if I divide equation 3 with equation 2, so R and R gets cancelled. A divided by 2 is how much? 4 is equal. This 2b entirely cancelled. A raised power X is cancelled. So I'll be left with only 2 raised power X, which tells you that X value has to be equal to 2. 2 raised power X is equal to 4. That means X has to be equal to 2. So X is 2, Y is equal to 1. So overall order of the reaction, if I ask you, overall order of the reaction is going to be X plus Y. So 2 plus 1 is 3. So 3 is the overall order of the reaction. Am I clear with this as well? Did you understand this sort of a question? So guys, whenever this sort of a question is asked, first of all, for the reaction, you are supposed to write the rate law. And when you write the rate law, after that, you are supposed to make certain equations, divide those equations and get the value of X and Y. That is something which you do in these sort of questions. Say yes or no if you got it. Tell me quickly in the chats if it is super clear to everyone. Done? Perfect. I hope all of this is clear to everyone. Now guys, there is one more type of the question that's asked. That is, how do we calculate rate of the reaction? How do we calculate order of the reaction experimentally? How do we calculate order of the reaction experimentally? Okay. It will be always mentioned in the question whether the reaction is complex or elementary. Don't worry about that. I'm not going to give any break yet. Just wait. What have we studied yet? Nothing. Already there was a glitch for like 15 to 20 minutes. So those 15 to 20 minutes were wasted. So please have a look on the question. Okay. See guys, how do we calculate the order of the reaction experimentally? Sometimes this sort of a question will be given to you. Okay. There are some experiments which have been carried out. Their data is mentioned in the question. And from the data, my dear students, we are supposed to calculate. From the data, we are supposed to calculate what? From the data, we are supposed to calculate the order of the reaction. So we know one thing. In order to calculate the order, what do we need to write? We need to write the rate law. And rate law for this reaction, how can I write? R is equal to K. It's going to be concentration of NO raised power X, concentration of H2 raised power Y. This is how you write the rate law. Is it done? Now, as per experiment number 1, rate of the reaction is how much? 3 into 10 raised power minus 5. So, instead of R, instead of rate, I'm writing 3 into 10 raised power minus 5 is equal to K. What is the concentration of NO in this first experiment? It is 5 into 10 raised power minus 3 raised power X. What is the concentration of H2 in the same first experiment? It is 2.5 into 10 raised power minus 3 raised power Y. I'm calling this as equation number 1. I am calling this as equation number 1. Now, similarly, my dear students, just put the second experiment data in the same equation. What is the value of R in the second experiment? It is 9 into 10 raised power minus 5 is equal to K, I'm writing as such. Concentration of NO in the second experiment, how much is that? It is 15 into 10 raised power minus 3 raised power X. What is the concentration of H2 in the second experiment? It is 2.5 into 10 raised power minus 3 raised power Y. This is equation number 2. Now, my dear students, put the third experiment data in the same equation. What is the value of R in the third experiment? It is 36 into 10 raised power minus 5 is equal to K. Concentration of NO, how much is that? 15 into 10 raised power minus 3 raised power X. H2, 10 into 10 raised power minus 3 raised power Y. So this is equation number 3. So how many equations you got? You got 3 equations. How did we get all these 3 equations? First of all, we wrote the rate law. And in the rate law, I just put these 3 experiments. I got 3 equations. Now we have to solve these 3 equations and we'll be done. And how do we solve these equations? There's a way to solve them. Let's do one thing. Let's divide equation 2 with equation 1. If I divide equation 2 with equation 1, 10 power minus 5, 10 power minus 5 cancels out. 9 by 3 comes out with 3 is equal. K and K gets cancelled out. This entire term gets cancelled out. This will be 15 into 10 raised power minus 3 divided by 5 into 10 raised power minus 3. 15 by 5 is 3. So this becomes 3 raised power X. Rest all the terms are cancelled. So I can say X value here is equal to 1. I got the value of X by dividing 2 equations. Now if I do one more thing, if I, for example, divide equation 3 with equation 2. If I divide equation 3 with equation 2, so 10 power minus 5, 10 power minus 5 cancels out. 36 divided by 9 is 4 is equal to K and K cancels out. This entire term cancelled out. 10 in 10 raised power minus 3 divided by 2.5 into 10 raised power minus 3. That comes over to 4. So it's going to be 4 raised power Y. 4 raised power Y is equal to 4. That means Y value is equal to what? Y value is equal to 1. So you got the value of X, you got the value of Y. So what is going to be the overall order of the reaction? I would say overall order of the reaction is 1 plus 1. That comes out to be 2. Will you be able to solve this sort of a question, people? Can you tell me that? Will you be able to solve this sort of a question if it comes? What are you supposed to do? You're supposed to do one thing. Make the rate law. In the rate law, fit the experiments, right? Fit the information given in the experiments, divide the equations, and get the value of X and Y, which you were supposed to calculate. I believe this is clear to everyone. If it is clear, let me know once in the chats. Let me know once in the chats, people. Quickly. Quickly tell me in the chats. Everyone. Now let's talk about something called as mechanism of the reaction, and let's see what kind of questions can be asked from the mechanism. What is mechanism basically? Mechanism is nothing but it is a series of elementary reactions. The series of elementary reactions through which the overall complex reaction occurs. The series of elementary reactions through which the overall complex reaction occurs is what you call as mechanism. Now, in the mechanism, some reactions are fast, some reaction will be slow. And the slowest step is what you call as rate determining step. For example, see, let's say you got the reaction like this. A plus B, it gives C. This is the reaction, for example, right? Now, my dear students, C plus D, it gives E. This is one more reaction. Here I'm writing fast. Here I'm writing slow. Okay. Now, if I add these two reactions, C and C gets cancelled out. So I'll be getting A plus B plus D. It gives what? It gives E. Is this particular reaction getting completed in one step? No. This reaction is getting completed in more than one step. So this is my complex reaction. This is my complex reaction. Now, my dear students, you know already the steps which are written to write the overall complex reaction. It is basically your mechanism. The series of elementary reactions through which overall reaction happens. The series of elementary reactions through which overall reaction happens is your basically what? is your basically mechanism. Now, in the mechanism, the slowest step, is what you call as the rate determining step. This particular step here is going to determine the overall rate of the complex reaction. So, overall rate of this particular reaction is determined by the slowest step. And that slowest step is called as the rate determining step. Now, the point is, if you want to calculate order of this complex reaction, my dear students, if you want to calculate order of this complex reaction, what we have to do is, if we have to calculate order of this complex reaction, we have to write the rate law. But remember, we have to write the rate law of what? We have to write the rate law for the slowest step. So if I want to write the rate law for this slowest step, how do I write it? I'll be writing R is equal to rate constant K, concentration of C, raised by X. But this is elementary. For elementary reactions, X value is equal to stoichiometric coefficient multiplied by concentration of D, raised by Y. Y here will be 1 as well. So this is your rate law. My dear students, remember one thing. Rate law must be free from the intermediate. What is intermediate? When you add these two reactions, that particular one which gets cancelled, when you add the reactions, the C and C gets cancelled. The one that gets cancelled is your intermediate. So in the reaction, I would say C is my what? C is my intermediate. And remember, rate law should be free from intermediate. So this is the rate law. Is this free from intermediate? It's not free from intermediate yet. So we have to make sure that this rate law becomes free from intermediate. How do we make sure that rate law becomes free from intermediate? What we have to do at that point of time? Understand what we have to do at that point of time. See guys, for example, since this reaction, it's given in equilibrium. So its equilibrium constant will be, for example, KEQ. Do you know how to write the expression for equilibrium constant? Yes, we know it. When you write the expression for equilibrium constant, you start with the product. So it's concentration of C raised by stoichiometric coefficient 1 divided by its concentration of A raised by stoichiometric coefficient 1. It is concentration of B raised by stoichiometric coefficient 1. So can we eliminate C from here? I would say C would be equal to KEQ multiplied by A multiplied by B. Now put this value of C over here in this particular expression. I'll say R is equal to K. Instead of concentration of C, I wrote KEQ multiplied by concentration of A multiplied by concentration of B, and there is already D over here, right? Perfect. So I'll write R is equal to, this is constant, this is constant. Multiplication of two constants will be a new constant, K dash. Concentration of A, concentration of B, concentration of D. Now is this rate law free from intermediate? Yes, this rate law now is free from intermediate. Right? So I would say the overall order of the reaction will be 1 plus 1 plus 1, which comes out to be 3. So I'll summarize it, I'll conclude it. When it comes to mechanism is nothing but the series of elementary reactions through which the overall reaction occurs. Number 1. Number 2, in the mechanism, there will be a slowest step, and that slowest step that determines the overall rate of the reaction, which is called as the rate determining step. In order to calculate order, we need to write rate law. But rate law is written for that particular step, which is the slowest step. And your rate law should be free from intermediate. Okay? Your rate law should be free from the intermediate. Let's try to solve certain questions so that you will master this concept as well. Look at this question, guys. Mechanism of the reaction is given. Calculate the overall order of the reaction. In order to calculate the order of the reaction, what do we need to write? We need to write rate law. Rate law is written for which step? Slowest step. Because slowest step is the rate determining one. So let's write the rate law for this step. I'll write R is equal to K. K is the rate constant. Concentration of O raised power 1. Concentration of O3 raised power stoichiometric coefficient 1 here. Right? Because this is elementary. For elementary reactions, law of mass action and rate law both are same. You know that. Correct? Now in this rate law, do you see any intermediate? What is intermediate? When you add these reactions, this O and O gets cancelled. The one that gets cancelled is intermediate. So in the rate law, there is intermediate. So we have to make sure that we eliminate this intermediate. How do we eliminate this intermediate? For that, particular reaction is going to help, which is at equilibrium. So this reaction is at equilibrium. Write the expression of equilibrium constant. Equilibrium constant expression. Start with the product. So I'll write concentration of O2 raised power 1, concentration of O raised power 1 divided by concentration of O3 raised power 1. So I would say concentration of O is nothing but it will be KEQ multiplied by concentration of O3 divided by concentration of O2. Got it? Now guys, put this value of O over here. So I'll say R is equal to K. What is the concentration of O? Concentration of O is nothing but KEQ multiplied by O3 concentration divided by O2 concentration, and here there is already one O3. So O3 makes it, first of all, K and K, constants, new constant K dash, O3 makes it, O3 ka square, and it's going to be O2 raised power minus 1. So do you see one thing? The powers are 2 and minus 1. The powers are 2 and minus 1. So what is going to be the overall order of the reaction? If you look carefully, overall order of the reaction is going to be 2 plus minus 1. The value comes out to be 1. So this is the overall order of the reaction. This is how you solve these sort of questions. I hope it's clear. And if it is clear, people, let's try to solve one more question. Look at this particular question. The question is, mechanism of the reaction is given as, we have to calculate order of the reaction. And in order to calculate order, what do we need to write? We need to write rate law. Write the rate law. For which step we are going to write the rate law? For the slowest step. When you write rate law for the slowest step, I'll say R is equal to, its rate constant is K1. It is concentration of NO3 raised power 1, concentration of NO raised power 1. Now, is this rate law free from intermediate? Talk about intermediate. When you add these two steps, NO3 gets cancelled out. So NO3 is your intermediate, which should be out of the rate law, which should be eliminated from the rate law, right? And how do we eliminate the intermediate? We eliminate intermediate by the help of that particular reaction, which is at equilibrium. Since equilibrium constant of this reaction is KEQ, if I want to write its expression, it's going to be concentration of NO3 raised power 1 divided by concentration of NO raised power 1 and concentration of O2 raised power 1, right? Now you can eliminate NO3 from here. You can say NO3 is equal. It's going to be KEQ multiplied by concentration of NO multiplied by concentration of O2. Now put the value of NO3 here. When you put the value of NO3 here, R is equal to K1. NO3 concentration is what? It is KEQ multiplied by NO concentration multiplied by O2 concentration. And already you have got NO concentration here. So NO makes it NO ka square. So R will be equal to constant, new constant K dash. So this is going to be NO ka square and this is going to be O2 raised power 1. Check this rate law now. Now this rate law is free from intermediate. If it is free from intermediate, that means the overall order of the reaction is 2 plus 1. So overall order of the reaction is 2 plus 1. That comes out to be 3. Did you understand, people? How these sort of questions are to be solved? Tell me once in the chats quick. Did you understand how these sort of questions are to be solved? Quickly. Yeah? Perfect. Perfect. Let's move on to the zero order reactions now. Let's move on to the zero order reactions now. What do you think will be the zero order reactions? What do you think are the zero order reactions? Zero order reactions are simply the ones wherein you see the order equal to 0. Wherein you see the order equal to 0. Or I can say, these are the reactions in which rate does not depend on the concentration of reactant. These are the reactions in which rate does not depend on the concentration of reactant. Try to understand these zero order reactions in detail. See guys, first of all, I'm not going to derive any expression here. There are a lot of expressions here in zero order. I'm not going to derive any because derivation is of no use to us. Derivation is of no use to us. I'm just going to give you the results and we'll utilize those results in the questions. Okay? We have got nothing to do with what? We have got nothing to do with any sort of derivation here. So understand what I'm going to do. For example, you have got the reaction like this. A gives B. Let's say its rate constant is K. and I'm assuming order of this particular reaction is 0. I'm assuming order of this particular reaction is 0, right? For example, I say time t is equal to 0. At time t is equal to 0, at time t is equal to 0, concentration of reactant always is equal to A naught. A naught represents concentration of reactant at time t is equal to 0. And concentration of product right now will be 0. Concentration of product right now will be 0 because the reaction has not started yet. Now let's say when the reaction proceeds, the concentration of reactant will decrease with time. Concentration of product will increase with time. So at time t, let the concentration of reactant be AT, let the concentration of product be BT. At time t is equal to 0, concentration of reactant was A naught. Now at time t, the concentration of reactant left is AT. And the concentration of product that got formed is BT. Now if you look carefully, guys, try to understand. First of all, if I want to write the rate law says that R is equal to rate constant is K, concentration of A raised per order is 0. Since you have got only one reactant here, so whatever is order with respect to A, same is going to be the overall order of the reaction. Overall order of the reaction is 0. So this power has to be 0 here. So you can say R is nothing but R is equal to K. If R is equal to K, what does that mean? That means the rate is independent of concentration of reactant. That means rate is independent of concentration of reactant. And any such reaction wherein rate is independent of concentration of reactant, you call that reaction as the zero order reaction, right? Now, my dear students, in zero order reactions, the first equation which you are going to remember, that is going to be AT is equal to A naught minus KT. This is the first equation which zero order reactions are going to follow. You call this particular reaction, you call this particular equation as the integrated rate equation. How it comes, you have got nothing to do with that. Just remember the result directly. AT is equal to A naught minus KT. What is AT? AT is the concentration of reactant left at time t. A naught. A naught is the initial concentration of reactant. Okay. T is the time interval. T is the time interval in which the concentration of reactant goes from A naught to AT. Okay. This is the first equation which you need to know. This is the first equation which you need to know. Perfect. My dear students, second thing which you need to know about zero order reactions. What is that? That is half-life. Half-life is represented by T 50%. Or you can represent it by T1 by 2. Now, how do we calculate half-life? What is the expression to calculate half-life? What is the expression to calculate half-life? I'll say T1 by 2 is equal to A naught divided by 2K. This is the equation with the help of which you calculate half-life of the reaction. What is half-life? Half-life is simply defined as the time taken to complete time taken to complete 50% of the reaction. Time taken to complete 50% of the reaction is what you call as half-life. And when it comes to zero order reactions, half-life is equal to A naught divided by 2K. The third point about the zero order reactions, what is that? That's what you call as completion time. Completion time, which I represent with T 100%. How do we define completion time? Completion time is nothing but it is the time taken. It is the time taken to complete 100% of the reaction. Time taken to complete 100% of the reaction. Time taken to complete 100% of the reaction. So remember your T 100%. It is calculated by the formula A naught by K. A naught by K. Okay. These are three results which I gave you till now. First of all is the integrated rate equation. AT is equal to A naught minus KT. Second is your half-life. A naught divided by 2K. Third is your completion time. Completion time is calculated by the formula A naught divided by K. Right? The fourth parameter. What is that? That is concentration of product. Concentration of product at time t. How do we calculate the concentration of product at time t? My dear students, first of all, concentration of product at time t is represented by Bt. So how do we calculate the concentration of B at time t? How do we calculate concentration of B at time t? Remember directly, concentration of B, concentration of product at time t is nothing but it is K multiplied by T. Now, if you want to see also how it's to be calculated, if you want to see also, you can have a look as well. You can have a look as well how it's calculated. See guys, for example, the reaction is A gives B. Okay. Let's say at time t is equal to 0, the concentration of reactant is A naught. This is 0. At time t, the concentration of reactant is AT, the concentration of product is BT. What do I need to calculate? I need to calculate this value. I need to calculate this value. I need to calculate this value. My dear students, at time t0, the concentration of reactant is A naught. At time t, the concentration of reactant left is AT. Initially, the concentration of reactant was A naught. Now, at time t, the concentration of reactant left is AT. So, how much concentration of reactant got converted into product? If I ask you, how much concentration of reactant got converted into product? I started with A naught and I'm left with AT. So, A naught minus AT. This is the concentration of reactant which got converted into product. This is the concentration of reactant which got converted into product. Now, my dear students, A naught you can write as such minus. Few minutes back, I told you AT is equal to A naught minus KT. So, A naught cancels out. The value comes out to be K multiplied by T. So, this is the concentration of B at time T, which you were supposed to calculate. Which you are supposed to calculate. Am I clear with this? Am I clear with this, people? Everyone? Am I clear with this? So this was our fourth parameter, that is concentration of product at time t. Now the fifth parameter, guys, which you need to know about zero order reactions. That is, how do we calculate degree of dissociation? Degree of dissociation is represented by alpha. Remember directly, degree of dissociation alpha is equal to KT divided by A naught. Degree of dissociation directly is equal to alpha is equal to KT divided by A naught. This is the result which is valid for zero order reaction. Okay. So first is integrate rate equation, which you have to remember. AT is equal to A naught minus KT. Second is your half-life. Half-life is A naught divided by 2K. Completion time is A naught divided by K. Concentration of product at time T is KT. Alpha, degree of dissociation. How do we calculate it? It is formalized KT divided by A naught. KT divided by A naught. I hope this point is also clear to everyone. Okay. Now, there are some graphs which I want to make about the zero order reactions. The first graph I'm going to plot, that is between the rate versus concentration of reactant. Rate versus concentration of reactant. And my dear students, as you know, for zero order reactions, R is equal to K, concentration of A raised power 0, right? Anything raised power 0 is 1. So R is equal to K. So rate is independent of concentration of reactant. So if you want to increase the concentration of reactant or decrease the concentration of reactant, nothing happens to rate. So this is the graph here between rate versus concentration of reactant. Okay, for a zero order reaction. For a zero order reaction. Okay. Second graph which I'm going to make here, what is that? The second graph which I'm going to make, that is going to be between AT and T. That's going to be between AT and T. Now, if I ask you, AT is equal to A naught minus KT. You know it already. AT is equal to A naught minus KT. Now, AT you are plotting along y-axis. T you are plotting along x-axis. This becomes your M. This becomes your C. The sign is minus. Y is equal to minus mx plus C. Y is equal to minus mx plus C is a straight line with a negative slope. And its slope, if I ask you, its slope is equal to minus K. Okay. This one more graph when it comes to zero order reaction. Right? Similarly, for example, I'm asking you to plot a graph between T half and A naught. T half and A naught. Since you know, T half is equal to how much? T half is equal to A naught by 2K, or I can say 1 by 2K into A naught. T half you are plotting along y-axis. A naught you are plotting along x-axis. This becomes my M. Y is equal to mx. Straight line passing through origin. If you talk about its slope, its slope is nothing but 1 by 2k. Its slope, m, is nothing but 1 by 2k. Similarly, if you talk about T 100% versus A naught, T 100% versus A naught, T 100% versus A naught is again a straight line like this, and its slope is equal to 1 by k. 1 by k. Okay. Similarly, my dear students, there is one more graph which you need to know about zero order reactions. That is alpha and A naught. That is alpha and A naught. Is alpha and A naught directly proportional or inversely? They are inversely proportional. And whenever you are supposed to make a graph between two variables which are inversely proportional to each other, the nature of the graph is rectangular hyperbole. So this graph is called as rectangular hyperbole. Okay, these are some graphs which you need to remember when it comes to what? When it comes to your zero order reaction. Okay, and my dear students, there are few examples of zero order reactions as well. Well, these are the examples which directly you are going to remember. These are some examples of the zero order reactions which directly you are going to remember. Okay, right? Similarly, there is one more parameter, my dear students, about zero order reactions. Let me tell you that parameter too. That's also important. For example, you have got the reaction like this. A gives B, whose rate constant is K. For example, here I am making a table. Here I am making a table. The table is between concentration of A versus time. Concentration of reactant versus time. Concentration of reactant versus time. Let's say at time T1, a second guys, I think there is electricity cut. Just a second. Okay, it's fine now. All right, see guys. So let's say at time T1, the concentration of reactant is A1. Let's say at some time T2, the concentration of reactant is A2. At some time T3, concentration of reactant is A3. At some time T4, the concentration of reactant is A4. These are the things which I'm assuming. Let's say at time T1, the concentration of reactant is A1. At some time T2, the concentration of reactant is A2. Time T3, concentration of reactant A3. Time T4, concentration of reactant A4. Remember, my dear students, if the time interval is same, what does that mean? That means if T2 minus T1 is equal to T3 minus T2, which is equal to T4 minus T3. This is what we call a same time interval. My dear students, if in the same time interval, A2 minus A1 will be equal to A3 minus A2, will be equal to A4 minus A3, remember at that point of time, the order of the reaction is 0. This is a simple trick which you are going to remember. Whenever you will be given with a table, and in the table some data is given like this, you have to first of all check whether the time interval is same or not. If in the same time interval A2 minus A1 is equal to A3 minus A2 is equal to A4 minus A3, remember the order of the reaction at that point of time is equal to what? The order of the reaction at that point of time is 0. Okay. Now what kind of questions can be asked from zero order? What kind of questions can be asked from zero order? This is the first question. Look at the question. A zero order reaction is 20% completed in 10 minutes. Okay. At what time it will be 80% completed? At what time it will be 80% completed? At what time it will be 80% completed? I'll give you a trick to solve this particular question. See, a zero order reaction is 20% completed in 10 minutes. So T 20% is equal to 10 minutes. Right? As per the question, at what time it will be 80% completed? T 80% needs to be calculated. Time taken to complete 20% is equal to 10 minutes. Time taken to complete 80% needs to be calculated. So I'll just write one thing. See, T 20% divided by T 80%. T 20 divided by T 80. Just remove this 0 and 0. What do I get? I get 2 by 8. If I remove this 0 and 0, I got 2 by 8. Right? I got 2 by 8. Now, this T 20% is how much? Is 10 divided by T 80% needs to be calculated. So, when you cross multiple, you can say T 80% comes out to be how much? 80 divided by 2. That is 40 minutes. So, time taken to complete 80% is equal to 40 minutes. Understood? Yes or no? Yes or no? Simple trick. For example, sometimes they give a question like this. Time taken to complete 20% of the reaction is equal to 10 minutes. Calculate the time taken to complete 60% of the reaction. Let's say the question is like this. What do? T 20% divided by T 60 is equal to 0, 0 cancel, it will be 2 by 6. 2 by 6 is basically 1 by 3. And T 20% is already 10 divided by T 60% needs to be calculated. We already know it's 1 by 3. So T 60% will come out to be 30 minutes. Yeah? Understood? Okay, for example, you have got a question like this. For a zero-order reaction A gives B, it was observed that at the end of an hour, 75% of A has reacted. 75% of A has reacted. That means 75% reaction has got completed. So technically T 75% is given us as 1 hour in the question. T 75% is equal to 1 hour, right? And 1 hour means how many minutes basically? 1 hour means, see, in the question, T 75% is given to be as 1 hour. 1 hour means how many, let's say minutes? 60 minutes, right? 1 hour means 60 minutes. Okay. At what time A will be 10% unreacted? 10% unreacted means 90% completed. So T 90% needs to be calculated. Do you understand? So if I write T 75 divided by T 90, T 75 divided by T 90 will be equal to what? Will be equal to, it's going to be what? It's going to be simply 75 divided by 90. And in the question, it's given to me as 60 divided by what? Divided by T 90%. So when you cross multiple, I think you'll be getting the answer. Right? Is that clear, guys? Can you tell me quickly in the chats? So when you cross multiple, T 90% will come out to be how much? 72 minutes. Do you understand how do we deal with these questions? I want everyone to say it once if it is clear. I want everyone to say it once if it is clear. Okay. For example, look at this question. Some table is given to me. We have to calculate rate constant of the reaction. Just understand. At time t is equal to 0, concentration of reactant is given. And we know at time t is equal to 0, the concentration of reactant is represented by what? The concentration of reactant is represented by A naught. At time t is equal to 0, the concentration of reactant is represented by A naught, which is 1 molar. So you see at t is equal to 120 seconds, the concentration of reactant left is 0 molar. Understand this point. At 120 seconds, the concentration of reactant left is 0 molar. That means this is the time taken to complete 100% of the reaction. So this is T 100%. So at 120 seconds, 100% reaction has got completed. That's why reactant left is how much? That's why reactant left is 0 molar. Now, tell me one thing. Do you know the formula of T 100%? T 100% is nothing but A naught by K. So can I say K will be equal to A naught divided by T 100%? What is A naught? A naught is 1, right? T 100% is 120 seconds. So this is 1 by 120. Since the reaction is zero order, so moles per liter per second. This is the value of the rate constant which I was supposed to calculate. Understood? Since the completion time was given, I use the formula for completion time and we are done. And we are done. Look at this particular question. Rate constant of the reaction is given. K value is given to us. 0.6 into 10 raised power minus 3 moles per liter per second. This is rate constant. This is rate constant. If the concentration of A is 5 molar, calculate the concentration of B at 20 minutes. Calculate the concentration of B at 20 minutes. Concentration of B means concentration of product, right? And I already gave you one formula. Concentration of product at a time t. Concentration of product at some time t is nothing but K multiplied by T. So I can say concentration of product at 20 minutes will be equal to K. K value is how much? 0.6 into 10 raised power minus 3. T is how much? 20 minutes. 20, but this is in minutes. This was moles per liter per second. This is in minutes, so convert this in seconds. So multiply with 60. The value comes out to be 0.72 molar. This is the concentration of B, which is formed at 20 minutes. Understood, people? Is it clear? So with this, zero order reactions are over. Now we are going to take a small break. And after the break, we are going to start the first order reactions. Okay? This chapter will further take 1.5 hours more. Tell me first of all, are all the things clear till here? Are all the things clear, guys? Quickly. Question practice will be tomorrow. Question practice will be tomorrow. Okay, I'm giving you your lunch break. You can have your lunch. It is 1:15 almost. 1:45, huh? So I'm giving you 30 minutes break. Finish your lunch and come back exactly on time. Okay, come back exactly on time. I'll be starting exactly at 1:45. See you. See you, guys. But be back on time, huh? Guys, can you hear me? Am I audible, visible again? Can you all hear me? Quick, 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 quick. Am I audible, visible again to everyone? Let me know once in the chats. Yes, I'm going to share the handwritten notes. Yes, yes, yes. I will be doing that. I will be doing that. Don't worry. Just tell me once if all of you can hear me properly now. If I'm perfectly audible and visible to everyone. Yes, yes, I'm done with my lunch. What about you guys? Are you done? Are you guys done or not? All right. So whatever things we discussed till now, is every single thing clear till now? Can you let me know once in the chats quick? Whatever things we discussed till now, is every single thing clear? Is every single thing clear, guys? Can you tell me once in the chats? Whatever things we discussed till now, is every single thing clear? Don't ask me about the time, how much time it's going to take. It's going to take till 10, till 11 maybe. Yeah? All right, got it. So let's move on then. Let's move on, let's move on. My dear students, you can mark the heading as first order reaction. First order reactions. What are the first order reactions and what are its parameters? Let's try to discuss about them one by one. Okay? See, guys. For example, I'm taking a reaction A gives B, whose rate constant is K. Since, my dear students, we have got only one reactant here, so I can say whatever is the order with respect to A, that is what will be the overall order of the reaction. And I'm assuming overall order of this particular reaction is nothing but it is 1. Overall order of the reaction is equal to 1. Okay. Now again, at time t is equal to 0, let the concentration of this reactant be A naught and this is going to be 0. At time t, let the concentration of reactant be AT and the concentration of product is BT. This is something which I'm assuming. Concentration of reactant at time t is equal to AT. Concentration of product at time t is nothing but BT. Perfect. The first thing, if I would want to write the rate law, how do I write the rate law? Rate law is R is equal to K concentration of A raised power 1. This is how you are going to write the rate law for this first order reaction. Okay, this is how you are going to write the rate law for the first order reaction. Now, my dear students, the way I wrote integrated rate equation for the zero order reactions, similarly, I am going to write integrated rate equation for the first order reactions. And you are going to remember that equation basically. Okay, what is that equation? Let me write that directly because its derivation is of no use to us. The integrated rate equation in the first order reactions is written as ln of AT is equal to ln of A naught minus KT. This is the first form of the integrated rate equation. This is the first form of the integrated rate equation when it comes to the first order reaction. Number one. Number two, there is one more form of the integrated rate equation when it comes to the first order reactions. That is the log of AT is equal to log of A naught minus K divided by 2.303 multiplied by T. This is one more form of the integrated rate equation when it comes to the first order reaction. Similarly, are there some other forms too? Absolutely, there are some other forms too of the integrated rate equation. What is the next form of the integrated rate equation? I can write K is equal to 1 divided by T ln of A naught divided by AT. Similarly, one more form, K is equal to 2.303 divided by T. It is the log of A naught divided by AT. These are all different forms of the integrated rate equation of the first order reaction. In zero order reaction, there was only one form, AT is equal to A naught minus KT. Here we have got a lot of forms of the integrated rate equation. Again, there is one last form of the integrated rate equation here, that is AT is equal to A naught e raised power minus KT. This is one more form of the integrated rate equation when it comes to the first order reactions. 1, 2, this is the third form, this is the fourth form, and this is the fifth form. So all these are basically different forms of the integrated rate equation when it comes to the first order reactions. Totally 5 forms. Okay. Now, my dear students, since this was the first parameter, which was the integrated rate equation, let's talk about the second parameter. Second parameter in first order reactions is the half-life. If I again ask you, how do you define the half-life? T1 by 2, or which you call as T50%. You already know half-life or T50%. It is the time taken to complete 50% of the reaction. Time taken to complete 50% of the reaction. And my dear students, you know, in first order reactions, T half is equal to 0.693 divided by K. This is the expression with the help of which you can calculate half-life of a first order reaction. This is the expression with the help of which you can calculate half-life of the first order reaction. T half or T50% is equal to 0.693 divided by K. In zero order reactions, it was A naught by 2K. Here it is 0.693 divided by K. Okay. My dear students, the third point. The third point in first order reactions. What is that? The third point is what you call as the completion time. The third point is what you call as the completion time. Well, the completion time we represent with T100%. And let me tell you, in case of first order reactions, completion time is equal to infinite. Completion time is equal to infinite. What does that mean? Remember, a first order reaction never undergoes. A first order reaction never undergoes 100% completion. A first order reaction never undergoes 100% completion. A first order reaction takes infinite time to complete. Let me write it like this as well. A first order reaction takes infinite time to complete. Similarly, the next parameter, that's going to be the fourth one when it comes to the first order reactions. What is that? How do we calculate degree of dissociation? How do we calculate the degree of dissociation in case of first order reaction? That's alpha. That is alpha. My dear students, degree of dissociation alpha in case of first order reactions is nothing but it is equal to 1 minus e raised power minus kt. This is a direct result which I would want you guys to remember. the degree of dissociation. In case of zero order, it used to be Kt divided by A naught. In case of first order reactions, the degree of dissociation is nothing but 1 minus e raised power minus Kt. Again, the next parameter, that is the fifth one, that is the concentration of product. The concentration of product at time t, which I represent with Bt. How do we calculate it? Concentration of product. Let me tell you, concentration of product at time t is nothing but, it is A naught multiplied by 1 minus e raised power minus Kt. This is the expression by means of which you can calculate the concentration of product at time t when it comes to the first order reactions. Okay, I'm giving you the results directly. I'm not deriving any result. Just remember these results directly. Okay. Now similarly, next point. Time taken to complete a certain percentage of reaction. That means time taken to complete X% of the reaction. There are some questions wherein you'll be asked to calculate the time taken to complete 20% of the reaction, time taken to complete 30%, 40%, 50, 60, 70, right? So in short, time taken to complete X% of the first order reaction is equal to 2.303 divided by K. It is log of 100 divided by 100 minus X. So this is one more important parameter which will be frequently asked in the questions. Time taken to complete X% of the first order reaction. Similarly, my dear students, if I talk about few more parameters, let's say the seventh parameter. Seventh parameter is certain direct results. Remember, time taken to complete 75% of the first order reaction is equal to 2 times the half-life. Time taken to complete 87.5% of the reaction is equal to 3 times the half-life. Time taken to complete 99.9% of the reaction is equal to 10 times the half-life. Okay. Time taken to complete 90% of the reaction is equal to 10 divided by 3 times the half-life. And similarly, time taken to complete 99% of the reaction is equal to 2 times the time taken to complete 90% of the reaction. These are some direct results which I would want every one of you to remember from now onwards. Some direct results which I would want every one of you to remember from now onwards. Because from these direct results, direct questions will be asked. You will see in some time. Okay. Similarly, guys, there is one more parameter. And let me write that parameter over here about the first order reaction. What is that? That is concentration of reactant. Concentration of reactant left after n half-lives. Concentration of reactant left after n half-lives. Concentration of reactant left is represented by AT, and its formula is A naught divided by 2 raised power n. A naught divided by 2 raised power n. What is n? N represents the number of half-lives, which is basically total time divided by T half. Total time divided by T half. What does it mean? For example, you got a reaction like this. A gives B. Okay. For example, I'm saying its half-life is equal to 5 minutes. I'm saying its half-life is equal to how much? 5 minutes. Its half-life is 5 minutes. If its half-life is 5 minutes, can you tell me 10 minutes means how many half-lives? Half-life is 5 minutes. That means 10 minutes will be 2 half-lives. 15 minutes will be 3 half-lives. Right? 20 minutes will be 4 half-lives. Perfect. So how are we getting these number of half-lives? Number of half-lives is total time divided by T half. Total time divided by T half. That gives you the number of half-lives. Now there are some questions which are asked wherein you will be asked to calculate the concentration of reactant left after 5 half-lives. Calculate the concentration of reactant left after 20 half-lives. Calculate the concentration of reactant left after 30 half-lives. You just have to use the formula AT is equal to A naught divided by 2 raised power n. This is the concentration of reactant left. It's always equal to A naught divided by 2 raised power n, where n represents the number of half-lives. Right? These are few parameters, my dear students, which you have to remember when it comes to the first order reaction. And at the same time, there are some graphs as well. Perfect. I would want you guys to remember those graphs as well. Well, you should be able to make those graphs for sure. For example, the first graph I'm making between rate of reaction versus concentration of reactant. Since you know, rate of reaction is equal to K, concentration of A raised power 1, as per your rate law is concerned. Now, rate of reaction you are plotting along y-axis. Concentration of reactant along x-axis. This becomes m. Y is equal to mx means straight line passing through origin, and its slope is nothing but its slope is equal to k. This is the first graph about the first order reactions. Look at the second graph, guys. Second graph is between ln of AT versus T. Ln of AT versus T. You know your equation. Equation was ln AT is equal to ln of A naught minus KT. Now ln AT you are plotting along y-axis. T you are plotting along x-axis. This becomes your m. This becomes c. Sign is minus. Y is equal to minus mx plus c. So straight line with a negative slope. And if you look at its slope exactly, its slope is equal to minus k. And the distance from here to here is your intercept. Intercept is denoted by c, and c value is nothing but that is ln of A naught. Correct? Similarly, if you look at the third graph, in the first order, the third graph is between log of AT versus T. Log of AT versus T will be the similar graph, but the slope will now change. The slope will come as minus k divided by 2.303. Okay. Similarly, if I plot a graph between half-life T1 by 2 versus A naught, since you know the formula, T1 by 2 is equal to 0.693 divided by k. T1 by 2 is equal to 0.693 divided by k. That means T half is independent of A naught. T half is independent because in the expression of T half, there is no A naught. So on increasing or decreasing A naught, nothing happens to half-life. Okay. Similarly, if you look at more graphs like this, for example, I want to make a graph between AT versus T. What is AT and what is T? AT is the concentration of reactant left at time t, right? First of all, at time t is equal to 0, the concentration of reactant will be maximum. That is going to be A naught. With time, the concentration of reactant decreases. With time, the concentration of reactant decreases. Now, if I ask you a question, whether this graph is going to touch the time axis or not, what will be your answer? Quickly. Is this graph going to touch the time axis or not? I'm waiting for your answers. Think over it once. Think over it once, quickly. People are saying no. Why is that? What is the reason? What is the reason? Reason is pretty much simple. If this graph touches the time axis, at that point, AT value becomes 0. At that point, AT value becomes 0. What is AT? AT is concentration of reactant left. AT is concentration of reactant left. If the graph touches the time axis, at that point of time, concentration of reactant becomes 0. Concentration of reactant becoming 0 means 100% reaction getting completed. But we already know first order reaction never undergoes 100% completion. Right? Perfect. Understood. Good. Okay. For example, let's try to plot some more graphs. See, AT versus T we have plotted. All these graphs we have plotted. Now, for example, I'm plotting a graph between ln of A naught divided by AT versus T. You know your equation. Equation is K is equal to 1 divided by T ln of A naught divided by AT. So can I say ln of A naught divided by AT is equal to K into T? Absolutely. Ln of A naught by AT you are plotting along y-axis. T you are plotting along x-axis. This K becomes M. Y is equal to mx means straight line passing through origin. Its slope is equal to K. Its slope is equal to K. Slope means M value, which is equal to K. Right? Similarly, guys, for example, if I ask you to plot a graph between log of A naught by AT versus T, the graph is again going to be similar. The graph is again going to be similar. But right now, if you look at it, you know K is equal to 2.303 divided by T log of A naught divided by AT, right? So I can say log of A naught divided by AT is equal to K divided by 2.303 multiplied by T. Now this log of A naught by AT, you plot along y-axis, right? And this T you plot along x-axis. Perfect. And this K by 2.303 becomes your M. Y is equal to mx straight line. And if you talk about its slope means the value of M, and M value here is K divided by 2.303. So these are some of the important graphs which can be asked directly in case of what? In case of the first order reactions. I believe this is clear. I believe this is clear. Yeah. Perfect. Now guys, one more thing. There are some examples of the first order reactions which I would want every one of you to remember. So to remember these direct examples, these are the direct examples of what? First order reaction. So any reaction can be asked as the memory based. These are the memory based ones. You have to remember them, right? You have to remember them. Okay? You have to remember them. I believe this is clear to everyone. Now, if this is clear to everyone, let's try to solve a few questions so that it will be perfectly clear to you. See, a first order reaction is 75% completed in 100 minutes. That means time taken to complete 75% of the reaction is given to me as 100 minutes. All right. Calculate the time taken to complete 87.5% reaction. You know, time taken to complete 87.5% of the reaction is equal to 3 times the half-life. We know that. So that means if I know the half-life of the reaction, I can calculate it easily. Now, how do I calculate the half-life? It's pretty much simple. You know, T 75% is equal to 2 times the half-life. Few minutes back I told you. So it's equal to 100. So T half will come out to be how much? T half will come out to be 50 minutes. If T half is equal to 50 minutes, put it here. So it's 3 multiplied by 50. The value comes out to be 150 minutes. Correct? So time taken to complete 87.5% of this reaction is how much? It is equal to 150 minutes. Similarly, if they ask you to calculate time taken to complete 99.9% of the reaction, that's equal to 10 times half-life. So 10 times 50, that comes out to be 500 minutes. Right? Time taken to complete 90% of the reaction, already I've told you, that's 10 by 3 times the half-life. 10 by 3 times the half-life. So 10 by 3 into 50. So 10 divided by 3 into 50. The value comes out to be 500 divided by 3 minutes. So anything can be asked out of all this. Right? It is just you have to calculate half-life from this particular expression. Once you get the half-life, you can easily solve any of these questions. Okay? If you look at the next question, guys, look at the next question. For an elementary reaction, reaction is X gives Y plus Z. As per the question, reaction is elementary. And already we know, for elementary reactions, order is equal to molecularity. For elementary reactions, order is equal to molecularity. What is the molecularity of the reaction? 1. So what would be the order of the reaction? Order of the reaction is also 1. So it's a first order reaction. It is basically a first order reaction, right? Now, as per the question, half-life is given. How much is half-life given? Half-life is given as 10 minutes. Half-life given as 10 minutes means 0.693 divided by K is equal to 10 minutes. So you can calculate K also from here. K would be 0.0693 and it's going to be minute inverse. What do we have to calculate? In what period of time would the concentration of X be reduced to 10% of the original value? Do you understand? In the question, they are asking you to calculate the time taken. In what period of time would the concentration of X be left to 10% of its initial value? What does that mean? That means 90% reaction has been completed. Because when 90% reaction gets completed, at that point of time, 90% of reactant would have got converted into product. So 10% reactant would be left. So technically, they are asking you to calculate time taken to complete 90% of the reaction. And you already know that's 10 by 3 times the half-life. So it's 10 by 3. Half-life is how much? Half-life is 10 minutes. So the answer is going to be 100 divided by 3 minutes. This is the time taken to complete 90% of the reaction. Right? Guys, I forgot to give you one parameter here. Just a second, sorry. I forgot to give you one parameter here. One more parameter here is, that is the trick. In first order reactions, there is one more parameter which I would want you to take down on your notes. For example, you have got the reaction A gives B. Its rate constant is K. Okay. Let's say I'm making a table here. Like I made one table in zero order reactions. Let's say I'm making one table here. And here I'm writing concentration of reactant versus time. Concentration of reactant versus time. Let's say at time T1, the concentration of reactant is A1. Let's say at time T2, concentration of reactant is A2. At time T3, concentration of reactant is A3. At time T4, concentration of the reactant is A4. Yeah, let's assume that at time T1, I'm selecting sometimes time T1, which can be 5 seconds, 10 seconds, 30 seconds, whatever seconds. So at time T1, the concentration of reactant is A1. At time T2, the concentration of reactant is A2, right? Similarly, at time T3, concentration of reactant is A3. Now, my dear students, remember, if the time interval is same, if the time interval is same, what does that mean? That means if T2 minus T1 is equal to T3 minus T2 is equal to T4 minus T3. This is what you call a same time interval. If in the same time interval, A2 divided by A1 comes out to be same as that of A3 divided by A2, comes out to be same as that of A4 divided by A3, then remember, at that point of time, the reaction follows the first order kinetics. That means the order of the reaction at that point of time is equal to 1. So sometimes a table like this will be given. From the table, you have to check what is the order of the reaction. So what do? We check first of all if the time intervals are same. If the time intervals are same, in the same time intervals, if A2 by A1 will be same as that of A3 by A2, will be same as that of A4 by A3, then directly remember the reaction is going to follow the first order kinetics. Okay? This was one more point which I had forgotten to tell you. I hope this is clear now. I hope this is clear now. For example, this is the question. In this question, guys, for a first order reaction, choose the value of half-life. We have to calculate half-life. The reaction is first order. And you know half-life is equal, for the first order reaction is equal to 0.693 divided by K. So to calculate the half-life, what do I need? To calculate the half-life, I need K. How do I calculate the K? The graph is given between log AT versus T. And few minutes back only I told you, slope of this particular graph is equal to minus K divided by 2.303. And you know, slope is what? Slope is tan of theta. So it is tan of 135. Slope is tan of 135. Tan 135 is minus 1. So K value will be equal. This minus gets cancelled. K comes out to be 2.303. And if the time is in minutes, then it's going to be minute inverse. So K is equal to this much. You got the value of K. If you got the value of K, you can easily calculate half-life, which will be 0.693 divided by 2.303. The answer is going to be 0.3 minutes. So this is the half-life of the reaction, which I was supposed to calculate. I believe this is also clear to everyone. If yes, let me know once in the chats quick. So see, these sort of questions are basically asked when it comes to your first order reactions. I hope all this is clear. I hope all this is clear. One more question, look at it. One more question, look at it, people. Rate constant for the first order reaction is given, okay? Rate constant is given as 1.386 minute inverse. Calculate the concentration of reactant left after 8 minutes. Calculate the concentration of reactant left after 8 minutes. Okay, calculate the concentration of reactant left after 8 minutes. Since K is given, if K is given, can we calculate half-life? Tell me. If K is given, can we calculate half-life? If K is given, we can calculate half-life easily. It's going to be 0.693 divided by T half, which is 1.386. The value is 1 by 2. 1 by 2 is 0.5. So this is the half-life. What are we supposed to calculate? Look at the question carefully, guys. In the question, they're asking us to calculate the concentration of reactant left after 8 minutes. The concentration of reactant left after 8 minutes. So first of all, 8 minutes means how many half-lives? 8 minutes means how many half-lives? Total time divided by T half. So technically, we are supposed to calculate the concentration of reactant left after 16 half-lives. And remember, concentration of reactant left after n half-lives is equal to A naught divided by 2 raised power n. So this is going to be A naught divided by 2 raised power. What is the value of n? N value is 16. So this is the concentration of reactant left after 16 half-lives, which I was supposed to calculate. So basically in this question, this T is equal to 8 minutes means actually 16 half-lives. So you're supposed to calculate the concentration of reactant left after 16 half-lives. And concentration of reactant left after 16 half-lives came out to be A naught divided by 2 raised power 16 molar. Okay. This sort of a question is also asked when it comes to your examination. Okay, look at this one, guys. Look at this one. Reaction is given. A gives B. Rate constant is also given. Time required for 40 grams of reactant to reduce to 10 grams will be. This sort of a question can also be asked. And how do we deal such kind of a question? Have a look. You know, at time t is equal to 0, the initial amount of reactant is represented by A naught, which is given to me in the question as 40 grams. It is given to me as 40 grams. Now the question is, how much time will take for the amount of reactant to reduce from 40 grams to 10 grams? How much time will it take for the amount of reactant to reduce from 40 grams to 10 grams? Okay. Since this is the concentration of, this is the amount of reactant left. This is the amount of reactant left. And you know, amount of reactant left is represented by AT. K is already given. If I use the integrate rate equation, one of its forms is 2.303 divided by K. It's a log of A naught divided by AT. Right? Let's put the values in this particular expression. P will be equal to 2.303 divided by, what is the value of K? K is 2.303 into 10 raised power minus 3. Log of A naught is 40, AT is 10. So this got cancelled. This also got cancelled. 10 raised power minus 3 comes up as 10 raised power 3. Log of 4 is 0.6. The answer will come out to be 600 seconds. So this is the time. This is the time taken for the amount of reactant to reduce from 40 grams to 10 grams. I believe all of this is clear to everyone. Okay. Perfect, guys. Now, let's move on to one more important topic. What is that? That is the kinetics of gaseous first order reactions. Kinetics of gaseous first order reactions. One more important topic that can be asked too. Kinetics of the gaseous first order reaction. Kinetics of the gaseous first order reaction. Try to understand very carefully what I'll be doing. For example, I'm taking a reaction. A gas, it gives B gas plus C gas. This is the reaction. Tell me one thing, at time t is equal to 0, how many gases will be there in the container? At time t is equal to 0, there will be only one gas in the container, and that's going to be gas A. So at time t is equal to 0, whatever is the pressure of the, that is entirely due to what? That's entirely due to A. Since I can say at time t is equal to 0, there is only one gas present in the container, that is gas A. Because time t is equal to 0 means the reaction has not started. B has not got formed, C has not got formed. So that means in the container there is only A present. So whatever is the pressure, that's entirely due to A. And pressure due to reactant initially, I'm going to take as P naught. This is the pressure due to A. And right now pressure due to B will be 0. Pressure due to C will be also 0. Now with the time, what's going to happen? When the reaction starts, moles of A are going to decrease in the container. Moles of B and C are going to increase in the container. So can I say pressure due to A will also decrease? Pressure due to B and pressure due to C, it will increase. Now you tell me, for example, at time t, which can be 10 minutes, 20 minutes, 30 minutes, whatever time. At time t, what will be pressure due to A? Is it going to be P naught plus something or P naught minus something? It is going to be P naught minus something, and let that something be X. Okay. Now we use the stoichiometry. 1 mole gives 1, so X is going to give us X. 1 gives 1, X gives X. So now if I ask you, at time t, how many gases are there in the container? At time t, how many gases are there in the container? I would say at time t, there are 3 gases in the container. At time t, there are 3 gases in the container. Gas A, gas B, and gas C. If I ask you what is the total pressure of the mixture at time t, which I am representing with PT. PT represents, since at time t, there are 3 gases in the container. So at time t, there is a mixture basically in the container. Total pressure of the mixture at time t, I am representing with PT. And I can say total pressure of the mixture at time t will be equal to pressure due to A, which is P naught minus X, plus pressure due to B, which is X, plus pressure due to C, which is again X. X got cancelled out. So I can say X is equal to PT, or let me write it completely for you so that it would be a problem. PT is equal to P naught plus X, or X would be equal to PT minus P naught. X would be equal to PT minus P naught. Okay? X would be equal to PT minus P naught. Now, my dear students, as the reaction keeps on going continuously, if I write at time t is equal to infinity, at time t is equal to infinity, since the reaction is first order, right? I wrote time t is equal to infinite. At t is equal to infinity, I would say 100% reaction would have got completed. And my dear students, if 100% reaction would have got completed, that means 100% reactant would have got converted into product. If 100% reactant would have got converted into product, what would be the pressure due to A at that time? 0. Right? Now, 1 gives 1. From P naught, you will get P naught. 1 gives 1. P naught gives P naught. So basically, at T is equal to infinity, how many gases will be there in the container? There'll be no gas A in the container, but there'll be gas B, there'll be gas C. So at infinity, there'll be 2 gases in the container. I can say total pressure of the mixture at infinity. Total pressure of the mixture at T is equal to infinity would be equal to P naught plus 0, which makes it 2 times P naught. So from here, I can calculate P naught. P naught is equal to P infinite divided by 2. P naught is equal to P infinite divided by 2. Okay. Now, what is asked in these questions? The first question that will be asked, that will be calculate the rate constant of the reaction in terms of rate constant of the reaction in terms of P naught and PT. This is the first question which will be asked. Rate constant of the reaction in terms of P naught and PT. Now, my dear students, if you remember the integrate rate equation, K is equal to 2.303 divided by T log of, it is going to be A naught by AT. What used to be A naught? A naught used to be the initial concentration of reactant. A naught used to be initial concentration of reactant. But instead of initial concentration of reactant, I'll write initial pressure of reactant. And how much is initial pressure of reactant? That is P naught divided by AT used to be the concentration of reactant left at time t. AT used to be the concentration of reactant left at time t. So here I'm going to write the pressure of reactant left at time t. And what is the pressure of reactant left at time t? That is simply P naught minus 6. Okay. So I can write K is equal to 2.303 divided by T log of P naught divided by P naught minus, what is the value of X? X value we have already calculated, that is PT minus P naught. Okay. If I make the final expression, so finally it's going to be K is equal to 2.303 divided by T. It's going to be log of P naught divided by. This becomes twice P naught minus PT. This is the direct expression which is asked in the question. Calculate the value of rate constant for the reaction A gives B plus C in terms of P naught and PT. So this is one expression. Well, you don't have to remember this expression. You should be in a position to make this expression, because if they change the stoichiometry, the entire expression is going to change. Okay, this is the first thing which they'll ask. The second thing they can ask in the question, calculate the rate constant expression in terms of PT and P infinite. They'll ask you to calculate rate constant in terms of PT and P infinite. So what do? This is the expression which we already made, and this expression is in terms of P naught and PT. What do I need now? I need the expression of K in terms of PT and P infinite. In terms of PT and P infinite. So PT I'll keep as such. So P naught I have to replace. P naught I have to replace with what? P infinite by 2, and we'll be done. So K is equal to 2.303 divided by T. It is a log of, instead of P naught, what can I write? I can write P infinite by 2 whole divided by 2 times. Instead of P naught, it's going to be P infinite by 2 minus PT. So 2 gets cancelled. So I would say K is equal to 2.303 divided by T. It is a log of P infinite divided by 2 times P infinite minus PT. This is the expression of K in terms of PT and P infinite for this particular reaction. I believe this is clear to everyone. Sir, why reactant at infinity is put as 0? Because at T is equal to infinity, a first order reaction gets 100% completed. It takes infinite time for the reaction to get 100% completed. So at T is equal to infinity, it would have got 100% completed. 100% completed means 100% reactant would have got converted into product. If 100% reactant would have got converted into product, that means there'll be no reactant. If there is no reactant, that means pressure due to reactant at infinity will be 0. Is it clear? I believe these sort of questions, again, you will be able to solve from now onwards if they come in your exam. Expression of rate constant in terms of P naught and PT. Okay, let me take one more example. If I change the stoichiometry, let's see what happens. If I change the stoichiometry, let's see what happens. See guys, for example, the reaction is A gas. It gives 2 times B gas plus 3 times C gas. Let's say this is the reaction. Now I'm going to change the stoichiometry. I'll see how the expression is going to change. Okay. See guys. First of all, at time t is equal to 0, pressure due to A will be P naught. This will be 0. This will be 0. Now at time t, this is going to be P naught minus X. Now 1 mole gives 2 moles, X gives 2X. 1 gives 3, X gives 3X. Okay. Now at time t, there are 3 gases in the container. That means at time t, there is a mixture containing 3 gases. At time t, total pressure of the mixture at time t will be equal to P naught minus X plus 2X plus 3X. So I would say PT is equal to P naught plus 4X. Or I would say X is equal to 1 by 4 PT minus P naught. I got the value of X. I got the value of X, right? Now, my dear students, at infinity, at t is equal to infinity, 100% reaction would have got complete, right? So there will be no reactant left at t is equal to infinity. So pressure due to reactant would be 0. Now 1 gives 2. So from P naught, you get 2 P naught. 1 gives 3. From P naught, you get 3 P naught. So what is the total pressure of the mixture at infinite? At t infinity? First of all, at this particular point of time, there will be only 2 gases in the container. So total pressure of the mixture at t infinity will be 3 P naught plus 2 P naught plus 0, which comes out to be 5 P naught. So I can say P naught is nothing but it is P infinite divided by 5. So I got these two things. One is X, one is P naught in terms of P infinite. Now people, understand. The first question, rate constant expression in terms of what? Rate constant expression in terms of P naught and PT. This is the first question that's asked. You know it already. Now you know your K is equal to 2.303 divided by T log of A naught by AT. Instead of A naught, I'll write P naught. Instead of AT, what is AT? AT is the concentration of reactant left at time T. So I'll write pressure of reactant left at time T, which is P naught minus X, right? Now X value already we have calculated. So it's 2.303 divided by T log of P naught divided by P naught minus X. X is already 1 by 4 into PT minus P naught. Now, if you make the final expression here, final expression is going to be 2.303 divided by T log of. This will be 4 P naught minus PT plus P naught divided by 4. So that 4 comes up. This becomes 4 P naught at the end. And this will be 5 times P naught minus PT. This is the expression of rate constant in terms of P naught and PT. Yeah. This is the expression of rate constant in terms of P naught and PT. Now, second thing which can be asked, write the rate constant expression in terms of PT and P infinite. So PT you are going to keep as such. Instead of P naught, you are just going to replace P naught with P infinite by 5. Here you are going to replace P naught with P infinite by 5. Here also you are going to replace P naught with P infinite by 5. So you will get one more expression of K that will be in terms of PT and P infinite. I believe I'm clear with all of this. Now, my dear students, if this particular stuff is clear, then comes one more thing. Then comes one more thing from which questions are frequently asked nowadays. What is that? It's calculation of order from half-life. Calculation of order from half-life. This is one more question which is frequently asked. Calculation of order from half-life. Priyanka, it's calculation. You check it. It will be 5 P naught. Don't worry. Look here now. My dear students, first of all, remember one thing. If you have got the reaction A gives B, if you have got the reaction A gives B, let the order of this particular reaction is equal to N. Let the order of this particular reaction is equal to N. Remember, T half is directly proportional to the initial concentration of reactant raised power 1 minus N. This is one important result. You can check it out too. For example, let's say you have got zero order reaction. In zero order reaction, N is 0. If N is 0, 1 minus 0 is 1. Your T half is directly proportional to A naught. You know that already. In zero order reaction, T half is equal to A naught by 2K. T half is equal to A naught by 2K. So T half is directly proportional to A naught in zero order reaction. Talk about if you put the value of N as 1. If you put the value of N as 1, 1 minus 1, 0. Anything raised power is 1. So T half is independent of A naught. And in first order, we already know T half is equal to 0.693 divided by K. So T half is independent of A naught. So this particular result is valid basically. So remember it directly. Or let's make it little easy. A naught is initial concentration of reactant. So let me represent initial concentration of reactant with small a. Let me represent initial concentration of reactant with small a. So small a is basically A naught. I'm replacing it. Okay, small a is A naught. Now the first thing, this small a can be the initial concentration of reactant, number one. Or the small a can be the initial pressure of reactant. The small a can be initial concentration of reactant or initial pressure of reactant. Okay. Now people, try to understand very carefully what I do. If I remove this proportionality sign, I'll get T half is equal to K A raised power 1 minus N. Correct? So from this particular result, I am going to generate a result which I'll be using in the questions. I'll write for example like this. I'll write T half 1 divided by T half 2. From this particular equation, I can write T half 1 divided by T half 2 is equal to A1 divided by A2 whole raised power 1 minus N. This is the expression from which questions are frequently asked, right? Related to order. This is the expression from which questions are frequently asked, related to order. Okay? T half 1 divided by T half 2 is equal to A1 by A2 whole raised power 1 minus N. Correct? Now guys, if you look at this particular equation, if I multiply this equation with log, it becomes log of T half is equal to log of M into N is basically log of M plus log of N. Okay? Or I can write it like this. Log of T half is equal to, this is log of K plus log of M raised power N. It is N log M. 1 minus N comes to the front, then it's log A. This is the logarithmic form of the same equation. Now, if you want to plot log T half along y-axis, you plot this along x-axis. This becomes my M, this becomes my C. In the sign, in the middle, the sign is plus, so it becomes y is equal to mx plus c. So now, for example, plot a graph. Plot a graph between what? Log of T half versus log of initial concentration of reactant. Y is equal to mx plus c, straight line. Slope is m. M value is nothing but 1 minus n. And the intercept from here to here is nothing but log of k. Done? Done, people? This can be asked too. Remember, its slope is what? Its slope is equal to 1 minus n. Now, what kind of question can be framed from this particular expression? Remember the expression, T half 1 divided by T half 2 is equal to A1 by A2 whole raised power what? Whole raised power 1 minus n. For example, this is the question. This is the question. You are given the reaction A gives B, and the table like this is given. T half, when the T half of the reaction is 4 seconds, concentration of reactant is 50 molar. When T half is equal to 2 seconds, concentration of reactant is 100 molar. See, I can say it like this. When the initial concentration of reactant is 50 molar, at that time T half of the reaction is 4 seconds. And when the initial concentration of reactant is 100 molar, at that point of time, half-life of the reaction is 2 seconds. So this is technically T half 1. This is your T half 2. Right? This is your A1 and this is your A2. When the initial concentration of reactant is 50 molar, half-life is this. When the initial concentration is 100 molar, half-life is this. So again, if I use the expression that I gave you right now, what was the expression? Expression was T half 1 divided by T half 2 is equal to A1 divided by A2 whole raised power 1 minus n. Now T half 1 is how much? 50. T half 2 is how much? Sorry, T half 1 is not 50. My bad. What just happened? T half 1 divided by T half 2 is equal to A1 divided by A2 whole raised power 1 minus n. Now T half 1 is how much? This was your T half 1. This was your T half 2. Now T half 1 is 4. T half 2 is 2 is equal to A1 is 50. A2 is 100. Whole raised power 1 minus n. So this value comes out to be 2. This will be 1 by 2 raised power 1 minus n. Correct? Now just a matter of calculation. Just a matter of calculation, right? So I'll be writing it like this. 2 is equal to 1 by 2 means 2 raised power minus 1. Whole raised power 1 minus n. So 2 is equal to 2 raised power n minus 1. That means n minus 1 value is equal to 1. N value is equal to 2. N is equal to 2. That means order of the reaction is equal to 2. Okay? Sir, can you increase your speed? I'm already moving at very high speed. But I'm just teaching everything in detailed manner. That's why it's taking time. So let it take time. We have nowhere to go, right? We are here till 11 p.m. What's the problem? And I don't want to skip anything. I do not want to skip anything. This is the maximum speed which I can keep. Is everything clear till here? Is everything clear, guys? Now there are two topics left in this chapter. One is your collision theory and one is Arrhenius equation. So let's get done with those two concepts as well. All clear? Say it once in the chats. All right, people. So let's move on to, okay, let's do one question first. Look at this question. Log of T half versus log of A. Graph is given. Log of T half versus log A graph is given. What do we need to calculate? Order. Right now, few minutes back, I told you slope of this graph. Slope of this graph is equal to 1 minus n. Slope is what? Tan of theta. What is theta? Theta is the angle which this graph makes with the positive x-axis in the anti-clockwise direction. This is theta. This is called as theta basically. So if this is 45, this is 90, this will be 45, this will be 135, right? So slope means tan of theta, tan of 135 is equal to 1 minus n. Tan 135 is already minus 1, so 1 minus n. So n value is equal to 2. What is n? N represents order of the reaction. Order of the reaction is 2. Okay? Order of the reaction is equal to 2. I believe this sort of a question you can easily do from now onwards. Now, people, let's talk about the collision theory. See, it's a complete theoretical question, okay? It's a complete theoretical concept. Collision theory. First of all, the collision theory which we are going to discuss now, it is completely based on your kinetic theory of gases. Completely based on kinetic theory of gases. And your kinetic theory of gases says that the molecules are assumed to be hard and rigid spheres. Same as this. The molecules are assumed to be hard and rigid spheres, right? And one more thing, in this collision theory, we are going to consider collision between two molecules. We are going to consider the bimolecular collisions. Now, what this collision theory exactly says? See, I have the slide ready. I just have to read it out loud so that you can understand it. My dear students, as per collision theory is concerned, for any reaction to happen, reacting species must collide first. For any reaction to happen, reacting species must collide first. Point number one. Point number two. All the collisions between the reactants, they are not going to lead to the formation of products. All the collisions between the reactants, they are not going to lead to the formation of products. There are only some collisions between the reactants. Which leads to the product formation. And those collisions between the reactants, which leads to the formation of product, those collisions are what you call as effective collisions. Those collisions are what you call as effective collisions. Do you understand? Again, I'm telling you one thing. For any reaction to happen, reacting species must collide first. Not all the collisions will lead to the formation of products. Not all the collisions will lead to the formation of products. Only some collisions will lead to the formation of products. Only some collisions between the reactants will lead to the formation of products. And those collisions, due to which product formation takes place, you call those collisions as the effective collision. And my dear students, for a collision to be effective, first of all, effective collisions are the ones due to which products are formed. Now, for the collision to be effective, two factors are going to decide. Two factors decide whether the collision between the reactants is effective or not. Two factors are going to decide whether the collision between the reactants is effective or not. One is called as energy factor, one is called as orientation factor. Now, what is this energy factor and what is this orientation factor? Let's talk about energy factor first. I think I would need a separate slide because here everything is already mentioned, so it won't be possible to make you understand through this ready-made slide. Okay, let me take one more slide here. See guys, as I told you, for the collision to be effective, how many factors are deciding? Two factors are deciding. One is called as energy factor, one is called as orientation factor. Now let's talk about this energy factor first. If you talk about your energy factor, my dear student, as per your energy factor is concerned, what happens exactly? When reactants are supposed to form the products, first of all, reacting species, they collide and they form a complex called as activated complex. First of all, reacting species, they collide and form the activated complex. The energy of activated complex is high, therefore its stability is low. And this activated complex finally breaks down into what? It finally breaks down into product. Energy possessed by reactant, I'm representing with ER. Energy possessed by the product, I'm representing with EP. So first of all, as per your, I'm going to discuss energy factor. So first of all, reacting species, they must collide and form the activated complex, which breaks down further into the products. My dear students, you have got two types of reactions. You know, one is your endothermic, one is exothermic. If I talk about endothermic reactions, in case of endothermic reactions, what is the value of delta H? Delta H value is positive for endothermic. Delta H simply means EP minus ER. So EP minus ER will be positive, which means that simply EP is greater than ER. Okay. If I show it graphically so that you can understand it in a better way. For example, here I'm plotting potential energy and here I'm plotting progress of reaction. Potential energy versus progress of reaction. Okay. Potential energy versus progress of reaction. My dear students, at this point of time, progress of reaction is 0. Progress of reaction is 0. That means reaction has not started. If the reaction has not started, that means we'll be only having reactant with us. And energy carried by the reactant is represented by ER. Energy carried by the reactant is equal to ER. Now these reacting species, they collide and form what? Activated complex, whose energy is high. So reacting species are going to collide and will form the activated complex. This is the activated complex whose energy is high, right? And this activated complex further breaks down into what? Into products. Now, you know, energy of product should be greater than energy of reactant. So the graph should be somewhere here. So this point represents, for example, product. And this particular point represents energy of product. This particular line over here represents energy of reactant. Right? And remember, energy carried by activated complex is called as threshold energy. Energy carried by activated complex is called as threshold energy. Now, people, comes a point. What is the point? Delta H is equal to EP minus ER. So first of all, this energy gap is EP. This energy gap is EP. This energy gap is ER. EP minus ER. That means I'm talking about this particular energy gap. This energy gap I'll be representing with delta H. This energy gap I'll be representing with delta H. Now, my dear students, as per energy factor is concerned, can I say reacting species must collide and cross this energy barrier to form the products? So for the reaction to happen, for reactants to form products, I would say reacting species must cross this barrier and form the products. Now people, understand one thing which I'm going to tell you. This is progress of reaction. Let me tell you, not all the reactants will have sufficient energy. Not all the reactants will have sufficient energy to cross this activation energy barrier, to cross this barrier basically. Not all the reactants have got sufficient energy to cross this barrier. The minimum extra amount of energy which is required by the reactants to cross the energy barrier. The minimum extra amount of energy which is required by the reactants. The minimum extra amount of energy which is required by the reactants to cross this barrier, to cross this energy barrier, to form the products, right? That minimum extra energy required is called as the activation energy. That's called as the activation energy. Okay? That's called as the activation energy. Okay? That's called as activation energy. Perfect? So basically, this particular energy gap, I'm calling as activation energy. Since I'm right now talking about the forward reaction, a reactant going to the products, so this is your activation energy of forward reaction. Similarly, my dear students, if I talk about the backward reaction, products into reactants. If products have to get converted into reactants, I would say products have to cross this barrier. What barrier products have to cross? Products have to cross this energy barrier, right? This is what I'll be calling as activation energy of backward reaction. Okay? Do you see this particular energy gap which was delta H? Can I say delta H will be also equal to EAF minus EAB? Delta H will be also equal to EAF minus EAB. Right? I believe this is clear. Now guys, similar stuff happens to the exothermic reactions as well. Look at this particular graph. It is just in exothermic reactions, the graph comes slightly down because energy of products will be less than that of energy of reactants. Rest everything is same. This is your activation energy of forward reaction. This is called as activation energy of backward reaction. Perfect. Oh, and in exothermic reactions, EAF will be less than that of EAB. Right? In your endothermic reactions, what was there? If you look at your endothermic reactions again, in your endothermic reactions, your EAF is greater than that of EAB. Perfect? In your endothermic reactions, EAF is greater than EAB. Now, if I plot a graph for exothermic reactions, let me plot a graph for exothermic as well. For example, I'm talking about the exothermic reaction now. In case of exothermic reaction, delta H value, positive or negative? Negative. That means EP minus ER is negative, which means that EP is less than ER. Okay. What happens? Reactants should collide and form the activated complex. which further should break into the products. So let's get to see what this graph would be. For example, I'm plotting potential energy along this axis. I'm plotting progress of reaction along this axis, right? At this point, progress of reaction is 0. That means reaction has not started. If the reaction has not started, we'll be only having reactants with us, and energy of reactants we represent with ER. Now these reacting species, they should collide and form activated complex. This is your activated complex, which further breaks down into products. Let's say this point represents the products, and this line over here, it represents energy of products. This particular line over here, it represents energy of reactants. Correct? This particular line over here, it represents energy of reactants. This particular line, energy of reactants. Now, not all the reacting species can cross this barrier on their own, right? The minimum extra energy which is required by the reactants to cross this energy barrier, right? To form the products. That's what I call as activation energy. Since I'm talking about the forward reaction, so this is EAF. If I talk about the backward reaction, now if products have to form the reactants, right? So I would say if products have to get converted into reactants, products should also cross this barrier, right? Now all the products won't be having the sufficient amount of energy so that they can cross the barrier. The minimum extra amount of energy which is required by the products to cross this barrier is what you call as activation energy of backward reaction. As you can say, in exothermic reactions, EAB will be greater than that of EAF, right? And this particular energy gap, which we already know, that's delta H. Delta H is already equal to EAF minus EAB. Now here in this particular case, EAF is less, EAB is more. EAF is less, EAB is more. So the difference between these two will come out to be negative, which is understood already because for exothermic reactions, delta H is negative. Am I clear? Am I clear, people? Is it clear? Everyone in the chats once? Now the point is, as per energy factor is concerned, what is the criteria? What is the criteria for the collision to be effective as per energy factor? What is the criteria? What is the criteria for the reaction? Sorry, what is the criteria for the collision to be effective? As per which factor? As per energy factor. My dear students, as per energy factor is concerned, reacting species must collide and should cross the barrier. Simple. This is the criteria. Or in other words, I can say, for the collision to be effective, as per energy factor, energy of reactant should be greater or equal to the activation energy barrier. Energy of reactants should be greater or equal to the activation energy barrier so that they can cross the barrier. Now, how many fraction of molecules are there? Which have got energy greater or equal to activation energy? That means how many fraction of molecules are there which can cross the barrier as per energy factor? That's given by this parameter, e raised power minus Ca by RT. E raised power minus Ca by RT. This factor is called as Boltzmann's factor. My dear students, if the value of this particular factor, e raised power minus Ca by RT, if the value of this factor is more, that means there will be more fraction of molecules which have got energy greater or equal to activation energy. That means more fraction of molecules can cross the barrier. If more fraction of molecules cross the barrier, that means more product formation will be there. If more product formation is there, that means more is the rate of the reaction, in short. So rate of reaction is directly proportional to this Boltzmann's factor. You understand? It is directly proportional to the Boltzmann's factor. Perfect. So remember, for the collision to be effective, reacting species should collide and cross the barrier. Or in other words, I can say, the energy of reactant should be greater or equal to activation energy, then only they are going to cross the barrier. Right? Those fraction of molecules which have got energy greater or equal to activation energy, that's equal to e raised power minus Ca by RT. Okay? E raised power minus Ca by RT. If the value of this particular term is more, that means we have got more fraction of molecules which can cross the barrier, more product formation, more rate of the reaction. So rate of the reaction is directly proportional to this particular term, this Boltzmann's factor. Okay? Now there is one more term called as collision frequency. Collision frequency, which we represent with ZAB. Collision frequency. Let's tell me just one thing. Collision frequency is nothing but number of collisions per unit volume per unit time. Number of collisions between the reactants per unit volume per unit time. Think over it. If the collision frequency is more, that means more collisions are happening between the reactants. If more collisions are happening between the reactants, that means more are the chances of effective collisions. If more are the chances of effective collisions, that means more product formation. More product formation means more rate of the reaction. So rate of reaction should be directly proportional to collision frequency as well. Did you understand this particular point? Rate of reaction should be directly proportional to the collision frequency as well. I believe this point is clear. Yeah? I believe this particular point is clear. Right, people? Now. There is one more parameter called as orientation factor. See, not only energy factor is going to decide. Not only energy factor is going to decide whether the collision is effective or not. There is one more factor that decides whether the collision is effective or not. That's called as orientation factor. And how this orientation factor decides? I'll give you a simple example. For example, this is your CH3I. This is your CH3I, okay? And this, for example, your OH negative. Nucleophile, okay? This bond is polar. The bond pair is towards iodine, so delta negative. This is delta positive. Now, this can either attack from front side or back side. When it attacks from front side, negative, there will be repulsions. So this is collision with improper orientation. If it comes from the back side, since hydrogens are attached, so less steric repulsions, right? So it can attack from back side. Less repulsions means proper orientation. So as per orientation factor is simply concerned, reactants should collide with which orientation? Proper orientation or improper orientation? Reactants should collide with proper orientation, wherein that particular orientation wherein steric hindrance is less. You can remember it like this. Okay. Now, guys, there's the point. What is the point? See, I told you rate of reaction is directly proportional to e raised power minus EA by RT. Rate of reaction is directly proportional to ZAB, right? This particular term gives us the information about which factor? Energy factor. This particular term gives us the information about the energy factor. This particular term gives the information about collision frequency. Okay. Is there anything missing here? What do you think? Is there anything missing here? This is energy factor. This is collision frequency. One factor is missing, that is orientation factor, which I represent with P, right? So this is my one more equation with the help of which we can calculate rate of the reaction. And this particular term here is called as the orientation factor. Okay? I believe this is clear to everyone. And if this is clear to everyone, this was once the question. Just a second. These are two questions basically. See, ignore this one. Just a second. Leave this particular graph aside. Okay, this is a separate question. Leave this graph aside. Look at the above question. In the above question, X gives Y is an exothermic reaction. Okay, EAF is given, delta H is given. We are supposed to calculate EAB. So first of all, the reaction is exothermic. If the reaction is exothermic, since you know delta H is equal to EAF minus EAB, and in exothermic reactions, delta H has to be negative. It's already given to me as minus 20 kilojoules. EAF, activation energy of forward reaction, is simply given to me as 30 kilojoules minus EAB. So from this particular equation, can't we calculate EAB? EAB will be equal to 50 kilojoules. Simple. EAB is equal to 50 kilojoules. Right? Do you understand? Simple. Delta H is equal to EF minus EAB. Since reaction is exothermic, so delta H has to be negative. So I took minus 20 here is equal to EF is given, EAB is to calculate it. So EAB we got. Now, if you look at this particular reaction, if you look at this particular graph, say, how many peaks do you see here? First peak, second peak. Every peak represents activated complex. Every peak represents activated complex. So this is your activated complex 1, this is your activated complex 2, right? Activated complex 1, activated complex 2. Remember, the number of peaks is equal to the number of steps. So it is basically like this. A colliding and forming the activated complex. It's called as activated complex 1. This breaks down into B, for example. Now these B molecules, again they collide. What do they form? Activated complex 2. And this activated complex 2 further breaks down into what? It further breaks down into C. So how many steps do you see? 2 steps, right? So if I ask you among these two steps, which one should be the slowest step? I would say first one would be the slowest step, because in the first one, the barrier is more. Lesser molecules can cross it. So first step is the slow step here. And slow step here is called as a rate determining step. So that particular step wherein the barrier is more, it is going to be the rate determining step, right? And remember, number of peaks is equal to the number of steps. Number of peaks is equal to number of steps. So if they ask you a question like this, if they give a graph like this, if they give a reaction profile like this, you have to count the peaks. That will give you number of steps in the reaction. Once you get the number of steps in the reaction, after that you can check which one is the rate determining step. That particular step whose barrier is more, whose activation energy barrier is more, remember, that's going to be your rate determining step. I believe I'm clear with all of this. Now guys, if you ask me what does a catalyst do? Effect of catalyst. Effect of catalyst on rate. Effect of catalyst on rate. See, catalysts are first of all of two types. One is positive catalyst, one is negative catalyst. One is positive catalyst, one is negative catalyst. What does a positive catalyst do? A positive catalyst increases the rate of the reaction. How it increases the rate of the reaction? By decreasing the energy barrier. By decreasing the activation energy barrier. By decreasing the activation energy barrier. Negative catalyst decreases the rate of reaction by increasing the activation energy barrier. By increasing the activation energy barrier. Okay, by increasing the activation energy barrier. So if you want to have a look at it graphically, understand properly. For example, this is your potential energy and this is the progress of reaction. The reaction is, for example, A gives B. Let's say this reaction is right now happening in absence of catalyst, and in absence of catalyst, it's following this particular reaction profile. This is in absence of catalyst. Absence of catalyst. Now, for example, in the same reaction, you are introducing positive catalyst. What does positive catalyst do? It speeds up the reaction. How it speeds up the reaction? How it speeds up the reaction? By decreasing the barrier. So it's going to decrease the barrier like this. This is the reaction profile in presence of positive catalyst. Okay. Similarly, if you use the negative catalyst, that increase the activation energy barrier. So this is the profile in presence of negative catalyst. Okay. Now what is the conclusion here? What is the conclusion here? What this energy gap used to be called? This energy gap used to be called as delta H. Is delta H being affected by any sort of catalyst? Delta H is not affected by any sort of catalyst. Delta H is not affected by neither positive catalyst nor negative catalyst. So delta H is not affected by your catalyst addition. Remember that. Okay. Got it? Got it, people? So catalyst does not affect the delta H. Remember this? Catalyst doesn't effect delta H. I hope all of this is clear to everyone. I hope all of this is clear to everyone. Now guys, let's talk about Arrhenius equation. Let's talk about Arrhenius equation, okay? Just give me a second. Okay, let's have a look on Arrhenius equation now. Or you call it as a temperature dependence. You call it as a temperature dependence. Arrhenius equation, guys. First of all, let me directly give you the Arrhenius equation. K is equal to A e raised power minus E divided by RT. This is your Arrhenius equation. K is equal to A e raised power minus E by RT. Now the point is, on increasing the temperature, when you increase the temperature of the reaction, what will happen to this term, EA by RT? If you increase the temperature of the reaction, that means you are increasing the denominator. If you increase the denominator, this entire term decreases. If this entire term decreases, now multiply this with minus. If you multiply this with minus EA by RT, this entire term now, including minus, it will increase. If this particular term was decreasing, then with minus, it's going to increase. And if it increases, if this particular term increases, that means this power is increasing. If this power increases, that automatically tells you rate constant is increasing. So that means when you increase the temperature of the reaction, rate constant increases. When you increase the temperature of the reaction, rate constant increases. Therefore, rate of the reaction also increases. Right? Rate of the reaction also increases. Now try to understand one more thing. First of all, these parameters here, this A, EA, what are they called as? Let me first of all tell you, this A is called as pre-exponential factor. A is called as pre-exponential factor, or you can call it as the frequency factor as well. Let me tell you, A and EA collectively are called as Arrhenius parameters. A and EA collectively are called as Arrhenius parameters. This pre-exponential factor, it takes into account two things. This pre-exponential factor, remember, it takes into account two things. Number one is called as collision frequency. Number two is orientation factor. The pre-exponential factor A here, it takes into account two things, collision frequency and orientation factor. And one more thing, this entire term, e raised power minus EA by RT, this entire term is called as Boltzmann's factor. This is called as Boltzmann's factor. Right? This is called as Boltzmann's factor. So remember these sort of things first of all. Okay. So if I conclude it, if you have got the reaction A gives B, on increasing the temperature, rate constant of the reaction increases. And remember guys, when you increase the temperature of the reaction by 10 degree, rate constant doubles or becomes even more. When you increase the temperature of the reaction by 10 degree, rate constant either doubles or becomes even more. Why is that? Because when you increase the temperature, nothing happens to activation energy. When you increase the temperature, nothing happens to activation energy. It is just when you increase the temperature, the fraction of molecules that could cross the barrier, those fraction of molecules increases. Those fraction of molecules which cross the barrier, they increases. Okay? कोई यहाँ एंजॉय करने आया है बेटा, एंजॉय यहाँ नहीं, एंजॉय वहीं पे करो जाओ, ठीक है? आई एम ब्लॉकिंग यू राइट नाउ. एंजॉय करना है तो नीट के लिए क्यों पढ़ रहे हो? मतलब आई फेल टू अंडरस्टैंड व्हाट काइंड ऑफ मेंटालिटी यू हैव. नॉनसेंस मेंटालिटी. सैड ऑन योर पार्ट. Okay, all clear? All clear, people? All clear? So remember, when you increase the temperature of the reaction by 10 degree, rate constant doubles or becomes even more. Why is that? Because the fraction of molecules which have got energy greater or equal to activation energy. The fraction of molecules which have got energy greater or equal to activation energy. That means I'm talking about those fraction of molecules which can cross the barrier. Those fraction of molecules increases, due to which more product gets formed, and hence more is the rate of the reaction. Okay? So remember, on increase the temperature by 10 degree, rate constant of the reaction generally doubles or becomes more. Why is that? Because the fraction of molecules which have got energy greater or equal to activation energy, that increases. Okay? Now guys, there's a term called as temperature coefficient. Temperature coefficient, which we represent with what? Temperature coefficient, which we represent with N. How do we define this temperature coefficient? Temperature coefficient is nothing but it is the rate constant of the reaction at temperature T plus 10 degree divided by rate constant of the reaction at temperature T. Rate constant of the reaction at temperature T plus 10 degree divided by rate constant of the reaction at temperature T. For example, what does that mean? See, for example, this is the reaction. This is the reaction. Let's say when the reaction was carried at temperature T, its rate constant was K. Now I'm increasing the temperature of the reaction from T to T plus 10. That means I'm increasing the temperature of the reaction by 10 degree. And when we increase the temperature of the reaction by 10 degree, rate constant generally doubles. If the rate constant initially was K, now it is going to be 2K, for example. Now it's going to be 2K, for example. Now it's going to be 2K, for example. Now, my dear students, N. How do we define N? A rate constant at temperature T plus 10. At temperature T plus 10, what is the rate constant? 2K. 2K. Divided by rate constant at temperature T. Rate constant at temperature T is K. So 2K divided by K. K gets cancelled. The value comes out to be 2. The value comes out to be 2. Okay? Do you understand? Do you understand? Is this clear? So there is a term called as temperature coefficient. Temperature coefficient is nothing but it is rate constant at temperature T plus 10 degree divided by rate constant at temperature T. Yeah? Is this particular point clear? Now guys, as I told you already, when you increase the temperature of the reaction by 10 degree, when you increase the temperature of the reaction by 10 degree, rate constant doubles or becomes even more. Correct? So here I clearly doubled the rate constant. It is not necessary that rate constant will be doubled only. It can be slightly more. If earlier it was K, now it can be 2.1K. It can be 2.2K. It can be 2.3K. So remember, this N can be sometimes 2. This can be sometimes 2.1, sometimes 2.2. So remember the value of N. This is the range of the value of N. It is greater or equal to 2, less than 3. Temperature coefficient, it will be greater or equal to 2, less than 3. Okay? This is one more point which you need to remember. And after remembering this particular point, there is one more result, guys, which I have for all of you. For example, this is the reaction. At temperature T1, the rate of the reaction is R1. Now I'm changing the temperature of the reaction from T1 to T2. From T1 to T2. The rate of the reaction is changing from R1 to R2. Is there any result that could relate all these 4 parameters? Absolutely, there is a result that can relate all the 4 parameters. R2 divided by R1 is equal to 2 times delta T divided by 10. This 2 is basically here, the N. This N basically, temperature coefficient. And I'm assuming N value is equal to 2. I'm assuming N value is equal to 2 means I'm assuming for every 10 degree rise, the rate constant doubles. This is one important result, guys, from which questions have been asked. R2 divided by R1 is equal to 2 raised power delta T divided by 10. And what kind of question can be asked? This is the question over here in front of you. Look at the question carefully. Look at it carefully. Look at the question. First of all, at temperature T1, if the rate of the reaction is R1, at temperature T2, rate of the reaction is R2. Now, what is the relation between all the 4? R2 by R1 is equal to 2 raised power delta T divided by 10. Okay. If I write the general form is R2 divided by R1 is equal to N. N represents temperature coefficient, delta T divided by 10. Okay. So, guys, look at this question. On increasing the temperature of the reaction from 10 degree to 100 degree, how many times rate of the reaction will increase? How many times rate of the reaction will increase? So R2 divided by R1 is equal to 2 raised power delta T. So let me write R2 divided by R1 is equal to 2 raised power delta T, change in temperature, final minus initial, that is 90 divided by 10. So R2 divided by R1 is equal to 2 raised power 9. So which tells you R2 is equal to 2 raised power 9 times R1. So when you increase the temperature of the reaction from 10 degree to 100 degree, the rate of the reaction increases how many times? 2 raised power 9 times. 2 raised power 9 times. Clear? For example, I'm giving you a question. On increasing the temperature of the reaction from 0 degree to 30 degree, 0 degree to 30 degree, how many times the rate of reaction is going to increase? Quickly, without using pen paper. If I increase the temperature of the reaction from 0 degree to 30 degree, how many times the rate of the reaction will increase? Quick. 2 raised power delta T by 10. Delta T is 30 divided by 10 is 3. So 2 raised power 3 times R1. Yeah? Guys, am I clear? So remember this particular result. This is also important. And these sort of basic questions can be asked from this result. Okay, one more important parameter, guys. One more important parameter. I've already mentioned it here. See what the parameter is. You have got the reaction A gives B and other reaction C gives D. 2 reactions we have. Activation energy of first reaction is 10 kilojoules. Activation energy of second reaction is 100 kilojoules. Okay. So both the reactions have got different activation energy. Initial temperature of this reaction is 0 degree. I mean, this reaction was carried out at 0 degree temperature. Even this reaction was carried out at 0 degree. Both the reactions are carried out at same temperature. Right? Now, you are increasing the temperature of this reaction as well as you are increasing the temperature of this reaction. And you are increasing the temperature of both the reactions by equal amounts. You are increasing temperature of both the reactions by equal amounts. So technically, when you increase the temperature, rate constant should increase. Technically, when you increase the temperature, rate constant should increase. But remember, my dear students, that reaction whose activation energy is more, its rate constant increases more than that particular reaction whose activation energy is less. This is very important point. This is very important point. Done? See, I took 2 reactions, their activation energies are different. The reactions were carried out at same temperature. Now you are increasing the temperature of this reaction as well as the temperature of this reaction, and you are increasing the temperature of both the reactions by equal amounts. For example, you are increasing the temperature of this reaction by 20 degree, even you are increasing the temperature of this reaction by 20 degree. So rate constant should increase on increase in the temperature. So rate constant of this reaction will increase as well as rate constant of this reaction will increase. But that particular reaction whose activation energy is more, its rate constant increases more than that of the reaction whose activation energy is comparatively less. This is an important conclusion. Remember that. Okay? Important conclusion. Remember that. My dear students, different forms of the Arrhenius equation, which I've already mentioned. One is your K A e raised power minus Ca by RT, one of the forms of the Arrhenius equation. Its ln form is ln K is equal to ln A minus Ea divided by R into 1 by T. This one more form of the Arrhenius equation. You have to remember all of them. You have to remember all of them. Log K is equal to log A minus Ea divided by 2.303 R into 1 by T. One more form. Log of K2 by K1 is equal to Ea by 2.303 R into 1 by T1 minus 1 by T2. One more form of Arrhenius equation from which equation comes. One more form in terms of half-life. Log of T half 1 divided by T half 2 is equal to Ea divided by 2.303 R 1 by T1 minus 1 by T2. So these are different forms. They have got derivations as well. But as I told you, I'm going to skip all the derivations. You just have to remember these formulas and utilize them in the question. Utilize them in the question. Now, two graphs here are important. Two graphs here are important. The first graph, that is between ln K and 1 by T. So you need to plot a graph between ln K and 1 by T. Ln K and 1 by T. Ln K you are plotting along y-axis. 1 by T you are plotting along x-axis. So this becomes your M. The sign is minus and this is C. This is equal to y is equal to minus mx plus c. Y is equal to minus mx plus c means straight line with negative slope. So this is the straight line with negative slope and its slope is how much? Minus Ca by R. Its slope is how much? Minus Ca by R. Similarly, log K versus 1 by T. This is log K and this is 1 by T. Log K versus 1 by T. Log K you are plotting along y-axis. 1 by T you are plotting along x-axis. This becomes your M. The sign here is minus and this is C. This is equal to y is equal to minus mx plus c. Y is equal to minus mx plus c. Straight line with a negative slope, but the slope right now will be how much? Slope right now will be minus Ea divided by 2.303 R. So remember these two graphs as well because they are frequently asked. They are frequently asked. Okay. Now, for example, this is the question. This is the question. Look at the question carefully. The question is calculate the activation energy of the reaction in kilojoules per mole and in kilocalories per mole. And this is the graph given. Graph is given between log K and 1 by T. I told you a few minutes back. Log K 1 by T. Log K versus 1 by T. Its slope is how much? Minus Ea divided by 2.303 R. Slope is nothing but tan of theta. Slope is nothing but tan of theta. It is given that theta is equal to tan inverse minus 3. That means tan of theta will be minus 3. Tan of theta will be minus 3. So minus minus gets cancelled. Ea will be equal to how much? Ea will be 3 into 2.303 into R. This is the activation energy. Now, as per the question, I need to calculate activation energy in what? First kilojoules. So what do I do? 3 into 2.303. R value I'll take as 8.314 joules per Kelvin per mole. I'm taking the R value in joules. If I take the R value in joules, see, first of all, you should know R has got three values, right? One is 8.314 joules per Kelvin per mole. Second value of R is 0.0821 atm liter per Kelvin per mole. And third is 1.98 calories per Kelvin per mole. So here I am taking the value of R as 8.314 joules per Kelvin per mole. So the answer is right now going to be in joules. But I don't need the answer in joules. I need the answer in kilojoules. So divide it with 1000. So this is going to be the activation energy in kilojoules. Okay. Now, talk about the second one. Calculate the activation energy in kilocalories. So you have to take the value of R in calories. So Ea will be equal to 3 into 2.303 into R. R is how much? R is 1.98. The answer is right now going to be in calories. So divide it with 1000. Now the answer is going to be in kilocalories. Clear? Is this particular stuff also clear? This sort of a question can also be asked, guys. You have to be careful with this. Okay, one more thing. If you have the hypothetical reaction, whose activation energy is 0. You have the hypothetical reaction whose activation energy is how much? 0. The rate constant at temperature 200 Kelvin is 1.6 into 10 raised power 6. Calculate the rate constant at 400 Kelvin. Remember, guys, first of all, take a note of one important point. Activation energy. Activation energy of the reaction cannot be 0. Remember this particular point. Activation energy of the reaction cannot be 0, right? as per your NCERT is concerned. Now, for example, you have got a hypothetical reaction, A gives B. For example, you have got a hypothetical reaction, A gives B, whose activation energy is, for example, 0. This is hypothetical. So hypothetically, I'm assuming activation energy is 0. What will happen? Your Arrhenius equation says K is equal to A e raised power minus EA by RT. Now, if activation energy is 0, this term becomes 0. Anything raised power 0 is 1. So K becomes A. So K becomes temperature dependent or independent. K becomes temperature independent. K becomes temperature independent. So that means if you change the temperature, nothing happens to rate constant. So whatever was the rate constant of the reaction at 200 Kelvin, same is going to be the rate constant of the reaction at 400 Kelvin. So the answer of this question is same, 1.6 into 10 raised power 6. Do you understand? So that hypothetical reaction whose activation energy is 0, its rate constant does not change on changing the temperature. If you change the temperature, nothing happens to rate constant. Remember this particular point. If the statement is asked whether activation energy can be 0 or not, activation energy of the reaction cannot be 0. Okay? Activation energy of the reaction can not be 0. I hope this particular point is clear. And if this particular point is clear, you have got one more question. Which of the following correctly represents Arrhenius equation? Some differential forms are given. What is our Arrhenius equation, guys? See, all these forms are given in terms of ln. Do we have any form of Arrhenius equation in terms of ln? Yes, we have. Ln K is equal to ln of A minus EA divided by R into 1 by T. This is one of the forms of Arrhenius equation which we have. Now, everywhere they have differentiated with respect to temperature. If I differentiate, it's ln of A. If I differentiate with respect to temperature, it becomes d of dt of ln of K is equal to A is a constant. Ln A will be also constant. So d by dt, differential of constant is 0 minus EA by R as such. 1 by T differentiation will be minus 1 by T square. Minus minus makes it plus. So d upon dt of ln of K will be equal to EA divided by RT square. Perfect. So this is the final answer of the question. This is one more form of the Arrhenius equation. D upon dt of ln K is equal to EA by RT square. I hope this sort of a question you should be in a position to solve if it comes. Just write the equation of Arrhenius in terms of ln and differentiate it with respect to temperature and you're done. And you're done. Okay? And you're done. Look at this question. K1 is given, K2 is given. The temperature at which K1 and K2 are equal. The temperature at which K1 and K2 are equal. So we have to calculate the temperature at which K1 becomes equal to K2. What is K1? 10 raised power 16 e raised power minus 2000 divided by T is equal to, what is K2? K2 is 10 raised power 15 e raised power minus 1000 divided by T. Right? So 10 power 15, 10 power 16 cancel. So on this side there is only 10 is equal. This becomes e raised power minus 1000 by T. In the denominator it's e raised power minus 2000 divided by T. Right? If you do a bit of calculation, so keep this 10 as such is equal. EE, bases are same, powers are subtracted in division, so it is going to be e raised power. This comes up, so it becomes 2000 divided by T minus 1000 divided by T. If I take T as common in the denominator, it becomes 2000 minus 1000, which is 1000 by T, right? Perfect. If I multiply throughout with ln, it becomes ln of 10 is equal to ln of E into 1000 divided by T. Ln of 10 is how much? 2.303. Remember it. Because ln 10 will be 2.303 log 10. Ln 10 will be 2.303 log 10. Log 10 is 1. So this is 2.3. Ln of E. Ln of E to the base E is equal to 1. Right? So this just becomes 1000 divided by T. So T will be equal to 1000 divided by 2.303 Kelvin. This is the temperature at which K1, K2 will become equal. This is the temperature at which K1, K2 becomes equal. Okay? Perfect. I hope even this sort of a question you will be able to solve. Then there is one more type of question. This is a complete formula based. I gave you one formula, if you remember, log of K2 divided by K1 is equal to EA divided by 2.303 R 1 upon T1 minus 1 upon T2. This was one of the forms of the Arrhenius equation, which can be used in these sort of questions. The rate constant of the reaction at 227 degree. So initial temperature of the reaction is 227 degree. Convert this in Kelvin, right? So this will be plus 273. So this is your initial temperature in Kelvin. Similarly, 427 degree plus 273. Now it's going to be in Kelvin. So T1, T2 we are given with. Okay. The rate constant of the reaction, I mean K1, K2 is also given to us. K1 is 0.02 and K2 is how much? 0.2. Everything is given. K1, K2 is given. R value, you know, 8.314. Temperature T1, temperature T2, but temperature has to be taken in Kelvin. This question is just a matter of calculation, right? It can be done by just putting the values. There is no concept involved here. Pretty much simple question, guys. At temperature T1, K1 is this. At temperature T2, rate constant is this. Put all the values in this expression, get the value of activation energy, EA. That's it. That's it. One very, very, very small topic, which I have not touched yet. What is that? Have you heard about pseudo first order? Have you heard about pseudo first order reaction? So mark the heading as pseudo first order. What are pseudo first order reactions? Pseudo first order or pseudo unimolecular. Have you studied this ever? Quickly. Just give me a second, guys. Exactly. Pseudo first order reaction is that particular reaction whose molecularity is greater than 1, for example 2, but its order is 1. Pseudo first order reaction is that particular reaction whose molecularity is greater than 1, but its order is equal to 1. What does that mean? For example, you have got a reaction like this. A plus B, it gives C. Okay. I'm writing the term excess here in the bracket. Let's say B is present in excess. Let's say B is present in excess. Now, for example, if I write its rate law, it will be R is equal to K, concentration of A, for example, raised power 1, concentration of B raised power 1. So, first of all, what is the molecularity of the reaction? 1 plus 1, 2. Molecularity of the reaction is 2. Now, what should be the order? Order of the reaction should be 1 plus 1, 2. Order of the reaction should be 2. It should be 2. But. My dear students, but if you see, B is in excess. If B is in excess, it is in larger amount. So that means if you slightly increase or decrease concentration of B, will anything happen to rate? It is already in larger amount. If you increase or decrease its concentration, nothing will happen to it. Nothing will happen to rate. Right? Right, people? So basically, B is in excess. It is in larger amount. If you slightly increase or decrease its amount, nothing will happen to rate. So rate becomes independent of concentration of B. If rate becomes independent of concentration of B, so rate law becomes something like this. There is no B in the rate law. So the reaction looked second order, but in reality, the reaction is of the order. The reaction has got the order 1 in reality. So that particular reaction whose molecularity is more than 1. That particular reaction whose molecularity is more than 1. Okay. Order seems more than 1, but is 1. You call this particular reaction as a pseudo first order. You call this particular reaction as a pseudo first order. Why? Because one of the reactant is present in excess. One of the reactant is present in excess. My dear students, they can ask you its examples as well. So 2 examples you are going to remember for the pseudo first order. The first example is called as hydrolysis of ester, CH3COO, C2H5 plus H2O gives CH3COH plus C2H5OH. This is the first reaction of pseudo first order. And your second is inversion of cane sugar, C12H22O11 plus H2O gives glucose plus fructose. Glucose plus fructose. This was your ester. This is the cane sugar, which got converted into glucose and fructose. And water in both these reactions is present in excess. This is in excess. This is also in excess. Okay. Now, if water is present in excess, so rate does not depend on the concentration of water. Its rate law will be R is equal to K, concentration of CH3, COO, C2H5. So its order, first of all, molecularity of this reaction. Molecularity is 1 plus 1, 2, right? Order look 2, but in reality order is 1. Similarly, in reality order of this particular reaction is also 1. Why is that? Because water is present in excess. And when water is present in excess, you know what happens at that time? Rate becomes independent of its concentration. So with this, your chemical kinetics is done and dusted, and I have not skipped a single thing, guys. I have taught this in very much detail. I hope it's clear. You can tell me once in the chats if it is clear, honestly. Is every single thing clear till now? Yeah? Perfect. Let's take a small break. It's 15:40 right now, so 3:40. So we'll start at 4, huh? And at 4, we'll start with electrochemistry. So take a small break. Okay, take a small break and we shall be starting with the electrochemistry. And I would want everyone to be back on time. See you in 20 minutes. Is everyone back? Is everyone back? All right. So guys, tell me whatever things we discussed till now, is every single thing clear till now? Say it once in the chats. Say it once in the chats. यार वो कल का सेशन पब्लिक कर दो. नहीं नहीं चल रही है, लाइव में हूँ मैं. ओके ओके ठीक है डन डन डन. ओके. ऑलराइट. So should we start, guys? Can you tell me whether you have studied electrochemistry before or not? I just want to know first of all. Can you tell me that? Have you studied electrochemistry before? I just want to know whether you have studied electrochemistry before or not. Say it quickly. I just want to know from everyone. All right, guys. Got it. Got it. Chalo. Let's start the chapter electrochemistry then. Let's start the chapter electrochemistry. My dear students, the first topic that we are going to discuss here in the chapter electrochemistry, what is that? That is your Daniell cell. That is your Daniell cell. First of all, when we talk about the Daniell cell, Daniell cell is basically the most typical example of what? It is the most typical example of the galvanic cell. It is the most typical example of the galvanic cell. And what does a galvanic cell do? Galvanic cell, it converts chemical energy into the electrical energy. Galvanic cell converts chemical energy into the electrical energy. So what this Daniell cell is going to do basically? This Daniell cell is going to convert your chemical energy into the electrical energy. Now that's what we have to see, how it converts chemical energy into the electrical energy and what all things we have to remember here. Try to understand very carefully what exactly I'll be saying. My dear students, in case of Daniell cell, in case of Daniell cell, we will be exactly using two electrodes. We'll be exactly using two electrodes. One is going to be your zinc electrode, one is going to be your copper electrode. Now, if I first of all compare zinc and copper, zinc is considered to be more electropositive. Zinc is considered to be more electropositive, and copper comparatively is considered to be less electropositive. The one that is more electropositive, that will be having the tendency to lose electrons. And the loss of electrons is what we call as oxidation. Loss of electrons is what we call as oxidation. So basically, at zinc electrode, oxidation is going to take place. Therefore, at copper electrode, what is going to take place? A reduction is going to take place. Remember, oxidation always takes place at anode and reduction always takes place at cathode. Okay? These are two basic things which I would want you guys to remember first of all. Okay? So first of all, zinc. Zinc is going to behave as the anode and copper electrode is going to behave like the cathode in case of your Daniell cell. Now, how this Daniell cell is made and how does it work? Let's talk about that now in detail. My dear students, for example, let's say this is the container. And in this container, I'm keeping zinc sulfate. In this container, I'm keeping zinc sulfate. So this zinc sulfate in the container, it would have dissociated as zinc dipositive plus SO4 dinegative. The zinc sulfate in the container, it would have dissociated as zinc dipositive plus SO4 dinegative. I would say this solution contains equal number of cations and anions. So this solution is electrically neutral. The solution is neutral right now. Now, what exactly am I going to do? I'm going to place a zinc rod here. I'm going to place a zinc rod in the solution. Okay? And this particular setup, I'll be calling as electrode. This is a zinc electrode. When the rod is introduced in a solution containing its own ions. When the rod is introduced in a solution containing its own ions, this setup is called as electrode. So which electrode this is? This is your zinc electrode. Similarly, guys, here, for example, I'm taking one more container. And in this particular container, I'm keeping, for example, copper sulfate. And this copper sulfate would have dissociated as copper dipositive plus SO4 dinegative. Even this solution contains equal number of cations and anions. So this solution is also electrically neutral. And in this particular solution, I'm introducing copper rod. So I've introduced copper rod in a solution containing its own ions. Okay. So this particular setup again is called as the electrode. So I've got two electrodes here. One is your zinc electrode, one is your copper electrode. Now, my dear students, I am connecting these electrodes externally. I'm connecting these electrodes externally, right? I'm connecting these electrodes externally with the help of a voltmeter, for example, with the help of a voltmeter. And my dear students, internally, I'm connecting these electrodes with the help of an inverted U-type tube. Internally, I'm connecting these electrodes with the help of inverted U-type tube. And this inverted U-type tube, what does it contain? It contains an inert electrolyte. It contains an inert electrolyte which is mixed with gelatin or agar-agar. It is mixed with gelatin or agar-agar. And inert electrolyte like your K2SO4. So this inverted U-type tube, it contains an inert electrolyte like your K2SO4, like your NH4Cl, mixed with gelatin or agar-agar. And when inert electrolyte is mixed with gelatin or agar-agar, what do we get? We get a jelly-like paste. We get a jelly-like paste. And that jelly-like paste is basically kept inside this inverted U-type tube. And let me tell you, this inverted U-type tube that contains this jelly-like paste, what do we call this inverted U-type tube as? This is called as the salt bridge. This is called as the salt bridge. So in the salt bridge, what kind of ions will be there? I would say in the salt bridge, there will be K positives and SO4 dinegatives. In the salt bridge, there will be K positives and SO4 dinegatives inside the salt bridge. And my dear students, the ends of this U-type tube, the ends of the salt bridge, they are sealed with the cotton balls. They are sealed with the cotton balls. Okay. Now what happens here? Now what happens here? I told you already in Daniel's cell, the zinc electrode, it behaves like anode. And at anode, what happens? Oxidation. Oxidation means loss of electrons. Now, my dear students, since this zinc rod is made up of zinc atoms, those zinc atoms of which rod is made up of, those zinc atoms will undergo oxidation. So, the zinc atom of which rod is made up of, it will undergo oxidation. It will get converted into zinc dipositive, and with that, you'll be getting 2 electrons. So basically, this zinc rod, it is made up of zinc atoms. One of the zinc atom will undergo oxidation, will get converted into zinc dipositive. With that, you get 2 electrons. With that, you get 2 electrons. And those 2 electrons are accumulated on the rod. And this extra zinc dipositive goes into the solution. And when the extra zinc dipositive goes into the solution, I would say solution will get the positive charge. Because earlier the solution was neutral. Now extra zinc dipositive is entering into the solution. So solution got positive charge. And 2 electrons got accumulated on the rod. Now again one more zinc atom. Again one more zinc atom will undergo oxidation, will get converted into zinc dipositive. Again 2 more electrons will get accumulated on the rod. So on the rod, electrons are being accumulated. If electrons are accumulated on the rod, so I would say this particular rod will have negative charge on it because electrons are accumulated on it. Perfect. Now, what happens at cathode? If I ask you, at cathode reduction takes place, you know it. At cathode reduction takes place. Reduction means gain of electrons. Reduction means gain of electrons. Reduction means gain of electrons. Now, my dear students, if you look carefully, talk about this particular solution. In this solution, there is copper dye positive and SO4 dye negative. The copper dye positive which is there in the solution, that collides with the rod. Copper dye positive which is there in the solution, that collides with the rod, takes 2 electrons from the rod, gets converted into copper solid. And that copper solid is deposited on the rod. Now think over it. If copper dye positive which was there in the solution, if it collides with the rod, takes 2 electrons from the rod, so electrons are snatched from the rod, due to which rod gets which charge? Positive charge. Rod gets positive charge. My dear students, this rod carries electrons. The path is already created. Can I say there will be the moment of electrons? Absolutely, there is moment of electrons. Is it just the moment of electrons, or this is the moment of electrons in a particular direction? This is the moment of electrons in a particular direction. And whenever charge flows in a particular direction, current is generated. Current is generated, right? Perfect. So the first question that will be asked here in the Daniel cell, what is the direction of electrons? Electrons, they move from anode to cathode. Electrons move from anode to cathode. If electrons move from anode to cathode, what will be the direction of current? If the moment of electrons is from anode to cathode, the direction of current will be from cathode to anode. The direction of current will be from cathode to anode. Perfect. Because the direction of current is always opposite to the direction of electrons. Clear? Now, my dear students, this rod, if you look, from this zinc rod, one zinc atom got oxidized, got converted into zinc dipositive, entered into the solution. One more zinc atom got oxidized, got converted into zinc dipositive, entered into the solution. So from the rod, zinc atoms are getting oxidized, right? So what would happen to the thickness of this rod with time? So remember, thickness of zinc rod, it decreases with time. Since copper is being accumulated on this rod, so thickness of copper rod, what happens to it? It increases with time. This is one more important thing which you need to know. Okay, thickness of zinc rod decrease with time, thickness of copper rod increase with time. Yeah. Now we will one more important thing. This is the reaction at anode, this is the reaction at cathode. Are the electrons balanced in both the reactions? Yes, 2 electrons. The electrons are balanced. So you can directly add these 2 reactions. And when you add these 2 reactions, this 2 gets cancelled. My net reaction is going to be zinc solid plus copper dye positive aqueous. It gives what? It gives zinc dye positive aqueous plus copper solid. This is my net reaction. This is the net reaction that takes place in the Daniel cell, right? How many electrons got cancelled? 2. So I would say the value of N here is 2. Value of N here is 2 means the number of moles of electrons. Number of moles of electrons exchanged. Number of moles of electrons exchanged in the net cell reaction. In the net cell reaction, that's equal to 2. That's equal to 2. I believe till here every single thing is clear. Yeah? So do you see what this cell is doing exactly? This cell is converting chemical energy. Because of the chemical reactions happening here, right? What is happening? Electrical energy is being generated. So that particular cell which converts chemical energy into electrical energy, you call that as the galvanic cell. And this is the most typical example of the galvanic cell. What is the name of it? What is the name of it? You call it as the Daniell cell. Okay. Now, my dear students, the salt bridge which we have used, what is the function of the salt bridge? Why did we use the salt bridge? The first point. What the salt bridge is doing here, see, salt bridge is completing here the internal circuit. Salt bridge is completing the internal circuit. So, if you talk about the functions of salt bridge, if you talk about the functions of salt bridge, the first thing which I would say, the salt bridge, it completes the internal circuit. It completes the internal circuit. Number one. Number two, the salt bridge maintains the electrical neutrality. It maintains the electrical neutrality of both the solutions. It maintains the electrical neutrality of both the solutions. Third point, it avoids liquid junction potential. It avoids the liquid junction potential. See guys what it means. First of all, this solution earlier was electrically neutral. This solution earlier was electrically neutral. Now, when the zinc atom came from the rod, got converted into zinc dipositive, that zinc dipositive entered in the solution. Due to that, this particular solution got the positive charge. As soon as this solution gets the positive charge, as soon as this particular solution gets the positive charge, at the same time, from the salt bridge, SO4 dinegative will come and will neutralize this charge. At the same time, SO4 dinegative will come and will neutralize this particular charge. And similarly, guys, since copper dipositive, which was there in the solution, it collided with the rod, took 2 electrons from the rod, got converted to copper solid. That copper solid got deposited on the rod, due to which the number of Cu dipositives here in this solution, are decreasing. Earlier, cations and anions were equal in number in this solution. Now, cations are decreasing. Why? Because Cu dipositive collides with the rod, got converted into copper solid, and that copper solid got deposited on the rod. So, in the solution, copper dipositive number is decreasing, due to which this solution effectively gets which charge? This solution effectively gets negative charge. As soon as negative charge comes in the solution, at the same time, K positive is going to come and will neutralize this. So, basically, this salt bridge, it's one of the important function is, it maintains the electrical neutrality of both the solutions. It maintains the electrical neutrality of both the solutions. Okay? It maintains the electrical neutrality of both the solutions. Now, my dear students, at the same time, this is one of the important points. It avoids the liquid junction potential. What is meant by that? Avoiding liquid junction potential. For example, this is one bigger sized container which I have taken. I'm dividing this container into 2 equal parts with the help of semi-permeable membrane. Now, in this left chamber, for example, I am keeping zinc sulfate. In this left chamber, I am keeping zinc sulfate. And this zinc sulfate, for example, got dissociated as zinc dipositive plus SO4 dinegative. In this right chamber, for example, you are keeping copper sulfate. And this copper sulfate, for example, got converted into copper dipositive plus SO4 dinegative. Right? Now, for example, what you are doing, here you are introducing a zinc rod. This is a zinc rod, and here you are introducing a copper rod. Here you are introducing a copper rod. For example, you are not using any salt bridge here. Let's say you are not using any salt bridge here. My dear students, first of all, I'm connecting these electrodes with the help of voltmeter. I've connected them. Now, I'm not introducing any salt bridge here. First of all, the circuit is externally complete. It is a complete circuit, externally complete. Internally also, circuit is complete. Internally also, the circuit is complete. So you are getting a closed loop here. Closed loop here, that means the circuit is complete. If the circuit is complete, what is going to happen? At anode, this is your anode. At anode, oxidation takes place, right? Oxidation takes place. Oxidation of zinc atoms of which rod is made, due to which positive charge gets accumulated here in the solution. Similarly, due to reduction, negative charge gets accumulated on this solution. Now, positive and negative, they are going to attract each other and they will get accumulated here at the junction. Similarly, positive and negative will keep on accumulating at the junction. Positive negative gets accumulated at the junction. So what is happening at this particular junction? See the left side of this junction. I would say left side of this junction is at positive potential. Right side of this junction is at negative potential. Can I say at the junction potential difference got created? And this potential difference which got created at the junction, this potential difference is called as liquid junction potential. You call this potential difference as liquid junction potential. And my dear students, if you do not use salt bridge, this liquid junction potential gets raised. If salt bridge is not used, what do you get? You get a liquid junction potential. But if you would have used the salt bridge, what would have happened? What would have happened? As soon as positive charge got developed in this solution, at the same time from the salt bridge, anion would have come, would have neutralized this. As soon as negative charge got developed here in the solution, at the same time, cation would have come, would have neutralized this, due to which there would have been no positive, no negative. If there was no positive, no negative, there would have been no potential difference here at the junction. So can I say salt bridge avoids liquid junction potential? I believe this is clear. Now, at the same time, there are two more things which you need to know. What is that? My dear students, the inert electrolyte which you use, here in the salt bridge, there are some properties of these inert electrolytes too. If you look carefully, in this net cell reaction, do you see any inert electrolyte ion? Do you see any K positive or SO4 dinegative in the net cell reaction? No. Remember, the first thing, ions of the inert electrolyte should not participate in the net cell reaction. Number one. Number two, the speed with which anion enters into the solution, with the same speed, cation should also go into the solution. Both the ions should move into the respective solutions with the same speeds. What does that mean? That means I would say the ionic mobilities. Of both the ions. The ionic mobilities of both the ions should be the same. Okay? Or in other words, we say the ions should have same transportation number. You can say it like that too. Am I clear till here? Did you understand what this galvanic cell is, how this works? And what are the important parameters which are related to the galvanic cell? Am I clear? Everyone once? Everyone quickly in the chats. Everyone quickly in the chats, people. Say yes or no quickly in the chats, guys. Is it all clear? Okay. Now let's move on. Guys. Let's move on. Now the point is, how do we represent the galvanic cells? See guys, how do we exactly represent the galvanic cells? Try to understand. This is also important. First of all, in the middle, you'll be drawing two parallel lines in the middle. And these two parallel lines, what do they represent? They represent the salt bridge. And let me tell you, on the left side of it, we write anode. On the right side of it, we write cathode. On the left side of it, we write anode. On the right side of it, we write cathode. Perfect. And you know, at anode, what happens? At anode, oxidation takes place. And at cathode, reduction takes place. This This is the general way of the representation of the galvanic cell. In the middle, put the two lines, salt bridge. On the left side of the salt bridge, anode. On the right side of the salt bridge, it's going to be cathode. Now see what we are going to do. For example, you have got a galvanic cell whose net cell reaction is this one. You have got a galvanic cell whose net cell reaction is this one. Okay. Now I have to represent this galvanic cell. How do I represent it? Tell me the charge on this zinc. It is 0. What is the charge on this zinc? +2. 0 to +2. Is the oxidation state increasing or decreasing? 0 to +2. Increase in the oxidation state. Increase in the oxidation state is called as oxidation. So I would say the zinc is undergoing oxidation here. Increase in the oxidation state is called as oxidation. So zinc is undergoing oxidation here. Similarly, +2 to 0. +2 to 0. +2 to 0 means decrease. Decrease in the oxidation state is what you call as reduction. So this copper dye positive is undergoing reduction. So I got to know your zinc is undergoing oxidation and copper is dye positive is undergoing reduction, right? And I have told you something already. Oxidation takes place at anode and reduction takes place at cathode. Reduction takes place at cathode. Now, my dear students, I'm drawing a two lines which represent the salt bridge. On the left side of the salt bridge, what do we write? We write anode. At anode, oxidation takes place. At anode, oxidation takes place. Your zinc is getting converted into zinc dye positive. So I would say zinc solid is getting converted into zinc dye positive at anode, right? Now, this is solid, this is aqueous. Is the phase same or different? Phase is different. Solid, aqueous, different phases. When phases are different, use the slash. When phases are different, use slash. If phases are same, we are supposed to use comma. Okay. Now go to the right side of the salt bridge. Right side means cathode. At cathode, reduction takes place. Reduction of what? Copper dye positive. So I would say copper dye positive aqueous gets converted into what? Gets converted into copper solid. Now, is the phase same or different? Phase is different. If the phase is different, use the slash in between. So this is how you represent a galvanic cell. Am I clear? Let's take a few more cases so that it becomes properly clear to you. For example, this is your cell, guys. Let's say we have got a galvanic cell whose net cell reaction is this one. Now, from the net cell reaction, we have to represent this cell. Again, how do we represent it? Again, how do we represent it? Again, how do we represent it? I think I should be blocking a lot of people. I should be blocking a lot of people now. Just give me a second. Who's this button nonsense? Logged. Who's the other one? Who's the other one? Just a second. Over. Okay. All right. Listen now. If I ask you what is the charge on this iron, it's 0. Charge on this copper, that's +2. Charge on this iron is +2. And charge on this copper here is 0. Now understand 0 to +2. Increase. Increase means oxidation. Increase means oxidation. And oxidation takes place at anode. Oxidation takes place at anode. Right? Now, +2 to 0. Decrease in the oxidation state. Decrease in the oxidation state is called as reduction. And you know, reduction takes place at cathode. So you identified your anode and cathode. Now, these two lines represent the salt bridge. On the left side of the salt bridge, you write anode. At anode, oxidation takes place. Oxidation of what? Oxidation of Fe solid. So Fe solid is getting converted into Fe dipositive aqueous. Right? Is the phase same or different? Phase is different. If the phase is different, put slash in between. Put slash in between. Right? Now, on the right side of the salt bridge, what do we write? We write cathode. At cathode, reduction takes place. Reduction of what? Cu dipositive. So Cu dipositive aqueous is getting converted into what? Is getting converted into copper solid. Is the phase same or different? Phase is different, so slash in between. So this is how you are representing this particular cell. Okay. Now, my dear students, let's take one more case. Let's take one more case. Understand this one. Zinc. The charge on zinc is 0. Hydrogen has got the charge +1. This zinc is in +2. This hydrogen is in 0. Now, 0 to +2, increase. Increase means oxidation. Oxidation takes place at anode, right? So this would be automatically cathode. This would be automatically cathode. So these two lines, salt bridge, on the left side, anode. At anode, zinc solid is getting converted to what? Is getting converted into zinc dipositive aqueous. Is the phase same or different? Phase is different. So use the term slash. Right side, cathode. At cathode, reduction. H positive aqueous. H positive aqueous is getting converted into what? H positive aqueous is getting converted into H2. Is the phase same or different? Phase is different. Aqueous, gas, phase is different. Use slash. Right? Now, at the same time, one more important thing. One more important thing, guys. Try to understand. See, these two lines is the salt bridge. Left side is one electrode, right side is one more electrode. This electrode is a normal electrode, solid aqueous. Solid aqueous means normal. Whenever you see any electrode apart from solid aqueous, whenever you see any electrode apart from solid aqueous, like this, gas aqueous or aqueous, something like that. Whenever you see any electrode other than this format, other than solid aqueous format, at that time, you'll be writing platinum solid as well on that particular side. You'll be writing platinum solid as well on that particular side. Okay. For example, if I take one more case, talk about this one. Silver here is in +1 oxidation state. The charge here is +1. The charge here is 0. The charge here is 0. The charge here is +1. Now again, if you look carefully, +1 to 0, decrease. Decrease means reduction. Reduction means cathode. Right? If this is cathode, that means this is supposed to be anode. Now, my dear students, these two lines, what do they represent? Salt bridge. On the left side of the salt bridge, we write anode. At anode, you see H2 is getting converted into H positive. So I would say H2 gas getting converted into H positive aqueous. Now, is the phase same or different? Phase is different. Use the term slash. Now, this is gas aqueous. It is not solid aqueous. If it is not solid aqueous, so comma karke, you have to use platinum solid on this side. Now, on the right side, we write cathode. At cathode, you see Ag positive getting converted into Ag. I'll say Ag positive aqueous got converted into Ag solid. Is the phase same or different? Phase is different. Use the term slash. So this is how you represent this particular cell. Okay. Perfect. See, this stoichiometric coefficient here is 2, right? You are not supposed to write 2 here. The stoichiometric coefficient here is 2. Twice H positive. You are not supposed to write 2 H positive. Just write H positive, just write Ag. That's enough. Okay. Perfect. I believe this sort of a thing is clear. Now, guys, one more thing. One more thing. For example, you have got a galvanic cell whose net reaction is this one. If net reaction is this one, from this net reaction, I have to represent the cell. Now, how do I represent this particular cell? Try to understand. For example, calculate the oxidation state of chromium here. I hope you know how to calculate oxidation state. This is going to be 2x. This will show -2 into 7 is equal to -2. Let me show it to you. 2x plus oxygen shows -2 into 7 is equal to -2. So x value when you solve, it comes out to be +6. This is how you calculate oxidation state, I believe. You know it. Right? Now here, iron is in +2 oxidation state already. Chromium here is in +3 oxidation state. Iron here is in +3 oxidation state. Now, my dear students, +6 to +3, decrease. Decrease means reduction. Reduction means reduction takes place at cathode. So this is cathode. Now, Plus 2 to plus 3, increase. Increase means oxidation. Oxidation takes place at anode. So one is your cathode, one is your anode. In the middle, use two lines, salt bridge. On the left side of the salt bridge, what do we do? On the left side of the salt bridge, we write anode. At anode, do you see Fe di positive? Do you see Fe di positive is getting converted into Fe tri positive? Right? Tell me one thing. Is the phase same or different? Phase is same. And when the phase is same, what do we use? We use comma in the middle. When the phase is same, we use comma in the middle. Right? Perfect. Am I clear, people? Yeah? Now, at the same time, whenever you see any electrode apart from solid aqueous, like this, aqueous. So, I have to use platinum solid as well on this side. Right? Because this is not solid aqueous. Apart from solid aqueous, whenever you see anything, what do we use? We use platinum on that particular side. On the right side, what do we do? On the right side, we write cathode. Right? And at cathode, what is happening? At cathode, reduction is happening. Cr2O7 di-negative. Cr2O7 di-negative aqueous is getting converted into what? Is getting converted into Cr tri-positive aqueous. Now tell me one thing. Is the phase same or different? Again, the phase is different. Sorry, again, the phase is same. When the phase is same, we are supposed to separate them with comma, right? Now, it is not solid aqueous. It is aqueous. So on this side also, I'll be using platinum solid. I hope you got to know how do we exactly represent. I hope you got to know how do we represent a galvanic cell. Yeah? Who is this Afan Yasin? Of course, everyone learns, bro. Right? Who comes with knowledge from the mother's lap? Everyone learns from the books, right? You can go to some other channel, not here. Okay? I hope all of this is clear to everyone. Now, guys, I'm going to teach you something which will be used. I'm going to teach you something which will be used in the Nernst equation. So understand properly what exactly I'm going to say. Understand properly, because this is something important and basic only. What is that? That is, how do we write? How to write net cell reaction and QC. How to write net cell reaction and QC. QC is what you call as reaction quotient. QC is what you call as the reaction quotient. Now the point is, how do we write the net cell reaction and the value of QC? Let's try to understand. For example, I'm giving you a cell over here. The cell is simple. It is zinc solid, gives zinc di-positive aqueous. This is the salt bridge. Let's say this is copper di-positive aqueous, and on this side I'm writing copper. This is a cell, for example. If it is a cell, how do we write its net cell reaction first of all? Try to understand very carefully. First of all, on the left side of the cell, on the left side of the salt bridge, what do we have? We have anode. So this is your anode first of all. And at anode, what happens? Oxidation. Oxidation means loss of electrons. Do you see zinc getting converted into zinc di-positive? If zinc gets converted into zinc di-positive, first of all, at anode oxidation takes place. Oxidation means loss of electrons. Loss of electrons. So zinc is basically losing some electrons and then getting converted into zinc di-positive. Now think over it. How many electrons this zinc will be losing to go into zinc di-positive? I would say this zinc would be losing 2 electrons and then it would be getting converted into zinc di-positive. Right? Now, talk about cathode, people. At cathode, what happens? At cathode, reduction happens. Reduction means gain of electrons. Reduction means gain of electrons, right? So at cathode, copper di-positive is getting converted into copper, right? Copper di-positive into copper. So I would say copper di-positive aqueous would be gaining 2 electrons and then getting converted into copper solid. See, at anode, oxidation takes place. Oxidation means loss of electrons. At cathode, reduction takes place. Reduction means gain of electrons. Now tell me one thing. Are the electrons balanced in both the reactions? Are the electrons balanced in both the reactions? Absolutely, electrons are balanced in both the reactions. So you can directly add these two reactions. And when you add these two reactions, the net reaction is going to be zinc solid plus copper di-positive aqueous. It gives zinc di-positive aqueous plus copper solid. This is my net reaction. So how many electrons got cancelled? 2. So the value of N here is 2. The value of n here is 2. Now, I'm going to teach you something which you need to know. What is that? That is, how do we write the reaction quotient? How do we write the expression of reaction quotient? Reaction quotient expression is written in the similar way as you write equilibrium constant expression. Reaction quotient expression you write in the similar way as you write the equilibrium constant expression. How exactly? You start with the product. This product is an aqueous phase, so use the term concentration. So it's concentration of zinc dipositive, raised power stoichiometric coefficient 1. This is in solid phase. The one that is in solid phase, its active mass is taken as 1. Its active mass is taken as 1, divided by. Go to the reactant side. This is in solid phase, its active mass is 1. This is in aqueous phase. The one that will be in aqueous phase, you have to take its concentration. Concentration of copper dipositive, raised power stoichiometric coefficient. So this is how you write the net reaction. You get the value of n, and you get QC over here, right? What is the difference between QC and KC? That we'll understand equilibrium, not here. Okay, it's a huge topic. All right. No, n is 2. You just have to see how many electrons got cancelled. So 2 electrons got cancelled. Okay. Let me take one more example. With that, things will be more clear. For example, I'm writing the reaction like this. Sorry, I'm writing the cell like this. Platinum solid. This is, for example, H2 gas. This is H positive aqueous. Right? This is salt bridge. Let's say this is copper dipositive aqueous. And this is copper solid. Let's say this is your cell. Now you have to write the net cell reaction. You have to get the value of n, and you have to get the QC value. All the things you have to do. Now, first of all, on the left side, you have got your anode always. So this is your anode, and this is supposed to be your cathode. Now you tell me one thing. At anode, what happens? Oxidation. At anode, what happens? Oxidation. Oxidation means loss of electrons. Do you see H2 is getting converted into H positive? So the reaction is supposed to be H2 gas. It gives H positive aqueous. Now, you have got 2 hydrogens on this side, so this should be 2H positive. Now, at anode, oxidation takes place. Oxidation means loss of electrons. Oxidation means loss of electrons, right? So basically, when H2 would be getting converted into H positive, it would be losing electrons. Now, the point is how many? How many it would be losing? How do we check it basically? You check it like this. 0 to plus 1. 0 to plus 1. What is the change in oxidation state? Final minus initial. Final minus initial. The value is 1. 1 is the change for one atom. How many we have? 2. So 1 into 2 comes out to be 2. This is how we check the number of electrons lost or gained. Yeah. Now similarly, if I talk about cathode, at cathode, reduction takes place. Do you see copper dipositive is getting converted into copper? Right? At cathode, reduction takes place. Reduction involves gain of electrons. So copper dipositive would be gaining electrons, then getting converted into copper solid. I would say copper dipositive aqueous would be gaining 2 electrons and then getting converted into copper solid. Perfect. I got the reaction at cathode as well. Now, are the electrons balanced? Yes, the electrons are balanced, so you can directly add them up. So 2 gets cancelled. My net reaction will be like this. H2 gas plus Cu dipositive aqueous. It gives 2 times H positive aqueous plus copper solid. This is my net reaction. This is my net reaction. If I write QC expression, start with the product. This is in aqueous phase. The one that's in aqueous phase, use the term concentration. So concentration of H positive raised power 2. This is in solid phase. The one that's in solid phase, its active mass is 1. Nothing to do with that. Divided by. This is in gaseous phase. The one that's in gaseous phase, use the term pressure for it. So pressure of H2 raised power stoichiometric coefficient 1. This is in aqueous phase. The one that's in aqueous phase, use the term concentration. So concentration of copper dipositive raised power 1. So this is how you get net reaction. This is how you get the QC. And this is how you get the value of N. I believe I'm clear to everyone. Yeah? I believe it's clear to everyone. Perfect. One more example I'm giving, guys. One more example I'm giving. Or just tell me you got to know how to do this. Or let me give you one more example. Slightly difficult one. In net reaction, you don't have to write this platinum. No. In net reaction, you don't have to write platinum. Platinum is only written when you represent the cell. Am I clear, guys? Let me give you one more example, right? A comparatively difficult one. Okay, with that, things will be like a lot clear to you. For example, I'm writing the cell like this. Platinum solid, Fe di positive aqueous, Fe tri positive aqueous, salt bridge. Let's say this MnO4 negative aqueous and this Mn di positive aqueous. And this is platinum solid. Okay. Now let's get to know how do we represent this one. First of all, if you look carefully, these are the two lines which represent the electrode. Sorry, which represent the salt bridge. On the left side of the salt bridge, what do we have? We have anode. On the right side, what do we have? We have cathode. Now you tell me, at anode what happens? At anode oxidation takes place. At anode oxidation takes place. Oxidation means loss of electrons. Oxidation means loss of electrons. Now see, plus 2 to plus 3. Plus 2 to plus 3. Increase in the oxidation state. Increase in the oxidation state means loss of electrons, right? So basically, at anode, Fe di positive would be getting converted into what? Fe tri positive. Now in this reaction, whether gain of electrons will be happening or loss of electrons. Of course, loss of electrons. Plus 2 to plus 3. Increase. Increase means oxidation. Oxidation means loss of electrons. So this one electron, right? Why did I write 1 here? Because plus 2 to plus 3. What is the change? Final minus initial. The value comes out to be 1. Okay. Now similarly, if you talk about cathode, at cathode what is going to happen? At cathode reduction will happen. Why reduction? Understand. Manganese here will be in plus 7 oxidation state. So it's in from plus 7 to plus 2. Decrease. Plus 7 to plus 2. Decrease in the oxidation state. And decrease in the oxidation state is what you call as reduction. Reduction means gain of electrons. So MnO4 negative would be gaining electrons, then getting converted into Mn di positive. I would say MnO4 negative would be gaining electrons and then getting converted into Mn di positive. Now the point is how many electrons it would be gaining. Plus 7 to plus 2. What is the change? Plus 7 to plus 2. What is the change? Plus 7 to plus 2. What is the change? Final minus initial. The value comes out to be 5. So it would be gaining 5 electrons, then getting converted to Mn di positive. Now tell me one thing. Are the electrons balanced in both the reactions? No, the electrons are not balanced yet. So we are supposed to balance these electrons. How do we balance it? Multiply this particular reaction by 5. So this becomes 5 times, this becomes 5 times, and this becomes 5 times. Now do one thing, just add these two reactions. When you add these two reactions, this 5 gets cancelled. So your net reaction is supposed to be like this. 5 times Fe di positive aqueous plus MnO4 negative aqueous. MnO4 negative aqueous, it gives what? It gives 5 times Fe tri positive aqueous. And with that, you'll be writing Mn di positive aqueous. Okay. Now, if I ask you whether this is the complete net reaction, no, it's not the complete net reaction. It is not the complete net reaction. Why? Why is that? Because oxygen is not balanced here. Oxygen is not balanced here. How do you balance oxygen? Oxygen is balanced with the help of water. See how? First of all, we have got 4 oxygen atoms on left side. There is no oxygen on right side. So right side is oxygen deficient. How many oxygen deficiencies on right side? 4 oxygen deficiencies. So add 4 water molecules here. Add 4 water molecules here to balance oxygen. Now balance hydrogen. Now balance hydrogen. Any hydrogen on this side? No. Any hydrogen on this side? Yes. How many? 8. So this side is hydrogen deficient. So I'll be adding 8 H positives on this side. And all the ions, they'll be written always in aqueous phase. All the ions will be in the bracket, you'll be writing aqueous with them. Okay. Now, my dear students, if I want to write the QC expression, I'll be starting with the product. So I'll be writing the concentration of Fe tri positive raised power stoichiometric coefficient 5. Concentration of Mn di positive stoichiometric coefficient 1. Water is in liquid phase. For solids and liquids, active mass is unity. You know that, right? Divided by. Go to the reactant side. Start with H positive. This is an aqueous phase. So the one that's in aqueous, use the term concentration. So concentration of H positive raised power 8. This is also an aqueous phase. So concentration of Fe di positive raised power stoichiometric coefficient 5. And this is going to be concentration of MnO4 negative raised power stoichiometric coefficient 1. This is how you write the QC expression. You wrote the net reaction and 5 electrons got cancelled. So N value here is 5. That means 5 moles of electrons will be exchanged between anode and cathode. I believe I'm clear to everyone. If yes, let me know once in the chats quick. Let me know once in the chats if all this stuff is clear to everyone. Quickly, guys. Done with this? I'm moving ahead, guys, and let's talk about one more important topic. What is that? That is electrode potential. Okay, this is one of the most important topics of the chapter. Okay, electrode potential. First of all, how do we define electrode potential? How do we define electrode potential? Let me tell you, electrode potential is nothing but it is the potential difference. The potential difference that gets created. It is the potential difference that gets created between the rod and the solution. The potential difference that gets created. The potential difference that gets created between the rod and the solution. What does that mean? Try to understand. For example, imagine that this is a solution containing zinc sulfate. Solution containing zinc sulfate, right? So zinc sulfate would have dissociated as zinc dipositives plus SO4 dinegatives. So I would say in this solution there would be equal number of cations and anions. Let's say in this solution there would be equal number of cations and anions. If there are equal number of cations and anions in this solution, can I say this solution is right now electrically neutral? Absolutely. This particular solution is right now electrically neutral. Okay. Now, my dear students, what I'll be doing? I'll be introducing a zinc rod here. I'll be introducing a zinc rod here, right? I'll be introducing a zinc rod here. I've introduced zinc rod in a solution containing its own ions. I've introduced zinc rod in a solution containing its own ions. So this particular setup is called as electrode. And which electrode this is? This is your zinc electrode, right? Now this zinc electrode, it can behave like anode or it can behave like cathode, right? An electrode can behave like anode, it can behave like cathode as well. Now you tell me, when the electrode behaves like anode, what happens? Oxidation. So if the zinc electrode behaves like anode, what's going to happen? Oxidation. So basically, the rod is made up of zinc atoms. Those zinc atoms will undergo oxidation. And I would say zinc solid will get converted into zinc dipositive. With that, you get 2 electrons. Since the rod is made up of zinc atoms, right? And those zinc atoms are undergoing oxidation, getting converted into zinc dipositive. And that zinc dipositive goes into the solution, due to which the solution gets which charge? The solution gets positive charge. And these 2 electrons are accumulated on the rod. These 2 electrons are accumulated on the rod, due to which the rod got which charge? Since electrons are accumulated on the rod gets negative charge. The solution gets positive charge. If rod gets negative, solution gets positive. Can I say potential difference got created between the rod and the solution? Yes, potential difference got created between the rod and the solution. And this potential difference, which got created between the rod and the solution, this is called as electrode potential. This is called as electrode potential. So whenever potential difference gets created between the rod and the solution, this potential difference is what you call as electrode potential. This is what you call as electrode potential, which I'm representing with E. Okay, which I'm representing with E. Now, my dear students, at the same time, this electrode could have behaved like cathode as well. It could have behaved like cathode as well, because any electrode can behave like anode or cathode sometimes. Correct? So this zinc electrode, I made sure that this zinc electrode behaves like anode here. Now the same zinc electrode, it could behave like cathode as well. And when it behaves like cathode, what's going to happen? Reduction. Let's try to understand what's going to happen at that time. See, in this particular solution, what do we have? We have got zinc sulfate. And this zinc sulfate got completely converted into zinc dipositives and SO4 dinegatives. The solution is electrically neutral right now. The solution is electrically neutral right now. Now here, I'm introducing zinc rod. I've introduced zinc rod here. I've introduced zinc rod here. Now this particular electrode has to behave like cathode, and at cathode reduction takes place. So what's going to happen? The zinc ions which are there in the solution, they'll collide with the rod. And when these zinc ions which are there in the solution, when they will collide with the rod, they'll take 2 electrons from the rod, will get converted into zinc solid. Since the zinc ions which are there in the solution, they are colliding with the rod, they are taking 2 electrons from the rod, due to which rod gets which charge? Positive charge. And this zinc solid, it gets deposited on the rod. It gets deposited on the rod, due to which in the solution, can I say the number of zinc dipositive ions will decrease? Earlier, cations and anions were equal in number. Cations and anions were equal in number. Now, what happens? Zinc dipositive number decreased, due to which this particular solution effectively will get which charge? This solution gets effectively negative charge. So rod got positive, solution got negative. So can I say again, potential difference got created between the rod and the solution? And this potential difference that gets created between the rod and the solution, what do we call it as? We call it as electrode potential. What is electrode potential in short? It is nothing but it is the potential difference that gets created between the rod and the solution, right? Now, my dear students, this electrode potential is actually of two types. This electrode potential is actually of two types. One is called as oxidation potential, one is called as reduction potential. One is called as oxidation potential, one is called as reduction potential. Let me tell you, see, over here I made sure that the electrode behaves like anode. And here I made sure that the electrode behaves like cathode. And when electrode behaved as anode, rod got negative, solution got positive. This potential difference is called as electrode potential. And this electrode potential, wherein rod gets negative, solution gets positive, this is called as oxidation potential, right? This electrode potential, wherein rod gets positive, solution gets negative, this electrode potential is called as a reduction potential. This is called as a reduction potential. In general, the potential difference between the rod and the solution is called as electrode potential. Now that electrode potential can be called as oxidation potential or reduction potential, whether the electrode is behaving like anode or the electrode is behaving like cathode, depending on that. Okay, depending on that. So I can say the electrode potential is basically of two types, oxidation potential and reduction potential. Or there is one more way of representing it. How do we represent it? It can be represented like this. E of M gives Mn positive. You can represent it like this as well. E of M gives Mn positive. See, 0 to plus N, 0 to plus N, increase in the oxidation state. Increase in the oxidation state is called as oxidation. Increase in the oxidation state is called as oxidation. So this particular term again represents what? It represents oxidation potential. It represents oxidation potential. Similarly, my dear students, how do we represent the reduction potential? A reduction potential can be represented as E of Mn positive gives M. Mn positive gives N. See, plus N to 0. Plus N to 0. Decrease in the oxidation state. Decrease in the oxidation state is called as the reduction. So this is what I call as reduction potential over here. Am I clear? Am I clear, people? Everyone in the chats? Am I clear? Everyone in the chats, quickly. Yeah? So your electrode potential is basically of two types. One is oxidation potential and one is reduction potential, right? I believe this is clear. Now, my dear students, one more thing. Whenever the electrode potential, whenever the potential difference between the rod and the solution, is measured under standard conditions, whenever the potential difference between the rod and the solution is measured under standard conditions, standard conditions means when pressure is kept as 1 bar, temperature 25 degrees centigrade, concentration 1 molar. These conditions are what you call as standard conditions. And whenever the potential difference between the rod and the solution is measured under standard conditions, at that point of time, you call that potential difference as the standard electrode potential. You call that as the standard electrode potential. So what is electrode potential and what is standard electrode potential? Both are basically the potential differences between the rod and the solution. But one is measured under standard conditions, one is measured under non-standard conditions. Simple, right? And let me tell you, people, the standard electrode potential is again of two types. One is called as standard oxidation potential and one is called as the standard reduction potential. One is called as the standard oxidation potential and one is called as the standard reduction potential. How do we represent the standard oxidation potential? It is represented like this. E naught of M gives Mn positive. This is how you represent it. E naught of M gives Mn positive. So 0 to plus N. 0 to plus N means increase in the oxidation state. Increase in the oxidation state means oxidation. So this is your SOP, standard oxidation potential. Well, you can call it as SOP as well. Now similarly, second one is standard reduction potential, E naught RED, or you can represent it like this, E naught of Mn positive gives N. So you can check it out, plus N to 0, decrease in the oxidation state. Decrease in the oxidation state is called as a reduction. So this particular term represents your standard reduction potential, or you can call it as SRP. You can call it as SRP. Perfect. You can call it as SRP. Now, my dear students, remember, for an element, SOP is always equal to minus times SRP. For an element, SOP is always equal to minus times SRP. For example, what does that mean? That means if I say E naught of zinc gives zinc dye positive, let's say this is equal to, for example, 0.7 volts. Let's say this is equal to 0.7 volts, for example. Okay. That means E naught of zinc dye positive gives zinc. E naught of zinc dye positive gives zinc. It will be minus 0.7 volts. Simple. So whatever is the oxidation potential of an element, you just need to reverse its sign. You'll be getting the reduction potential of the element. That's all. Okay? You'll be getting the reduction potential of the element. I hope all the things are clear till here. Let me tell you, every element has a particular value. Every element has a particular value of SOP and SRP. Every element has a particular value of SOP and SRP, which is calculated. With the help of a reference electrode, Reference electrode can be either calomel electrode or hydrogen electrode, but generally we use the reference electrode as the hydrogen electrode, which is called as standard hydrogen electrode, SHE. So remember, every element will be having a particular value of SOP or SRP, right? And that SOP and SRP of an element is calculated basically with the help of a reference electrode, and that reference electrode is called as the hydrogen electrode. Okay. Now a term came here, hydrogen electrode. Let's try to understand what this hydrogen electrode first of all is. Let's try to understand what this hydrogen electrode exactly is. See, guys. Talk about standard hydrogen electrode. First of all, how the standard hydrogen electrode is measured. So, I mean, how the standard hydrogen electrode is formed. How the standard hydrogen electrode is formed. Understand, guys. For example, here I am taking a container, and this container is completely filled with H positive ions. Let me tell you, the concentration of H positive here is 1 molar. The concentration of H positive here in the container is 1 molar. Okay. Now, what exactly am I doing? I'm taking an inverted U-type tube like this. In this inverted U-type tube, I'm keeping a platinum wire. And this platinum wire, it is coated with platinum black. This platinum wire is coated with platinum black. Okay. Now, here I'm introducing H2 gas. I'm introducing H2 gas at a pressure of 1 atm or 1 bar. I'm introducing H2 gas at a pressure of 1 atm or 1 bar. Now, what happens exactly? This platinum, when hydrogen gas is introduced, the hydrogen gas molecules, they get adsorbed on the surface of this platinum. Right? They get adsorbed on the surface of the platinum. So now, tell me just one thing. If this is the platinum wire, hydrogen gas is introduced, right? The hydrogen molecules are adsorbed on the surface of the platinum. due to which all the surface of the platinum got covered with what? It got covered with hydrogen gas. All the surface, entire surface of this platinum rod got covered with hydrogen gas. Now, as if you have got a hydrogen rod and you have introduced it in a solution containing O ions. Whenever you have a rod, and that rod is introduced in a solution containing its own ions. Whenever you have a rod and that rod is introduced in a solution containing its own ions, what do you get out of it? You get electrode. So you have got now the hydrogen rod, which is introduced in a solution containing its own ions. So this particular setup I'll be calling as electrode. And which electrode is it? It is the hydrogen electrode. Perfect. Have I used the standard conditions? Absolutely, I've used the standard conditions. I've kept concentration as 1 molar. I've kept pressure as 1 bar. And let me keep temperature as 25 degrees centigrade. So this hydrogen electrode under standard conditions would be called as the standard hydrogen electrode. Now, my dear students, this hydrogen electrode over here, it can behave like anode as well as cathode. And let me tell you, when hydrogen electrode behaves like anode, oxidation takes place. What reaction happens at that time? Remember, at that time, H2 gas gets converted into 2 times H positive aqueous plus 2 electrons. This is the reaction which takes place when hydrogen electrode behaves like the anode. Okay. Now, the same hydrogen electrode, it can behave like cathode as well. And when the hydrogen electrode behaves as the cathode, reduction takes place. Reduction means gain of electrons. Now, reverse the same reaction. If you reverse the same reaction, it's going to be 2 times H positive aqueous plus 2 electrons. Gives what? Gives H2 gas. This is the reaction which is going to happen when the hydrogen electrode behaves like anode. This is the reaction which is going to happen when hydrogen electrode behaves like the cathode. My dear students, irrespective of the fact whether hydrogen electrode behaves like anode or cathode, remember the SOP and SRP of hydrogen electrode is taken as 0. Since it is a reference electrode. With the help of which we calculate the SOPs and SRPs of different elements, right? So we consider, irrespective of the fact whether the hydrogen electrode behaves like anode or cathode, it's SOP or SRP. Both are taken as how much? Both are taken as 0. Okay? Am I clear? Guys? Am I clear? So remember, your hydrogen electrode is a reference electrode. And let me tell you whether hydrogen electrode behaves like the anode or it behaves like the cathode, it's SOP as well as SRP. Both are taken as 0. SOP means standard oxidation potential, SRP means standard reduction potential. Okay? Now, guys, understand. What is the significance of this SOP and SRP? What is the significance? What kind of questions can be framed? See, guys, understand just 2 points. Remember them. You'll be able to solve each and every question. Just 2 points. First of all, SOP of an element gives us the idea about the tendency of an element to undergo oxidation. SOP of an element gives the tendency of an element to undergo what? To undergo oxidation. Okay? And SRP of an element gives the tendency of an element to undergo reduction. Now, what does it mean? Have a look. Remember, more the SOP of an element, more is the tendency of an element to undergo oxidation. More is the tendency of an element to undergo oxidation. My dear students, the one that undergoes oxidation is called as reducing agent. The one that undergoes oxidation is called as reducing agent. And more the SOP, more the tendency to undergo oxidation, it means better will be the reducing agent. And the one which is the better reducing agent, remember, its reducing power will be more. Its reducing power will be more. Remember this particular statement. More the SOP, more the tendency of an element to undergo oxidation, better the reducing agent, more the reducing power. Okay? Perfect. Am I clear, guys? Now, one more point. More the SRP of an element. More the SRP of an element. More is the tendency of an element to undergo reduction. More is the tendency of an element to undergo reduction. The one that undergoes reduction is called as oxidizing agent. That to a better oxidizing agent. The one that has got more tendency to undergo reduction, that is the better oxidizing agent. And the one that is the better oxidizing agent will be having more oxidizing power. Just these two statements and we are done. Just these two statements and we are done. More the SOP of an element, more is the tendency to undergo oxidation. More the SOP of an element, more is the tendency to undergo oxidation, better the reducing agent, more the reducing power. More the SRP, more the tendency to undergo reduction, better the oxidizing agent, more the oxidizing power. Just these two things and we are sorted. See how we are sorted. For example, here I'm writing element. Here I'm writing element. Element A, element B, element C, element D. So 4 elements I've taken, right? Let's say I'm giving you some arbitrary values. I'm writing E of M gives Mn positive. E of M gives Mn positive. So first of all, tell me, is this SOP or SRP? Is this SOP or SRP? Look at it carefully. 0 to plus N, increase. Increase means oxidation. Oxidation means SOP. So this SOP. Let's say the SOP of this A is 1 volt. SOP of B is 2 volt. This is 3 volt. This is 4 volt. Okay. Now, which one has got more SOP? Which one has got more SOP? Which one has got more SOP? The last one. The one that has more SOP, that will have more tendency to undergo oxidation. So this will have more tendency to undergo oxidation. The one that has got more tendency to undergo oxidation is the better reducing agent. So this is the better reducing agent. I would say its reducing power would be more. Its reducing power would be more. Okay? Its reducing power would be more. Now similarly, guys, for example, I am writing E naught of M gives Mn positive. Now the value I'm keeping as minus 1 volt, minus 2 volt, minus 3 volt, minus 4 volt. Is this SOP or SRP? This is again SOP. Now which one has got more SOP? This one has got more SOP. This is the more SOP value. More the SOP, more the tendency to undergo oxidation, better the reducing agent, more the reducing power. Okay. For example, I'm writing E naught of Mn positive gives M. Okay. This for example 1 volt, this is 2 volt, this is 3 volt, this is 4 volt. Now, is this SOP or SRP? Just tell me that. Plus N to 0. Plus N to 0. Decrease. Decrease means reduction. Plus N to 0. Decrease. Decrease means reduction. Decrease means reduction. So this is SRP. So which one has maximum SRP? This has maximum SRP. The one that has got maximum SRP, that will undergo reduction easily. So it's going to be a better oxidizing agent. So its oxidizing power will be more. Perfect. This is how we compare things here. Similarly, guys, if you look carefully, if I write E naught of Mn positive gives M. So this is minus 1 volt, this is minus 2 volt, this is minus 3 volt, this is minus 4 volt, right? So this is again SRP. Now, which one has got more SRP? This is the more SRP value. More the SRP value, more the tendency to undergo reduction, better oxidizing agent, more oxidizing power. Clear? So this is how you compare oxidizing agents, reducing agents, oxidizing powers, and reducing powers. If I'm clear, let me know once in the chats. Quickly. Quickly, guys. Okay. I believe this is clear. And if this is clear, guys, if this is clear, just give me the answer of this question. Yeah, this question. What do you think will be the answer of this question? Usab, I have no idea what will be the duration of this chapter. I'm teaching. I don't know when it'll get over. It's a big chapter, so yeah, it will take time. Can you tell me what is going to be the answer of this question? What is going to be the answer of this particular question, guys? Quick. See, how do we exactly check it? Try to understand and remember once for all, okay? Remember once for all. How do we check it? What is happening in this reaction? Loss or gain? Gain of electrons is happening. Gain of electrons means reduction. So these are basically SRP values. These are basically SRP values. Now tell me which one is undergoing reduction? Mg dipositive or Mg? Mg dipositive or Mg? Tell me that. I'm telling you the tricks to do these sort of questions. Which one is undergoing reduction? Mg dipositive or Mg? The one that gains electrons, that is undergoing reduction. So this is the SRP of Mg dipositive. So this is the SRP of ion. This is the SRP of ions. This is the SRP of ions. Now if I reverse these reactions, the above reaction becomes Mg gives Mg dipositive plus 2 electrons. Right? So now, is it reduction reaction or oxidation reaction? Tell me. Is it reduction reaction or oxidation reaction? Tell me that. It's oxidation reaction, right? Because here in this particular reaction, loss of electrons is happening. Loss of electrons means oxidation. So it's oxidation. Oxidation of what? Who is losing electrons? Magnesium is losing electrons now, right? Magnesium is losing electrons. So what I need to do, if you have reversed the reaction, change its sign. It's going to be E naught is equal to plus 2.37 now. But now it is not, earlier it was SRP, now it is SOP. But this is the SOP of what? SOP of that species which is undergoing oxidation. What is undergoing oxidation? Magnesium. So this is the SOP of metal. This is the SOP of metal. Correct? Similarly, the SOP of zinc, SOP of metal will be plus 0.76. SOP of nickel will be plus 0.73. SOP of iron will be plus 0.04 volts. Right? Now, how do I check it? Sir, sky क्यों छोड़ा? हता मैं क्या थ्रो sky by that issues परनावा. Issues तैते परनावा. क्या थ्रो? पान एक सही करा. Clear? I hope everything is clear till here. Now, what do we have to check? Strongest reducing agent, right? What do we have to check? Guys, this was Kashmiri, okay? This was Kashmiri. We have to check which of the following is the strongest reducing agent. Now tell me one thing. A reducing agent, if I talk about the reducing agent undergoes what? Oxidation. Reducing agent undergoes oxidation. Okay. I would say the one that undergoes oxidation easily is the better reducing agent. Now, which one undergoes oxidation easily? The one that has got more SOP. The one that has got more SOP. So, which one is the maximum SOP among all? Maximum SOP value among all is plus 2.37, which is the SOP of magnesium, right? So, more the SOP, more the tendency to undergo oxidation, better the reducing agent. So, the answer is going to be B, it's magnesium. Okay? I believe it's clear. I believe this is clear. Okay, can you tell me the answer of this question? We have to give the order of what? We have to give the order of oxidizing power. Or guys, you can just remember it like this as well, okay? You can remember it like this as well. Reducing power is directly proportional to SOP. Reducing power or reducing agent directly proportional to SOP, okay? Oxidizing power or oxidizing agent directly proportional to SRP. You can remember it simply like this as well. Now, if you look at this particular question, in this particular question, we have to check the oxidizing power. We have to check the oxidizing power. So, oxidizing power, as I told you, is directly proportional to what? SRP. Is directly proportional to SRP. So, am I given with SRPs only? I'm given with SRPs only. I'm given with SRPs only. So, which one has got maximum SRP value? There is this or this. This is the maximum SRP. This is the maximum SRP value, right? So, this is the SRP of the one which is undergoing reduction. SRP means standard reduction potential. So, this is the SRP of one which is undergoing reduction. And cobalt tripositive is undergoing reduction. So, cobalt tripositive has got the maximum SRP. After cobalt tripositive, which one to prioritize? It is plus 1.67. So, PB plus 4. PB plus 4. So, it's option B. That's going to be the correct answer of the question. Okay? I hope this sort of a question you can do on your own. Tell me, reducing power order. Few minutes back I told you reducing power is directly proportional to SOP. But is this SOP or SRP? Everywhere gain of electrons is happening. Gain means reduction. So these are SRP values. SRP values of what? SRP of the ones which undergo reduction. Here zinc dipositive undergoes reduction. Calcium dipositive. So these are the SRP values of ions. But I need SOP values. So reverse the sign. So it's plus 0.76. It will be plus 2.87. This will be plus 2.36. This will be plus 0.25. Now this is SOP, but SOP of what? SOP of metals. SOP of metals. Tell me which metal has got more SOP? Which is the maximum SOP value? Plus 2.87. That is the SOP of calcium. So calcium will be having maximum SOP means more reducing power. So calcium. After calcium, it's going to be? After calcium, it's going to be your magnesium. It's going to be magnesium. So option B again. Right? Perfect. So it's option B. That's going to be the correct answer of this particular question. I hope this is clear. Now guys, let's talk about one more term, that is EMF. Let's talk about one more term, that's EMF. Electromotive force. What is EMF exactly? First of all, what does a galvanic cell do? If I ask you a general question, what does a galvanic cell do? A galvanic cell produces current. Right? Galvanic cell, it produces current. It converts chemical energy into electrical energy. Right? It produces current. My dear students, current flows due to what? Current flows due to potential difference. Current flows due to what? See, the work of the galvanic cell is to produce current. And we know current flows due to potential difference. Current flows due to potential difference. We know that. We know that. Current flows due to potential difference. Now the point is, if you talk about your galvanic cell, in the galvanic cell there are two electrodes. There are two electrodes connected externally as well as internally. Now this galvanic cell is producing current. So there must be potential difference between the electrodes, because of which the galvanic cell produces current. There must be potential difference between the electrodes. There must be potential difference between the two electrodes, due to which this galvanic cell produces current. Now, the maximum potential difference the maximum potential difference between the electrodes. The maximum potential difference between the electrodes when the cell is not in use. The maximum potential difference between the electrodes when the cell is not in use is what you call as EMF. Is what you call as EMF. And this EMF is represented by what? EMF is represented by E cell. And let me tell you, when this EMF is calculated under standard conditions, when this EMF is calculated under standard conditions, you call it as standard EMF for the cell, E0 cell. You call this as a standard EMF for the cell, E0 cell. And how do we calculate this E0 cell? How do we calculate this E0 cell? E0 cell is calculated as E0 cathode minus E0 anode. What is E0 cathode? E0 cathode is called as SRP of cathode. E0 anode is called as SRP of anode. SRP of cathode minus SRP of anode. Remember it in short. Okay? Remember in it short. So basically, when you talk about the galvanic cell, the work of the galvanic cell is to produce current. And we know current flows because of what? Current flows because of potential difference. The maximum potential difference between the electrodes when the cell is not in use, you call the potential difference as, you call that potential difference as the EMF. And when EMF is measured under standard conditions, when EMF is calculated under standard conditions, you call it as the standard EMF. And standard EMF is calculated as E0 cell minus, E0 cathode minus E0 anode. So this is your SRP of cathode, this is your SRP of anode. Okay? I believe this is clear. Now guys, try to understand what exactly am I going to do. Try to understand very carefully. I'm going to tell you something good, which will make your question solving comparatively easier. For example, I'm writing two things here. I'm writing E0 of A dye positive gives A is equal to 2 volt. Here I'm writing E0 of B plus gives B is equal to 3 volts. Can you tell me how many electrodes I took here? How many electrodes I took here? Tell me that. I took 2 electrodes. I took 2 electrodes. For example, if I connect these electrodes externally as well as internally, if I connect these electrodes externally as well as internally, can I say I'll be getting a galvanic cell? I will be getting a galvanic cell, right? Now the galvanic cell which I got, I want to calculate its E0 cell. And E0 cell is nothing but E0 cathode minus E0 anode. Now which one is cathode and which one is anode here? Which one is cathode and which one is anode here? Tell me one thing. Is this SOP or SRP? Plus 2 to 0, decrease, reduction. So this SRP. Plus 1 to 0, decrease, reduction, SRP. So both are SRP values. Which one has got more SRP? Where do you see more SRP? Can I say SRP is more here? More the SRP, more the tendency to undergo reduction. More the SRP, more the tendency to undergo reduction. And reduction takes place at cathode. So this is going to be your cathode and this is going to be your anode. If you identified your cathode and anode, so I'll be writing E0 cathode, SRP of cathode. SRP of cathode is 3 volt minus SRP of anode is 2 volt. So 3 minus 2 comes out to be 1 volt. So this is the E0 cell. This is the E0 cell of the cell which we generated here. Got it? Similarly, for example, let me take one more case. Let's say I'm writing E0 of A gives A dye positive. It is equal to 3 volt. Similarly, E0 of B gives B negative. It's equal to 5 volt. Now what am I doing? I've got 2 electrodes. Again, I'm connecting them externally. I'm connecting them internally. So I'll be getting a complete cell. Got complete cell, right? Now I want to calculate the E0 cell of this complete cell. The standard EMF of the complete cell. Basically, I want to calculate the maximum potential difference between these 2 electrodes. I want to calculate the maximum potential difference between these 2 electrodes when the cell is not in use. So what do we do? E0 cell is equal. You know, it is E0 cathode minus E0 anode. Now, first of all, I need to check which one is cathode and which one is anode. I need to check which one is cathode and which one is anode. How do we check? 0 to plus 2. 0 to plus 2 means increase. Increase means oxidation. So this SOP. 0 to minus 1. 0 to minus 1. Decrease. Decrease means reduction. So this SRP. So if this is SOP, that means its SRP will be minus 3 volt. Its SRP will be minus 3 volt. Its SRP will be minus 3 volt. Now which SRP is more here? This value is more. More the SRP. More the tendency to undergo reduction. And reduction takes place at cathode. So this is your cathode. Automatically this becomes your anode, right? So E naught cathode, SRP of cathode. SRP of cathode is how much? 5 volt. Minus SRP of anode. SRP of anode is minus 3 volt. Value comes out to be 8 volt. So 8 volt is the E naught cell. Am I clear, guys? Am I clear? Everyone in the chats? Am I clear? If this is clear, tell me the answer of this particular question. Give it a try. Give it a try, guys. If you look at this particular question, we are supposed to calculate EMF of this particular cell. EMF of this cell. You know, EMF of the cell is nothing but that is E naught cathode minus E naught anode. So first of all, I should know which one is cathode and which one is anode. I should know which one is cathode and which one is anode. Look carefully. 0 to plus 2, oxidation. 0 to plus 2, increase. Increase means oxidation. Oxidation takes place at anode. So this zinc is your anode, iron is your cathode. Understood? Now, iron is your cathode. Iron is your cathode, right? So, E naught cathode means SRP of cathode. SRP of cathode. That means SRP of iron. SRP of iron. Well, this is SOP which is given. This is SOP, loss of electrons. Loss of electrons means oxidation. Oxidation means this is SOP. This is also SOP. What do I need? I need SRP. SRP of cathode, SRP of iron. SRP of iron will be minus 0.41. Minus E naught anode, SRP of anode. That means SRP of zinc. This is SOP of zinc. I need SRP of zinc. So minus 0.76. Value comes out to be plus 0.35 volt. So this is the E naught cell. Perfectly done. Perfectly done, guys. Quick, everyone. Quickly in the chats. Yeah? If this is clear, let me tell you one more important thing. What is that? A relation between delta G and E cell. A relation between delta G and E cell. I'm not going to derive the relation. I'll give you the relation and we'll see its significance. We'll see its significance. First of all, the relation is, you know, delta G is equal to minus NF E cell. Delta G is equal to minus NF E cell. And if you write the same equation under standard conditions, if I write the same equation under standard conditions, so how do I write it then? Then it's going to be delta G naught is equal to minus NF E naught cell. Minus NF E naught cell under standard conditions. Now, why do we need this particular equation? What is the need of it? What is the need of it? See, guys, pretty much simple. Tell me one thing. A galvanic cell is made up of 2 electrodes. A galvanic cell is made up of 2 electrodes, right? For example, I'm giving you any 2 electrodes. I'm giving you any 2 electrodes. Electrode number 1, electrode number 2. I gave you 2 electrodes. I want you to connect these electrodes externally as well as internally. I gave you 2 electrodes. You connected these 2 electrodes externally as well as internally. When you connected these electrodes externally as well as internally, you got complete cell. You got a complete cell, right? Now the point is, no doubt you got the complete cell. But whether that complete cell will be working or not, whether that complete cell will produce current or not, that depends on this particular topic. That depends on delta G of the cell. That depends on delta G of the cell. See what happens. When you take 2 electrodes, when you connect them externally and internally, if at anode, oxidation takes place on its own, if reduction takes place on its own, then only there will be movement of electrons from anode to cathode. Then there will be direction of current from cathode to anode. So can I say, for the cell to be working, for the cell to produce current, can I say cell reactions must be spontaneous? Can I say something like that? Cell reaction must be spontaneous. What does that mean? That means when you connect the 2 electrodes externally, internally, spontaneously at anode oxidation should happen, at cathode reduction should happen, then only there will be movement of electrons, then there will be, movement of current. Perfect? So for the cell to be working, let me write it like this. If let me write it like this. For the cell to be working, comma, cell reactions must be spontaneous. Cell reactions must be spontaneous. For the cell to be working, cell reactions must be spontaneous. And for any process to be spontaneous, delta G value should be negative. So for the cell reactions to be spontaneous, I would say delta G for the reaction. Delta G for the reaction should be negative. Because when delta G is negative, then only we say the process is spontaneous. Okay, so delta G technically should be negative. Delta G negative means, delta G for the reaction negative means delta G is nothing but minus NF E cell. So minus NF E cell, this value should be negative. Now the point is, when can this value be negative? This value can come out to be negative only. This value can come out to be negative only if E cell is positive. Then only positive negative makes it negative, right? So I would say E cell should be positive. So I got two things here. I would say for any cell to be working, either you should say delta G for the reaction should be negative, or you should say E cell should be positive. Okay, correct? Now similarly guys, similarly. For example, if delta G for the cell reaction is positive, delta G is positive. When can be delta G positive? Delta G can be positive if this particular term comes out to be positive. This particular term comes out to be positive only if E cell is negative. If E cell is negative, negative comes out positive, right? Perfect. So if delta G is positive, that means E cell would be negative. Now the point is, if delta G is positive, would the cell reactions be spontaneous or non-spontaneous? I'll say reactions would be non-spontaneous. Reactions would be non-spontaneous. And if the reactions are non-spontaneous, will the cell produce any current? Will the cell work? I would say directly cell does not work. Cell does not work. Okay. Now, the third point. If delta G for the reactions will be equal to 0, delta G 0 means minus NF E cell 0. When can be minus NF E cell 0? It is only possible if E cell value is 0. E cell 0 means there is no potential difference between the electrodes. If there is no potential difference between the electrodes, there would be no current, right? There would be no current. So, no current. Cell does not work. I mean, or I should say directly, cell does not produce any current. Cell does not produce current. And this particular state in the cell, when delta G becomes 0, when E cell becomes 0, we call this particular condition as the equilibrium condition in the cell. This is something which I'll be discussing later on in detail. Right now, you can just remember it. When delta G is equal to 0, E cell is equal to 0, right? And I would say the cell does not produce any current at that point of time, or I can say the cell is at equilibrium. All right. So basically, this particular topic is telling you that telling us that if you are given with a cell, if you want to check whether the cell will be working or not, if you want to check whether the cell will produce current or not, then you have to check the value of, you have to check the value of delta G or E cell. If delta G is negative, E cell is positive. That means the cell will be working. If delta G is positive, E cell is negative. Cell does not work. Delta G 0, E cell 0. Cell is at equilibrium. Simple. Okay. Now, there are two more things which I would want to tell you here. What is that? Remember, delta G is an extensive property. And E is the intensive property. Extensive properties can be added or subtracted directly. Extensive properties can be added or subtracted directly. Whereas intensive properties cannot be added or subtracted directly. Extensive properties can be added or subtracted directly. Intensive properties cannot be added or subtracted directly. There is a question which is asked from it. Let's have a look on that question. You are given with 3 reactions. Fe tri positive plus 3 electrons gives Fe solid. Fe di positive plus 2 electrons gives Fe solid. Fe tri positive plus 1 electron gives Fe di positive. E1 is given, E2 is given, we need to calculate E3. That is the question. We need to calculate E3. Whenever you see such kind of the question, whenever you see such kind of the question, whenever you see such kind of the question, wherein you have to calculate the value of E3, for example, how do we solve it? My dear students, that particular reaction whose E value is to be calculated, that particular reaction whose E value is to be calculated, you are supposed to make that reaction out of those reactions whose E value is given. That particular reaction whose E value is to be calculated, you are supposed to make that reaction out of those reactions whose E value would be given to us. Whose E value would be given to us. Now understand. Now understand. How do I make this equation number 3 from 1 and 2? From 1 and 2, how do I make equation number 3? If I do one thing, if I subtract second from first, I'll be getting Fe tri positive plus 3 electrons minus Fe di positive minus 2 electrons gives Fe solid nothing. On this side there is nothing, right? So I can write Fe tri positive 3 electrons minus 2 electrons is 1 electron. Take this minus Fe di positive on that side, it becomes Fe plus 2, right? So do you see? I made the reaction. I made the reaction. Look at these two reactions. I made the reaction. How did I make this particular reaction? I made this particular reaction. This third reaction I made when I subtracted second from first. When I subtracted second from first. Okay? When I subtracted second from first. Now if you think, the operation which you did to the reactions, if you think you are going to do the same operation with their E values. If you think instead of 3 you'll write E3, instead of 1 you'll write E1, instead of 2 you'll write E2, the answer is going to be a big no. Why is that? Because this E, it is intensive. If E is intensive, you cannot add or subtract intensive properties directly. You cannot add or subtract intensive properties directly, but you can add or subtract extensive properties directly. So that means this question will be solved not in terms of E. This question will be solved in terms of delta G, which is the extensive property. So I can say instead of 3, I'll write delta G3. Instead of 1, I'll write delta G1. Instead of 2, I'll write delta G2. Now, delta G is equal to minus NF E cell. So delta G3 is minus N3F E3 is equal. This would be minus N1F E1. Minus 1 becomes plus N2F E2. So first of all, F cancels out. F everywhere cancels out. Now, if I multiply throughout with minus sign, it becomes N3 E3 is equal to N1 E1 minus N2 E2. So what I can do here is, I can write E3. E3 is N1 E1 minus N2 E2 divided by N3. Divided by N3. So first of all, what is N1, what is N2, and what is N3? N1 value is 3. N2 value is 2. N3 value is 1. This is N1, this is N2, this is N3. E1, E2 is also given. This is E1, this is E2. N1, N2, N3 is given. E1, E2 is also given. Put the values, get the answer. That's it. Yeah? Perfect. I hope this is clear. The similar sort of question I'm writing again. I'm giving you again. This is the question. MnO4 negative. MnO4 negative gives us what? Gives MnO4 di negative. Its E1 value is equal to 1 volt. Second, MnO4 di negative gives MnO2. And its E2 value is how much? Its E2 value is 2 volt. Third reaction. MnO2 gives Mn di positive. Its E3 will be equal to 3 volt. Okay. And the last reaction. MnO4 negative gives Mn di positive. Its E4 is to be calculated. Its E4 is to be calculated. How do we solve this sort of equation? How do we solve this sort of equation? Just understand. Just understand. What is the oxidation state of manganese here? When you calculate, it's plus 7. Here, it's going to be plus 6. Plus 7 to plus 6. Decrease. Decrease means reduction, gain of electrons. So I would say MnO4 negative is gaining 1 electron, getting converted into MnO4 dinegative. Similarly, this is plus 6, this is plus 4. Plus 6 to plus 4, decrease, reduction, gain of electrons. So 2. So plus 4 to plus 2, plus 4 to plus 2, again 2 electrons. Right? Plus 7 to plus 2, plus 7 to plus 2, 5 electrons. So basically, this is the reaction for which I need to calculate E. This is the reaction for which I need to calculate E. Now the reaction for which I need to calculate E, I'm supposed to make that reaction out of those reactions whose E is given. Basically, I'm supposed to make this fourth reaction out of first, second, and third. I'm supposed to make fourth reaction out of first, second, and third. Do you understand? I'm supposed to make fourth reaction out of 1, 2, and 3. Yeah? Because the reaction whose E value is to be calculated, you are supposed to make that reaction out of those reactions whose E value is given. Now, how do we make this reaction, guys? Just think about it. How do we make this reaction? Simple. When I add these three, 2 plus 2 plus 1, that means 5, right? MnO4 dinegative cancels out. MnO2 cancels out. So if I'm adding 1, 2, and 3, I'm getting the fourth one, right? So fourth equation I'm getting only when I'm adding 1, 2, and 3. Now, whatever operation I'm doing with the reactions, am I supposed to do the same operation with their E values? No. I'm not supposed to do the same operation with their E values. I'm supposed to do the same operation with their delta G values. So this would be delta G4, this would be delta G1, this would be delta G2, this would be delta G3. Now, you know, delta G4 is minus N4 FE4 is equal to, this would be minus N1 FE1, this would be minus N2 FE2, this would be minus N3 FE3. So F everywhere cancels out, multiply throughout with minus sign. Finally, you'll be getting E4 is equal to N1 E1 plus N2 E2 plus N3 E3 divided by, this is going to be N4. Now tell me, N1, N2, N3, N4. Do we already know? This is N1, this is N2, this is N3, this is N4. I already know. N1 value is 1, N2 is 2, this is 2, this is 5. N1, N2, N3, N4. We already know. Do we know the values of E1, E2, E3 as well? E1, E2, E3 is also given. So all the parameters are given. Put it here and get the value of E4, which I was supposed to calculate. I believe I'm clear with this. Did you understand, people? Everyone in the chats? Everyone in the chats, quick, quick, quick. Done? Done, guys? Okay, if this is done, then let's do one thing. Let's talk about your Nernst equation. Let's talk about your Nernst equation. First of all, how do we get the Nernst equation? How do we get the Nernst equation? My dear students, first of all, I'm writing one equation from thermodynamics. Delta G is equal to delta G naught plus RT ln of QC. This is one of the equation from the chapter thermodynamics, which I'm using. Now, first of all, delta G is nothing but minus NF E cell. Delta G naught would be minus NF E naught cell, right? Minus RT ln of QC. Correct? Let's do one thing. Let's divide throughout with minus NF. Let's divide throughout with minus NF. Okay, it gets cancelled out, so I'll be left with E cell is equal to, this is going to be E naught cell minus RT divided by NF is going to be ln of QC. So I can write it like this: E cell is equal to E naught cell minus, this is going to be 2.303 RT divided by NF, then it's going to be log of QC. It's going to be log of QC. This is the general form of your Nernst equation. This is how your actual Nernst equation looks like. E cell is equal to E naught cell minus 2.303 RT divided by NF log of QC. Now, my dear students, if I take the value of R exactly as 8.314 joules per Kelvin per mole, if I keep the value of temperature as 25 degrees centigrade, which means 298 Kelvin, if I take the value of F, F stands for Faraday's constant, whose value is 96500 coulombs. If I put all these three values into this particular equation, what do I get? I get a final equation like this. E cell is equal to E naught cell minus 0.0591 divided by N, and then it's going to be log of QC. This is how your Nernst equation looks like. Am I clear to everyone? Now, my dear students, this Nernst equation, where all do I use it? See, where all do I use it? First of all, I can use this Nernst equation to calculate oxidation potential of an electrode. Electrode means half cell. Whether you can write electrode or you can write half cell, it is one of the same thing. Electrode or half cell. This Nernst equation is used to calculate the oxidation potential of the electrode at non-standard conditions. How do we calculate oxidation potential of the electrode under non-standard conditions? With the help of Nernst equation. And how do I write Nernst equation at that point of time? Instead of E cell, I write EOX, which stands for oxidation potential. Instead of E naught cell, I write E naught OX. This is SOP, standard oxidation potential, minus 0.0591 divided by N, log of QC. When do I use this particular equation? This particular equation I'll use only if I need to calculate oxidation potential of the half cell, oxidation potential of the electrode under non-standard conditions. Now, if I need to calculate the reduction potential of the half cell, reduction potential of the electrode under non-standard conditions. How do I calculate reduction potential of the electrode under non-standard conditions with the help of this particular equation? The equation is going to be simply like this. Instead of E cell, you write ERED is equal. This is going to be E naught RED minus 0.0591 divided by N, log of QC. This is the equation which I'll be using to calculate a reduction potential of the half cell, reduction potential of the electrode under non-standard condition. And this equation as it is used to calculate the EMF. The EMF of the complete cell. Complete cell is made up of two half cells, two electrodes. EMF of the complete cell under non-standard condition. Perfect. My dear students, Nernst equation I can directly use to calculate oxidation potential of the electrode under non-standard conditions, reduction potential of the electrode under non-standard conditions, EMF of a complete cell under non-standard conditions. Now, one by one, we are going to see its application part. So first of all, tell me if all the things still here are clear or not. Tell me if all the things still here are clear or not. Everyone. Yeah? Now, I think let's take a small break. Yeah, the last break we took at 4. At 4 we started, 4 to 6, yeah. Let's take a small break and get back and then see the variety of the questions that could be asked from this Nernst equation. Okay. So, break till The time is almost 6. Let me keep it as 6:30. You can have your tea, freshen up, but be back on time, every one of you. Be back on time. Okay? Be back on time. We'll see you. Bye-bye. Be back on time, guys. Is everyone back? Is everyone back? Yes. All right. So guys, whatever things we discussed till now. Whatever things we discussed till now, is every single thing clear? Tell me quickly in the chats. Tell me quickly in the chats, everyone. Sir, we are from Tamil Nadu watching. I mean, 6 people are watching from one laptop. Good, good, good. Nice. Keep going. Keep studying. That's great. 11th physical chemistry will be also done. It will be also done. All right, guys. Let's move on then, huh? Let's move on. Let's move on. Let's move on. Let's move on. Okay, so we are done with the Nernst equation, right? Now it's going to be the time to see the application of this Nernst equation. Let's see what all kinds of the questions can be solved from the Nernst equation. Okay, what all types of the questions are there. See guys, before showing you the types of the questions and stuff, before showing you the types of the questions and stuff, I would want you guys to take a note of one simple statement. Take a note of one simple statement. My dear students, the reduction potential of the half cell means electrode, reduction potential of the half cell, reduction potential of the electrode. Remember, it is directly proportional to the concentration of electrolyte. It is directly proportional to the concentration of electrolyte present in the container. And similarly, oxidation potential of the half cell. It is inversely proportional to concentration of electrolyte present in the container. What does it mean? See, it has got derivation also through Nernst equation, but I'm not going there. I'm just telling you the conclusion which is needed to us. See what it means exactly. For example, here I'm taking a container and this particular container contains zinc sulfate. For example, let's say the concentration of zinc sulfate here is 10 molar. Okay, and here you have got the zinc rod. So this is one of the zinc electrodes here. Similarly, over here, again, I'm taking zinc sulfate only. But the concentration of zinc sulfate, for example, is 100 molar here. Okay, and here you are again introducing zinc rod only. So basically, you have got 2 zinc electrodes. Basically, you have got 2 zinc electrodes, as you can see. Okay. Now, as per this particular statement, more the concentration of electrolyte in the container, more is going to be the reduction potential of the electrode. No doubt this is the zinc electrode. Again, this is the zinc electrode. But this zinc electrode will be having more reduction potential. This will have comparatively less reduction potential. So wherever you see the concentration of electrolyte more, remember, in that particular case, the reduction potential is going to be more. Remember this particular thing. This concept I'll be using in some time when I'll be teaching you Nernst equation at equilibrium. Okay. Now, Let's first of all see what kind of questions can be framed from the Nernst equation and how they are solved. For example, this is the simple question. Understand what I'll be doing in order to solve this question. Calculate the oxidation potential of the half cell. We are supposed to calculate oxidation potential of the half cell. How do we exactly calculate oxidation potential of the half cell? Try to understand, guys. First of all, this is the half cell that is given to me. Over here, the oxidation state of iron is 0. Right here, the oxidation state of iron will be +2. Right? Now, since we are supposed to calculate the oxidation potential of this half cell, in order to calculate oxidation potential, I'll make sure that the electrode behaves like anode. Because at anode only, oxidation takes place. So, if this electrode behaves like anode, what is going to happen? Oxidation will take place. Oxidation means loss of electrons. I would say Fe solid will get converted into Fe dye positive aqueous, and with that you'll write 2 electrons. Okay, this is the reaction which is going to happen when this particular electrode behaves like anode. Okay, how many electrons do you see here? 2 electrons. So first of all, the value of N is 2. If I ask you to write the QC expression, in order to write the QC expression, we always start with the product. So I'll simply write concentration of Fe dye positive raised by stoichiometric coefficient divided by, this is in solid form, its active mass is 1, nothing to do with that. Okay. Now, as per the question, what is the concentration of Fe dye positive? Concentration of Fe dye positive is given to me as 0.1 molar, which means 10 raised power minus 1. So this is the QC value, this is the N value. Now, simple, you guys are going to use the Nernst equation, and Nernst equation says that oxidation potential of the half cell is equal to A0OX, standard oxidation potential, minus 0.0591 divided by N, and it's going to be log of QC. Now, you just need to put the values. I'll say oxidation potential of the half cell is equal to E0OX is basically SOP, standard oxidation potential. Look at this particular thing. This is +2 to 0. +2 to 0. Decrease in the oxidation state. Decrease means reduction. So this is basically your SRP. This is basically your SRP. What do I need? But I need SOP. I need SOP. Okay. So I just need to reverse the sign. It's going to be 0.44 minus 0.0591 divided by N value is how much? N value is 2 and log of QC. QC value is 10 raised per minus 1. Okay. So this is 0.44 minus 0.0591 divided by 2 log of M raised per N, which is N log M. So minus 1 comes to the front, log 10 is 1. Just solve this particular term and get the oxidation potential of the half cell, which you were supposed to calculate. Right? Simple. I believe this particular question is done. Look at this particular question, guys. Again, we are given the half cell. If you look carefully, this is H2 gas, gives this basically H positive here. This HCl means H positive. Right? So, if you look carefully, I would say this is your hydrogen electrode. Hydrogen rod is introduced in a solution containing H positive ions. This is your hydrogen electrode basically. Yeah? This is your hydrogen electrode. Now, we have to calculate what? Oxidation potential of the hydrogen electrode. In order to calculate oxidation potential of the hydrogen electrode, I'll make sure that this electrode behaves like anode. And when hydrogen electrode behaves like anode, I've already given you the reaction. The reaction will be H2 gas gives 2 times H positive aqueous, and with that you'll be writing 2 electrons. This is the reaction which takes place when hydrogen electrode behaves like anode. Now, how many electrons do you see here? 2 electrons. So the value of N is 2. If you want to write the QC expression, QC is going to be concentration of H positive raised by stoichiometric coefficient divided by, this is pressure of H2 gas because it's in gaseous state. What is the concentration of H positive here? 0.1 molar, which means 10 raised power minus 1 raised power 2 divided by partial pressure of H2 is again 10. So the value comes out to be 10 raised power minus 3. So you got QC, you got N. Now, my dear students, use the Nernst equation. I'll write EOX, oxidation potential, is equal to E0OX minus 0.0591 divided by N. That is going to be log of QC. Now, you know, when it comes to hydrogen electrode, the SOP as well as SRP of hydrogen electrode is taken as 0. So this becomes minus 0.0591 divided by N value is given to me as 2 log of QC. What is the QC value? QC is 10 raised power minus 3. Now, my dear students, this is minus 0.0591 divided by 2 log of M raised power N, which comes out to be N log M. So minus 3 comes to the front. Minus 3 comes to the front. And then it's going to be log 10. Log 10 value is 1. So the answer is going to be in volts. That's all. I believe these sort of small questions you can easily solve if they come in your examination. Okay. Now look at this one. Look at this one, guys. Look at this one. Again, you are given with the half cell. What do we have to calculate? We have to calculate the reduction potential. We have to calculate reduction potential. Yes, yes, tomorrow we have question practice session at 8 p.m. tomorrow. 8 p.m. Yes, yes, yes. We have to calculate reduction potential of this half cell. My dear students, if you look at the question carefully, the reaction is Cr2O7 di-negative gives Cr tri-positive. First of all, is the reaction balanced? No. 2 chromium, 2 chromium. Since the oxidation state of chromium here is +6, here it is +3. +6 to +3, decrease in the oxidation state. Decrease in the oxidation state means reduction. Reduction involves gain of electrons. How many? +6 to +3. The change in the oxidation state is 3. 3 is the change for one atom, but I have 2, so 3 2s are 6. So I'll get 6 electrons here. Okay, I'll write 6 electrons here. But still the reaction is not complete. It is not balanced yet. We have to balance this reaction completely. How do we balance this reaction? Understand. We have got 7 oxygen atoms from this side. 7 oxygen atoms from this side. So what I'll be doing, I'll be writing 7 water molecules from this side. We have got 14 hydrogens on this side. I'll write 14 H positives on this side. With every ion you write aqueous. With every ion you write aqueous. So now it's a complete reaction. Now it's a complete reaction. Okay? Now it's a complete reaction. Now first of all, how many electrons do you see here? 6. So I would say the value of N right here is 6. The value of N right here is 6. If you want to write the expression for QC, start with the product. So it's concentration of chromium tri-positive raised power stoichiometric coefficient 2. Water is in liquid state. Its active mass is 1 divided by. This is going to be concentration of Cr2O7 di-negative raised power stoichiometric coefficient 1. Similarly, concentration of H positive raised power stoichiometric coefficient 14. What is the concentration of Cr tri-positive? It's given to us in the question. That is 2 into 10 raised power minus 2 raised power 2 whole divided by. Concentration of Cr2O7 di-negative is again given in the question. 4 into 10 raised power minus 4. Now, H positive concentration is not given. But, my dear students, no doubt, H positive concentration is not given. But at the same time, pH is given. pH is how much? pH is 1. pH is 1. Remember, if pH is given as X, remember H positive concentration means 10 raised power minus X. Remember this particular point. If pH of the solution is given to me as X, okay, H positive concentration is going to be 10 raised power minus X. So I would say H positive concentration right here will be equal to 10 raised power minus 1 molar. Okay, so you got the H positive concentration, 10 raised power minus 1. So 10 raised power minus 1 raised power 14 is going to be 10 raised power minus 14. So this entire term cancels out. So it comes out to be directly 10 raised power 14. Okay, this is QC. Now you got QC, you got the value of N, right? What do I have to calculate? I have to calculate the reduction potential. My dear students, reduction potential. Use the Nernst equation. ERED is equal to E naught RED minus 0.0591 divided by N. Then it's going to be log of QC. Then it's going to be log of QC. Now, first of all, E naught RED represents standard reduction potential. Look at this particular term. This is your SRP. Why? Because see, +6 to +3. +6 to +3, decrease, reduction. So this is SRP, right? I need SRP value only here. So it's 1.5 minus 0.0591 divided by N value is how much? N value is 6. Log of QC. QC came out to be 10 raised power 14. Now log of M raised power N will be N log M. So 14 comes to the front. With that, you have log 10. Log 10 is 1. You just have to solve this equation and you'll be getting the answer in volts. I believe this is clear. Quickly. Okay. Am I clear, guys? Mohsen, you have already completed 6 MCQs. Okay. You have already covered 6 MCQs till now. Don't worry. It happens. All right. Now, my dear students, where else do we use Nernst equation? Where else do we use Nernst equation? The question is calculate the EMF of the cell. Calculate the EMF of the cell. Calculate the EMF of the cell. First of all, this is the complete cell. It's the complete cell. As you see, this is the salt bridge here. As you see, this is the salt bridge here. On the left of the salt bridge, you'll be having anode. On the right side of the salt bridge, you have got cathode. What do we have to calculate? We have to calculate EMF of a complete cell. Now, what do we do in order to solve such question? First of all, write the reaction at anode. Write the reaction at anode. Reaction at anode oxidation takes place. Sn gets converted into Sn dipositive. I would say Sn solid gives Sn dipositive aqueous, and with that you write 2 electrons. This is the reaction at anode. Similarly, if I ask you what is the reaction at cathode reduction takes place. Pb dipositive gets converted into Pb solid. So I would write Pb dipositive aqueous would be gaining 2 electrons and would be getting converted into Pb solid. Because this is the reaction taking place at cathode, and at cathode reduction takes place, and reduction means gain of electrons. Yes? Perfect. Now, my dear students, try to understand. Are the electrons balanced in both the reactions? Yes, the electrons are balanced. So you can directly add these 2 reactions up. When you add these 2 reactions, this is going to be Sn solid plus Pb dipositive aqueous. It gives what? It gives Sn plus 2 aqueous, and with that you get Pb solid. So this is your net reaction. Look at the N value. How many electrons got cancelled? 2. So N value is 2. N value is 2, right? N value is 2. My dear students, if N value is 2, can we write QC expression? Start with the product. So it's going to be concentration of Sn plus 2 raised by stoichiometric coefficient. This is in solid form, its active mass is 1, nothing to do with that. This is in solid form, active mass 1 multiplied by concentration of Pb dipositive raised by 1. Now the concentration of Sn dipositive is given to me in the question, that's 1 divided by concentration of Pb dipositive is also given to me, 10 raised by minus 3. The value comes out to be 10 raised by 3. So you got QC, you got N. Now one thing is missing. What is that? That is E naught cell. How do we calculate E naught cell? E naught cell is calculated as E naught of cathode minus E naught of anode. E naught of cathode minus E naught of anode. Now, my dear students, which one is cathode? On the left side of the salt bridge, you always write anode. On the right side, you write cathode. So lead is your cathode. Lead is your cathode, right? So SRP of cathode, SRP of lead is given to me as minus 0.13 minus SRP of anode, SRP of tin. SRP of tin will be how much? SRP of tin is, say, plus 2 to 0, decrease, reduction. So this SRP, so it's already given minus 0.14. The value comes out to be 0.01. So this is your E naught cell. So you got E naught cell, you got QC, you got the value of N, everything you got. Now it is the time to use Nernst equation, that's all. I would say, as per Nernst equation, E cell is equal to E naught cell minus 0.0591 divided by N, then it's going to be log of QC. Now people, just put the values and we are done. E cell is equal to E naught cell is how much? 0.01 minus 0.0591. N value is how much? N value we got as 2 log of QC. QC came out to be 10 raised by 3. So this would be simply 0.01 minus 0.0591 divided by 2 log of m raised by n, which is n log m. Log 10 is 1. It is a matter of calculation, and this is going to be the value of the EMF of the cell. Right? Perfect. So guys, is it clear? Did you understand what kind of questions can be framed from the Nernst equation? Sometimes they'll ask you to calculate the oxidation potential of the half cell. Sometimes they'll ask you to calculate the reduction potential of the half cell. Sometimes like this, they'll ask you to calculate the EMF of the complete cell. So I hope you got to know all the 3 procedures. Okay? All right? So simply reaction at anode first, then reaction at cathode, add the 2 reactions, get the net reaction, get the QC value, get E naught cell, and finally use the Nernst equation. That's all. Quickly let me know in the chats if it is clear. Everyone. Quickly, guys. Quickly in the chats. Perfect. The ones who have got some doubt in this question, just drag the video a little back. It will be a replay for you automatically. Just use common sense a bit, right? The ones who are telling me to explain this question again, just drag the video a little back. It will be a replay for you. Why do you want me to say it again? All right, this is done, guys. So let's move on. Let's move on. Let's move on. Let's move on to one more topic. That is your Nernst equation at equilibrium. How do we write Nernst equation at equilibrium? How do we write Nernst equation at equilibrium? How do we write Nernst equation at equilibrium? I hope you remember, my dear students. I hope you remember. Like some time back, I told you, when the cell attains equilibrium, at that point of time, your delta G becomes 0 as well as E cell becomes 0. Do you remember that? Do you remember at equilibrium, delta G will be 0, also E cell will be 0. And remember at equilibrium, QC is replaced by KC. QC is replaced by KC. That's all. Rest everything is same. Okay? So first of all, if you remember your Nernst equation, that used to be delta G is equal to, or if you directly use the general equation of the Nernst form, that was E cell is equal to E naught cell minus 2.303 RT divided by NF. Then it used to be log of QC. Now, if I use the above condition in this equation, E cell value at equilibrium is 0 is equal to E naught cell minus 2.303 RT divided by NF. Then it's going to be log of, instead of QC, I'll write KC. Right? So if you take E naught cell on this side, minus gets cancelled out. So I get one expression, E naught cell is equal to 2.303 RT divided by NF, and it's going to be log of KC. This is the equation with the help of which you can calculate E naught of the cell. Okay? E naught of the cell. At the same time, people, if you look at this particular equation, what we can do here is, again, we can take the value of R as 8.314 joules per Kelvin per mole. Right? We can take the value of temperature as 25 degrees centigrade, which is nothing but 298 Kelvin. We can take the Faraday's constant as 96500. If you put these three into this particular expression, what do we get finally? We get E naught cell is equal to 0.0591 divided by N log of Kc. This is particularly the equation which I'll be using in majority of the questions which are asked about Nernst equation at equilibrium. Okay? Which are asked about Nernst equation at equilibrium. So, E naught cell is calculated as 0.0591 divided by N log of Kc, where Kc represents your equilibrium constant. One more expression which we can use here. Since you know delta G is equal to delta G naught plus RT ln of QC. Do you remember this? From this expression only, we derived Nernst equation. Now, if I use this particular condition here, right? Delta G value is 0 already. So, delta G naught comes this side. It becomes minus delta G naught. So, I'll write minus delta G naught is equal to RT ln of. Instead of QC, what should I write? I should write KC. So, I got one more result. Delta G naught is equal to minus RT ln of KC. Or I can say delta G naught is equal to minus 2.303 RT log of Kc. This is one more expression with the help of which we can calculate delta G naught for a cell. Okay. So, two expressions are important here in this slide. E naught cell is equal to 0.0591 divided by N log of Kc, right? Similarly, delta G naught is equal to minus 2.303 RT log of Kc. Okay. This is used to calculate E naught cell. For example, if you are given the question, in the question Kc, equilibrium constant is given. N value is also given. Okay, let me give you one question. For example, I'm giving you a question like this. Question is like this. I'm giving you the cell like this. Zinc solid plus copper dye positive aqueous. For example, it gives, or let me write a general reaction here. A plus B gives A positive plus B negative. A plus B gives A positive plus B negative. For example, the reaction is at equilibrium. the sign is given as equilibrium in the question. For example, Kc value is given to me as 10 raised power 10. They are asking me to calculate E naught cell. Can't we calculate it? We can do it easily, right? How do we calculate E naught cell? Since the cell is at equilibrium, you know E naught cell is equal to 0.0591 divided by n log of Kc, right? So it's going to be simply 0.0591. What would be the n value? See, 0 to plus 1. N value here is 1, right? Log of Kc. Kc value is how much? 10 raised power 10. Log of m raised power n is n log m. So this comes out with, this 10 comes to the front. It comes out to be finally 0.591 volt. This is your E naught cell. So like this, you get these sort of questions. Like this, you get these sort of questions. Again, simple and basic only. Yeah? Is it clear? Is it clear, people? Or sometimes in some of the questions, they will give you E naught cell value. They'll give you n value. They'll ask you to calculate equilibrium constant Kc. Again, you have to use the same expression, nothing else. Okay? Got it? Now, guys, we are going to move on to something called as concentration cells. What are concentration cells exactly? How do we define the concentration cells? See, first of all, whatever galvanic cells we saw till now, in every galvanic cell, how many electrodes did we use? We used 2 electrodes. In order to make a galvanic cell, how many electrodes do we use? We use 2 electrodes, right? But both the electrodes, were they same or different? Both the electrodes used to be different till now. Both the electrodes used to be different. For example, on one side we used zinc, on another side we used copper. On one side we used hydrogen, on another side we used silver. Something like that. On one side one electrode, on another side another electrode. Then connect them externally and internally. Yeah? But when it comes to your concentration cell, in your concentration cell, remember, 2 same electrodes are used. Two same electrodes are used. In your concentration cell, I would say 2 same electrodes are used. Okay? First of all, point number 2. In case of concentration cells, E naught cell value is equal to 0. How E naught cell is equal to 0? You'll get the idea in some time. Or let's first of all check it out. For example, let's say this is your zinc sulfate and this is your zinc rod. Let's say this is again zinc sulfate and this is your zinc rod. So, do I have 2 same electrodes or different electrodes? Again, I have got 2 same electrodes. Now, I'm connecting these electrodes externally. I'm connecting these electrodes externally with the help of voltmeter and internally with the help of salt bridge. Can I say I got a complete galvanic cell? In this particular cell, do you see 2 same electrodes being used? Yes, 2 same electrodes are used. Whenever you see a cell in which 2 same electrodes will be used, you'll be calling the cell as the concentration cell. Now, in the concentration cell, how do we calculate E naught cell? E naught cell is nothing but E naught cathode minus E naught anode. E naught cathode minus E naught anode. What is E naught cathode? It is SRP of cathode. What is E naught anode? This is SRP of anode. Now see, let's say this is your cathode, for example, this is your anode. Cathode means zinc electrode. This is also zinc electrode. So basically SRP of zinc minus SRP of zinc. SRP of zinc minus SRP of zinc will be 0. Simple. SRP of zinc minus SRP of zinc. Because both sides we have got zinc only. SRP of zinc minus SRP of zinc will be 0, right? So remember, when it comes to your concentration cell, your E naught cell will be equal to 0. Now, let me tell you, these concentration cells are further classified into 2 types. What all types? One is called as electrolytic concentration cell. One is called as electrolytic concentration cell. And one is called as electrode concentration cell. One is called as electrode concentration cell. Now, what is the difference? In electrolytic concentration cell, partial pressure is kept same, but concentration is kept different. What is meant by that? You'll understand in some time. In electrode concentration cell, partial pressure is kept same, but concentration is kept, just a second, guys. There is electricity cut, I think. Okay, just a second, okay? All right. So what I was trying to say is, in your electrode concentration cell, what you will see partial pressure is kept different, but concentration is kept same. What is meant by that? What is meant by all this? We have to understand this a bit in detailed way. First of all, you can mark the heading as electrolytic concentration cell. If I mark the heading as electrolytic concentration cell, what is happening in electrolytic concentration cell? What happens in it? What happens in electrolytic concentration? What happens in electrolytic concentration cell? Try to understand. Try to understand, guys. For example, this is a container. It contains a solution. And for example, this solution contains Mn positive ions. Let's say the concentration of Mn positive ions here in this container is C1 molar, for example. And this is a rod of metal M. So can I say I got an electrode first of all? I got the rod which is dipped in a solution containing its own ions. This is one electrode. Similarly, another one, again you have got Mn positive ions here, concentration C2 molar, and this is a rod. Which rod? M rod. Do you see two same electrodes or two different electrodes? Tell me that. We have got two same electrodes. Now, my dear students, I'm connecting them with the help of voltmeter, right? And internally connecting them with the help of salt bridge. So, I got two electrodes, two same electrodes, which are connected externally as well as internally. Perfect. Now, people, if you look carefully, how do we represent this particular cell? So, in the middle, I'll be writing salt bridge. On the left side, I'll be writing anode. For example, this is your anode. At anode, your M is getting converted into Mn positive. At anode, your M solid is getting converted into Mn positive. Mn positive aqueous. The concentration of Mn positive here is C1 molar. On the right side, you will be writing cathode. And at cathode, Mn positive will be getting converted into Mn positive aqueous, whose concentration in the right container is C2 molar. It would be getting converted into what? It would be getting converted into M solid. Now you tell me one thing. Did I use two same electrodes or two different electrodes? These are two same electrodes. These are two same electrodes. Is the concentration same or different? Concentration is different. Whenever you have two same electrodes, wherein the concentration is kept different, you call this concentration cell as the electrolytic concentration cell. Now, my dear students, let's try to understand few things about this electrolytic concentration cell. So first of all, on the left side of the salt bridge, what do we have? We have got anode. Now at anode, what happens? Oxidation. M solid gets converted into what? M solid gets converted into Mn positive aqueous with concentration C1 molar plus how many electrons? N electrons. This will be the reaction taking place at anode. Similarly, what reaction takes place at cathode? At cathode, reduction takes place. Reduction means gain of electrons. So Mn positive gets converted into M. Mn positive aqueous plus N electrons gets converted into what? Gets converted into M solid. Now this Mn positive, its concentration was C2 molar. Perfect. Now are the electrons same? Yes, the electrons are same. So you need to add them. When you add them, what do we get? M solid gets cancelled. So I'll be left with Mn positive aqueous, whose concentration is C2 molar. It gives what? It gives Mn positive aqueous, whose concentration is C1 molar. This is my net reaction. If this is my net reaction, can we write QC expression? QC expression is going to be concentration of Mn positive, right? This one, which is C1. Concentration of Mn positive, which is C1, divided by concentration of Mn positive, which is C2. So C1 divided by C2. Perfect. Now, already we know it's a concentration cell. And you know, in case of concentration cell, your E cell value. In case of concentration cell, your E naught cell value is equal to what? In case of concentration cell, your E naught cell value will be equal to 0. will be equal to 0, right? Will be equal to 0, correct? Now guys, if you use the Nernst equation says that E cell is equal to E naught cell is 0 minus 0.0591 divided by n log of QC. QC value is how much? C1 divided by C2. Now, if you multiply this log with minus sign, it becomes E cell is equal to 0.0591 divided by n, then it's going to be log of C2 divided by C1. Multiplying log with minus, the reciprocal happens here. It becomes C2 by C1. Okay. Now guys, do you remember I had told you for any galvanic cell to be working, E cell value should be greater than 0. E cell value should be positive. So I'll write a statement. For the electrolytic concentration cell, involving which electrodes? See, this is the electrolytic concentration cell involving metal ion electrodes. Involving metal ion electrodes to be working. For this cell to be working like a normal galvanic cell. E cell value should be positive. Then only delta G will come out to be negative. And when can be E cell positive? E cell can be positive only if this particular term is positive. If log of C2 divided by C1 is positive. And when can be log of X positive? Let's say this is X. When is log of X positive? Log of X is positive when X is greater than 1. So that means C2 divided by C1 should be greater than 1, which means that C2 should be greater than C1. What was C2 and what was C1? C2 was the concentration of electrolyte in cathode and C1 is the concentration of electrolyte in anode. So I would say for any electrolytic concentration cell involving metal ion electrodes to be working like a normal galvanic cell, remember, concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anode. Then only what? Then only E cell value will come out to be positive, and once E cell comes out to be positive, delta G would be negative, and once delta G is negative, that means cell reactions will be spontaneous, and if cell reactions are spontaneous, electrons will move from anode to cathode and current will go from cathode to anode. Simple, right? All clear, people? Quickly. Everyone in the chats. Perfect. Now let's have a look on electrode concentration cell. Electrode concentration cell. Okay, electrode concentration cell. So what happens in electrode concentration cell? I told you, in electrolytic concentration cell, concentrations are kept different. In electrode concentration cell, partial pressure is kept different. What does that mean? Try to understand what it means. See guys, for example, understand carefully. I'm going to make a cell here, like this. Platinum solid, H2 gas, whose partial pressure is P1 bar. This is H positive aqueous. Its concentration is C molar. This is basically the concentration of H positive in anode, right? Now, here I'm writing H positive aqueous, whose concentration is again C molar. And this is, for example, your H2 gas, whose partial pressure is P2 bar. And on this side, I'm using platinum. What do you observe in this particular cell? Are we using two same electrodes or two different electrodes? What do you see? Are we using two same electrodes or two different electrodes? We are using two same electrodes. Hydrogen electrode. Two same electrodes. No doubt we are using two same electrodes. That means it's a concentration cell, because in concentration cells, we use same electrodes. So it is a concentration cell. Number one. Number two is the concentration of H positive, is the concentration of electrolyte in both the solutions, anode and cathode, same or different. Concentration of electrolyte is same. But partial pressure is kept different. Whenever you see such kind of the cell, wherein the concentration of electrolyte in both the containers will be the same, but partial pressures of both the electrodes will be different. This particular cell I'll be calling as electrode concentration cell. Now we have to see what is the condition which this particular cell has to follow such that it will start working. We have to see the condition. Like we saw in the earlier case, concentration of electrolyte in cathode should be greater than that of anode. Then only E cell will be positive. Once E cell is positive, the cell will work. Okay. Similarly, what is the condition here? What is the condition here? We have to make that condition. And how do we make that condition? Let's have a look. This is the salt bridge. On the left side, we write anode. At anode, what happens? Oxidation. Do you see H2 getting converted into H positive? So I would say H2 gas, whose pressure is P1 bar. It gets converted into 2 times H positive aqueous plus how many electrons? 2 electrons. The concentration of H positive here is C molar. Okay. This is the reaction which takes place at anode. Now, similarly, what reaction takes place at cathode? What reaction takes place at cathode? At cathode, reduction takes place. H positive gets converted into H2. So the reaction is going to be 2 times H positive aqueous plus 2 electrons. The concentration of H positive here is C molar, right? It gives what? It gives H2 gas, and the partial pressure of H2 gas here is P2 bar. Perfect. Now guys, if I add the two reactions, this 2 gets cancelled, so N value is equal to 2. N value is equal to 2. Now, my net reaction. This twice H positive gets cancelled because their concentration is same. Now talk about their partial pressures. So H2 gas, whose partial pressure is P1 bar, gives H2 gas, whose partial pressure is P2 bar. Whose partial pressure is P2 bar. Perfect. Now guys, let's try to get the QC value. QC is this partial pressure divided by this partial pressure. So P2 divided by P1. This is QC. If I ask you what would be the E0 cell, since it is a concentration cell, so E0 cell has to be 0. Now, if I use the Nernst equation says that E cell is equal to E0 cell is equal to E0 cell. E0 cell is already what? E0 cell is 0 minus 0.0591 divided by N log of QC. What is QC? QC here is P2 divided by P1. P2 divided by P1. If I multiply with minus sign, I'll say E cell is equal to 0.0591 divided by N. It's going to be log of P1 divided by P2. Log of P1 divided by P2. Okay, log of P1 divided by P2. Now, the point is, for this cell to be working, E cell value should be greater than 0. For this cell to be working, E cell value should be greater than 0. Then only delta G would be negative. And delta G negative means cell reaction spontaneous. Cell reaction spontaneous means at anode oxidation will happen, at cathode reduction will happen. Electrons will move from anode to cathode. Current will go from cathode to anode, right? Do you understand? Now the point is, how can be this E cell positive? E cell can be positive if this particular term is positive. E cell can be positive if log of P1 divided by P2 is positive. When can be log of P1 by P2 positive? That means when can be log of X positive? Log of X can be positive only if X is greater than 1. That means P1 divided by P2 should be greater than 1, which means that P1 should be greater than P2. What was P1 and what was P2? P1 was the partial pressure of anode. P2 is the partial pressure of cathode. So for this particular cell to be working, partial pressure of anode should be greater than that of partial pressure of cathode. Do you understand? This is the condition for the cell to be working. Partial pressure of anode should be greater than that of partial pressure of cathode. Then only E cell value will be positive. Once E cell is positive, then only delta G will be negative. Once delta G is negative, cell reactions will be spontaneous. And if the cell reactions are spontaneous, that means the cell is working. Got it? Am I clear, guys? Am I clear till here? Yes? Perfectly done. Yes, this is for 12th. I mean, this for NEET students basically, as well as 12th students. I hope all this is like very, very, very clear to everyone. Quickly tell me in the chats, guys, is every single thing clear? Yes, we have solutions also. Oh my God. When is our next session, by the way? Do you know the schedule? Today it was Wednesday. Wednesday was my session, right? Wednesday is your physical chemistry. Thursday, that means tomorrow. Tomorrow at 8 p.m. What do we have? We have got questions. Question practice of this 12th. Friday is your physics. Saturday is also physics. Questions. Then Sunday is my session again. Okay. Sunday and Monday. Huh? Guys, see, I don't think we will be able to complete solutions today. We have to take it in another session. Because it will be a rush to this chapter then. I don't want that to happen. Now we have seen everything detailed, so is that okay? Sunday morning 10 a.m. Right? Not tomorrow morning. How come it's possible? Yes, Sunday also you have session. Yes, I have kept class on Sunday also. See, if we continue solution in the today's session, then it will be a rush to solution chapter. And that should not happen. So let's take solution on Sunday. Tomorrow question practice will happen as such, as usual. It has got nothing to do with that. Question practice will be there already. Right? हाँ बेटा 2 बजे तक कंटिन्यू करो हाँ 16 घंटे पढ़ाऊँ No, tomorrow I cannot teach solutions. See, basically when I take the marathon, I keep my online classes off that day. Do you understand that? So I cannot, I keep my offline classes off that day, basically. So we can do one thing. We can do one thing like this. Wait. I got it. We can do one thing. See, today we were supposed to complete 3 chapters. Okay. So keep it as part 1, part 2. Physical chemistry part 1 and physical chemistry part 2. Okay. Let's say part 1 is done today. Now we are left with part 2. Part 2, if we do on Sunday, for example, let's say people are saying they have exam on Sunday. What time you want to keep the session on Sunday? What is your feasible time? Tomorrow we'll keep the question practice. Tomorrow means tomorrow is Thursday. We'll keep the question practice for chemical kinetics and electrochemistry. That makes sense, right? Chemical kinetics plus electrochemistry. Question practice tomorrow. I'm not going to add questions of solution chapter tomorrow. Makes sense, right? फिर इनऑर्गेनिक संडे का शिफ्ट हो जाएगा आगे की ओर. What is the problem? Why are you so worried? I'm here, don't worry. I've told you I'll complete everything. Okay? We don't have 7 hours remaining for today. What are you telling me? We have started at 10:30 today. We have started at 10:30 today. So it's already been how many hours? I think we are about to finish 10 hours. The live session on YouTube can go maximum till 12 hours. Do you know that? It's a YouTube policy. The maximum live in one stream can go to maximum 12 hours. Okay, let's continue for now. Let's continue for now. Then we'll see. At the end. We have got 2 options for solutions. Either I'll be providing you the recorded lecture of solution today only. Okay, but that will be recorded. Okay, or else we have to take the live session on Sunday. 2 options. We'll see that at the end. So first of all, let's complete this. Guys. Can you tell me the answer of this particular question? I want to know. What is going to be the answer of this particular question? Quickly, check it out. Check it out, quick, 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 quick. I solve the question. We'll talk about that at the end. Live recorded. We'll talk about at the end. First of all, try this question out. First of all, do you see two same electrodes? Zinc electrode, right? Two same electrodes. So it's a concentration cell. It's a concentration cell, first of all, number one. Number two, is the concentration same or different? Concentration is different. So it is electrolytic concentration cell. It is electrolytic concentration cell. And for the electrolytic concentration cell involving metal line electrodes to be working, what is the condition? Condition is concentration of electrolyte in cathode should be greater than that of anode. Cathode's concentration is C1. So C1 should be greater than C2. Then only the cell will work. Then only the cell will work. This is the condition here. Concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anode. Then only the cell will work. Correct? Now, the cell reactions will be spontaneous if C1 is greater than C2. Absolutely, C1 should be greater than C2. Right? The cell will work. So this is correct. If C2 is greater than C1, if C2 is greater than C1, current flows from cathode, current does not flow. If C2 is greater than C1. Guys, I just interchanged things here. Do you understand that? Do you understand? Few minutes back, I was keeping this as C1, this as C2. Then at that time, C2 should have been greater than C1. But here, C1 should be greater than C2. I've interchanged them just to confuse you, nothing else. Right? Do you understand? Now, look at the third option. If C1 is greater than C2, if C1 is greater than C2, if concentration of electrolyte in cathode is greater than that of concentration of electrolyte in anode, then E cell will be positive, delta G would be negative, cell reactions will be spontaneous, electrons will go from anode to cathode, current will go from cathode to anode, This is correct. If C1 and C2 are same, if there is no concentration difference, if C1 and C2 are same, what will happen at that time? If C1 and C2 are same, what will happen at that time? If C1, C2 are same, they'll cancel out. It becomes log 1. Log 1 is 0. So this entire term becomes 0. So E cell is 0. So E cell becomes 0, right? If E cell becomes 0, that means potential difference between the electrodes is 0. And when potential difference between the electrodes is 0, that means current will not flow. So this is also correct. So ACD is the correct answer. ACD is the correct answer. Yeah? Got it? Am I clear till here? Everyone in the chats once? Perfect. All right. Let's move on to electrolysis now. Let's move on to electrolysis now. Let's move on to electrolysis now, guys. All right. So we'll be first of all starting with electrolysis of molten NaCl. Electrolysis of molten NaCl. Now try to understand what exactly we are going to do. First of all, I'm going to take one container. Till now, in galvanic cell, I used to take two containers. Now here, I'm taking one container. In this particular container, for example, we are keeping molten NaCl. We are keeping molten NaCl. Okay? We are keeping molten NaCl. Molten NaCl means what? That means you have taken NaCl, you have heated it up till it melted, right? So this is the molten NaCl here in the container. So basically, I would say there will be two types of ions in the container. One is going to be your Na positive and one is going to be your Cl negative. One is going to be your Na positive, one is going to be your Cl negative. Now, first of all, these are two electrodes which I'm using here. And these two electrodes I'm connecting with the external battery. These two electrodes I'm connecting with the external battery. Okay. Since this electrode I'm connecting with the negative end of the battery, so this electrode gets negative charge. And this electrode I'm attaching with the positive end of the battery, so it gets positive charge. Now, this particular cell, my dear students, this particular cell is first of all what we call as electrolytic cell. This device is called as electrolytic cell. And that electrode which carries the negative charge here in electrolytic cell, it is called as cathode. And the device which carries the positive charge here, it's called as anode. It's called as anode. Okay. Rest everything is same. At cathode, reduction takes place. At anode, oxidation takes place. Okay. Now what is going to happen? If you think logically, what is going to happen? You have kept molten NaCl here. So there would be Na positive and Cl negative in the container. And between Na positive and Cl negative, there will be attraction. Between Na positive and Cl negative, there will be attraction. Now this negatively charged rod will attract Na positive towards itself, and this positively charged rod will attract Cl negative towards itself. So what is going to happen? At cathode, what happens? At cathode, reduction happens. At cathode, reduction happens. Reduction means gain of electrons. Reduction means gain of electrons. So Na positive will go to the cathode. Na positive will go to the cathode and will undergo reduction. Reduction means it will gain electron and will get converted into Na solid. So I would say on cathode, sodium solid is getting deposited. Na solid is getting deposited. Na solid is getting deposited, right? Now similarly, guys, at anode what happens? At anode, oxidation takes place. This is your anode basically. And this anode, towards this anode, which ion is going? Cl negative. At anode, oxidation takes place. So I'll say Cl negative at anode will undergo oxidation, will lose electrons. So the reaction is going to be 2 times Cl negative gives Cl2 plus 2 electrons. Gives Cl2 plus 2 electrons. Now the question that is asked here, during the electrolysis of molten NaCl using inert electrodes, during the electrolysis of molten NaCl using inert electrodes, what are the products of electrolysis? What are the products of electrolysis? What are the products of electrolysis? So the products of electrolysis here are sodium and chlorine. Products of electrolysis means what got deposited or liberated at the each electrodes. What got deposited or liberated at each electrodes. So as you can see over here clearly, at cathode, metal is being deposited. Which metal? Sodium is being deposited. At cathode, sodium is getting deposited. And similarly, if I talk about anode, at anode, what is produced? At anode, Cl2 gas is produced. At anode, Cl2 gas is produced. These are the direct questions which are asked. These are the direct questions which are asked. Okay. So basically, if you look carefully, what is happening? Can I say chemical decomposition of NaCl is happening? Chemical decomposition of NaCl is happening. And this NaCl is getting converted into its constituents. Sodium is separated, chlorine is separated. So this phenomenon over here is what you call as electrolysis. And the device in which electrolysis is carried out is called as electrolytic cell. I'll give you one more example of it so that it becomes like very clear to you. For example, if I talk about electrolysis of molten PbBr2, again using inert electrodes. Again using inert electrodes. Again using inert electrodes. Say guys, for example, this is the container in which electrolysis is going to happen. Let's say this is your molten PbBr2. Let's say this is your molten PbBr2. Okay, so basically, if you crisscross, this is Pb di positive technically, this is Br negative. So in the solution, there are Pb di positive ions and there are Br negative ions. Correct? Let's say this is one of the rod and this is one more rod. They are connected with the external battery. Let's say this rod carries negative, this rod carries positive. This negatively charged rod here in electrolysis is called as cathode and this is called as anode. This is called as anode. Correct? Now, this negatively charged rod is going to attract this Pb di positive towards itself and this is going to attract this one. Perfect. So at cathode, what happens? At cathode, if you remember, if you see, at cathode reduction takes place. At cathode reduction takes place. Reduction means gain of electrons. Reduction means gain of electrons. So I would say at cathode, Pb di positive will go at cathode and will undergo reduction, will gain electrons. When it gains electrons, it will gain 2 electrons and get converted into Pb solid. So at cathode, Pb solid is being deposited. At cathode, Pb is being deposited, right? Similarly, what is happening at anode? At anode, what happens? Oxidation takes place. Towards anode, who is going? Br negative. So Br negative will undergo oxidation. So the reaction is going to be 2 times Br negative gives Br2 plus 2 electrons. So what is produced at anode? At anode, I would say Br2 is produced. So what are the products of electrolysis? Conclusion. What are the products of electrolysis? At cathode, Pb is getting deposited. At cathode, Pb is getting deposited. And similarly, at anode, what is happening? At anode, I would say Br2 is produced. Br2 produced, or I can say Br2 is liberated. Okay? These are the products of electrolysis when we do the electrolysis of what? When we do the electrolysis of molten PbBr2. I hope this is clear. Yeah? Now guys, similarly, this was electrolysis of molten electrolytes. Now, there are few reactions which I would want you guys to remember. Few reactions. One reaction is called as oxidation reaction of water. And one reaction is called as the reduction reaction of water. One is the oxidation reaction of water. One is the reduction reaction of water. Just a second. This is 2 hydrogen. This is supposed to be 2 times OH negative. Make the change here. This is 2 times OH negative. Just a second. 2 hydrogens, 2 hydrogens. 2 to 4, 4 to 2, correct. Yes. Okay. 2 reactions which you have to remember. One is called as oxidation reaction of water. One is called as reduction reaction of water. Remember them as such. Remember them as such. Why is that? Why I'm telling you to remember these 2? Because there is a logic behind that. The logic I'll make you understand in some time. First of all, you have to remember these reactions. First one is called as oxidation reaction of water. Second one is called as reduction reaction of water. This is oxidation reaction of water, loss of electrons happening. This is a reduction reaction of water, gain of electrons happening. So you have to remember these 2 reactions first of all. Okay. Now, my dear students, try to understand what exactly we are going to do. After remembering these 2, I want you to remember 2 series as well. That's called as discharge potential series for cations and anions. These 2 series I would want you guys to remember as well. Directly. Okay. From where it comes, that time is over. We have got nothing to do with that. Just remember these 2 series directly. One is for cation, one is for anions. Cationic series and anionic series. You can create any sort of mnemonic based on your wish. Okay. One is your cationic series, one is your anionic series. Why am I telling you to remember oxidation reaction of water, reduction reaction of water, discharge potential series for cations, discharge potential series of anions? There is a logic behind that. What is the logic? Let's try to understand. See guys, I'm marking the heading here as electrolysis of aqueous NaCl using inert electrodes. Electrolysis of aqueous NaCl using inert electrodes. Yeah? If you look carefully, this is the container which I'm taking, and in this particular container, I am taking aqueous NaCl. Till now, I was taking molten NaCl. Now what am I taking? I'm taking aqueous NaCl. Now I'm taking aqueous NaCl, right? Aqueous NaCl, what does that mean? That means in the container there'll be Na positive, there'll be Cl negative. Since aqueous means water, that means in the container there'll be H positive as well as OH negative. Correct? Now there will be 4 ions. Yeah? Now, this is the rod, this is one more rod, and they are, connected with the battery. Let's say this rod got negative, this rod got positive. Negatively charged rod is what you call as cathode here, and positively charged rod is what you call as anode here. One is your cathode and one is your anode. One is your cathode and one is your anode, right? Now, my dear students, can I say this is negatively charged? So, Na positive would want to go here, as well as H positive would want to go here. So, at cathode, Na positive would want to go, as well as H positive would want to go, correct? And at cathode, what happens? Reduction. So, technically, I should say, Na positive as well as H positive, both would want to undergo a reduction here at cathode, because at cathode reduction happens. Both would want to undergo reduction here. But among these two, only one will undergo reduction. Among these two, only one cation will undergo reduction. That cation undergoes reduction, which has got lesser discharge potential. Now, among sodium and H positive, which one has got lesser discharge potential? The series I gave you a few minutes back. It is the H positive that has lesser discharge potential than Na positive. If H positive has lesser discharge potential, so H positive will undergo a reduction here at cathode. So H positive will undergo a reduction here at cathode. So if you talk about the reaction at cathode, H positive is undergoing reduction. But this H positive has come from where? H positive has come from water. H positive has come from water. So you are going to write the reduction reaction of water here. This is the reduction reaction of water. And because of the reduction reaction of water, which gas is getting produced? So over here, H2 gas will be produced. Do you understand? Do you understand? Similarly, guys, this Cl negative would want to go here, even OH negative would want to go here. Clearly, right? So, this positively charged rod will try to attract this one as well as this one. Positively charged rod is anode. At anode, oxidation takes place. So, in other words, I can say Cl negative as well as OH negative, both would want to undergo oxidation here. Both would want to undergo oxidation here. But among these two anions, which one will undergo oxidation? That anion will undergo oxidation, which has again lesser discharge potential. So among these two, which one has lesser discharge potential? If you look at the series, it is Cl negative that has lesser discharge potential. So Cl negative would go here and undergo oxidation. So what is the reaction at anode? At anode, Cl negative is undergoing oxidation. It's losing 2 electrons and getting converted into Cl2. So I would say here, which gas is being produced? Cl2 gas is being produced. So direct questions are asked. Which gas is produced at cathode? Which gas is produced at anode? What are the products of electrolysis, right? So I would say, if I talk about the products of electrolysis, this is the conclusion. Here is our product of electrolysis. Cl2 is liberated at anode and H2 is liberated at cathode. Right? Perfect. Is it clear, guys? Let me take one more example. With that, things will be more clear. Let me take one more example. With that, things will be more clear. Understand properly. See, for example, I am doing the electrolysis of aqueous copper sulfate. So, for example, this is the container. This is the rod carrying negative, and this is the rod carrying positive. Negatively charged rod here in electrolysis is called as cathode. This is your anode, right? At cathode, a reduction takes place. At anode, oxidation takes place. We already know that, right? Now, guys, what we are keeping here? We are keeping aqueous copper sulfate, not molten copper sulfate. Aqueous copper sulfate. Aqueous copper sulfate means there will be copper dye positives, there will be SO4 dye negatives in the solution. Since it's aqueous, so H positive and OH negative also will be there. Now, this negatively charged rod is called as cathode. At cathode, reduction takes place. Now, reduction of Cu dye positive or H positive. Which cation will undergo reduction? That cation will undergo reduction which has got lesser discharge potential. Which has lesser discharge potential? Cu dye positive or H positive? Cu dye positive has lesser discharge potential. If Cu dye positive has lesser discharge potential, it will undergo reduction at cathode. So at cathode, Cu dye positive will undergo reduction, will gain 2 electrons, get converted into copper solid. That means over here on this particular rod, copper solid is being deposited. Perfect. Perfect, guys. Now similarly, this is your anode. At anode, oxidation takes place. See, this anodic rod carries positive charge. Positive is going to attract negative ones, right? Now, at anode, what happens? Oxidation. So I would say both of them would want to undergo oxidation. Both of them would want to undergo oxidation. But which one will undergo oxidation among these two? Again, that anion would undergo oxidation which has got lesser discharge potential. SO4 dinegative and OH negative. Which one has got lesser discharge potential? OH negative has got lesser discharge potential. So OH negative will undergo oxidation here, right? So what should be the reaction at anode? At anode, OH negative undergoes oxidation. But this OH negative has come from where? It has come from water. It has come from water. So I'll write the oxidation reaction of water, which I told you already to remember. Understood? So what is happening here? O2 gas is being produced. At anode, O2 gas is being produced. At anode, O2 gas is being produced, right? Clear? Perfect, guys. So what is the conclusion here? O2 gas is liberated at anode, copper solid is deposited at cathode, right? And guys, one thing. Similarly, there are so many electrolytes which you have to remember. There are like 7 to 8 electrolytes whose electrolysis you have to remember. You have to remember which metal gets deposited at anode, which metal gets deposited at cathode, which gas gets liberated at this, at that, right? That is something which you have to remember. So after this particular session, I'll be providing you one sheet. On my Telegram, right? I hope you are the part of the Telegram channel. If not, be the part of the Telegram channel on which I will be providing you a sheet. Wassim But Chemistry Official is the name of the Telegram channel. If you are not the part of Telegram, be the part of Telegram, because I'll be sending you one sheet of all the electrolytes and all the products which are obtained at cathode and anode, which you will be remembering. Okay? But after the class. Okay, I hope every single thing is clear till here. Can you tell me the answer of this particular question? Okay, leave it right now as such. We'll talk about this in the tomorrow session when I'll teach you this top 300 questions of physical chemistry. Now let's talk about one more interesting and amazing topic. What is that? That is your Faraday's law of electrolysis. Faraday's law of electrolysis. If I talk about the Faraday's first law of electrolysis, we saw one thing. At the electrode, either metal is being deposited or the gas is being liberated. At the electrode, either metal is deposited or the gas is produced. Now, Faraday's first law says that mass of the metal deposited or liberated in grams. Mass of the metal deposited or the mass of the gas produced. That is directly proportional to the charge that goes into the solution. So basically, the electrodes at the top, they are attached with the battery. What that battery does? Battery sends charge in the solution. So Faraday's first law says that the mass of the metal deposited at the electrode or the mass of the gas produced at the electrode, that is directly proportional to the charge that goes into the solution. So I'll say mass of the metal deposited or mass of the gas released is equal to, I'll use a constant Z multiplied by Q. This Z is what you call as electrochemical equivalent, whose value is equal to E divided by 96500. This Z is called as electrochemical equivalent. Whose value is E by 96500. E is basically the equivalent mass of the substance which gets deposited or liberated. Okay? E is the equivalent mass of the substance that gets deposited or the liberated. Perfect? Who is this Mirubad? Can you get the hell out of this channel, bro? Or do you want me to block you? कहीं से भी आता है, कोई भी आता है. Okay, let's move on now. Let's move on. So I can say mass of the metal deposited or mass of the gas released will be equal. What is Z? Z is E divided by 96500. Multiplied by what? Multiplied by Q. This is one of the results which I would want you guys to remember. One more result, mass of the substance deposited or liberated is equal. Equivalent mass I'm writing as such. Q is basically current multiplied by time. Q is equal to I multiplied by T. Q is basically I multiplied by T divided by 96500. This is one more result which you can remember directly. Now people, one more thing. I can convert this particular result in a different form as well. I can say mass of the substance deposited or liberated is equal. What is E? E is the equivalent mass of the substance deposited or liberated. And let me tell you, equivalent mass is nothing but molar mass divided by N factor. Molar mass divided by N factor. Into 96500 is already in the denominator, and in the numerator you have got I and T, right? If you take this M in the denominator, this becomes W divided by M. W divided by M is equal to I multiplied by T divided by N factor multiplied by 96500. So what is W by M? W stands for mass of the substance deposited or liberated. M stands for the molar mass of the substance. So given mass by molar mass gives me number of moles. So number of moles of the substance deposited or liberated is equal to I multiplied by T divided by N factor of the substance that gets deposited or liberated multiplied by 96500. This is one more important result which you have to remember. Okay, so how many results we have? We have got two results right now. Mass of the substance deposited or liberated at an electrode is equal to EIT divided by 96500. Number of moles of the substance deposited or liberated at the electrode is equal to I into T divided by N factor of the same substance that gets deposited or liberated multiplied by 96500. Clear? Now let's see what kind of questions can be framed out of this. Before showing you the questions, let me tell you one more important thing. How do we calculate N factors of these substances? Understand one simple trick. How many electrons do you see here? 12. So write 12 divided by, what is the stoichiometric coefficient of A? That's 1. So 12 divided by 1 comes out to be 12. 12 divided by 2 comes out to be 6. 12 divided by 3 comes out to be 4. 12 divided by 4 comes out to be 3. 12 divided by 6 comes out to be 2. So these are the respective N factors of A, B, C, D, E respectively. So whenever we have to calculate stoichiometry, whenever you have to calculate the N factor, so what do? Whatever are the number of electrons in the reaction, divide the number of electrons by the respective stoichiometric coefficients of reactants and products. You'll be getting the N factor of each reactant and a product. Got it? Got it, people? For example, look at this reaction. I want you to calculate N factor of O2. See the number of electrons here in this reaction. 4 divided by stoichiometric coefficient 1. So 4 by 1 is 4. N factor of H positive. 4 divided by 4 comes out to be 1. Do you understand? For example, this particular reaction. Tell me the N factor of H2. Electrons are 2 divided by stoichiometric coefficient is 1. What about this one? Electrons are 2 divided by stoichiometric coefficient 2. So 2 by 2 is 1. Perfect. So this is how you calculate N factors of different reactants and products. Now, let's see some questions which will make you understand this particular concept in a better way. Okay? See guys. A solution of aqueous copper sulfate is electrolyzed. So we are doing the electrolysis of aqueous copper sulfate. A solution of aqueous copper sulfate is electrolyzed for 10 minutes. With a current of 1.5 amperes. What is the mass of copper deposited at the cathode? So first of all, we are doing the electrolysis of aqueous copper sulfate. And when we do the electrolysis of aqueous copper sulfate, what happens at cathode? I hope you remember what happens at cathode and what happens at anode. At cathode, copper gets deposited. Few minutes back only we saw. And how copper gets deposited? This is the reaction which takes place. Copper dye positive. I would say copper dye positive at cathode would gain 2 electrons. Copper dye positive at cathode would gain 2 electrons. Copper dye positive at cathode would gain 2 electrons, will get converted into copper solid. So basically here copper solid gets deposited. Now the question is, what mass of copper solid is deposited at the cathode? What mass of copper solid is deposited at the cathode? First of all, how much current goes to this into the solution? 1.5 amperes of current goes into the solution. For how long it goes into the solution? 10 minutes. 10 into 60. That means 600 seconds. Okay, 600 seconds. We are supposed to calculate the mass of copper that gets deposited. Calculate the mass of copper that gets deposited at the cathode when the current of 1.5 amperes is passed through the solution for exactly 10 minutes. So I can directly use Faraday's first law. I can directly use Faraday's first law. As per Faraday's first law, mass of copper deposited is equal. Equivalent mass of copper multiplied by I multiplied by T divided by 96500. Equivalent mass of copper means molar mass of copper divided by N factor. What is the molar mass of copper? 63.5 grams. What is the N factor of copper? What is the N factor of copper? 2 divided by 1. That is 2. This is 96500. What is the value of I? I value is 1.5. What is the value of T? T is 600. When you solve this, the answer comes out to be 0.29 grams. So I would say 0.29 grams of copper is deposited at the cathode when we do the electrolysis of aqueous copper sulfate by the help of 1.5 amperes, which is passed through the solution for exact 10 minutes. Right? Perfect. One more question I'm giving you guys. Look at this question. Look at this question, guys. In this question, again, we are doing the electrolysis of aqueous copper sulfate. Again, we are doing the electrolysis of aqueous copper sulfate. But this time, they are asking you to calculate the volume of oxygen produced at anode. You know, when we do the electrolysis of aqueous copper sulfate, we already know at anode O2 gas is produced, right? At anode O2 gas is produced. We have to check the volume of O2 gas that is produced. The volume of O2 gas that is produced when a current of 2 amperes. When a current of 2 amperes is passed for how many minutes? It's passed for 8 minutes. Is passed for 8 minutes, right? So tell me first of all, the N factor of O2. N factor of O2 will be how many electrons here? 2 divided by stoichiometric coefficient here, 1 by 2. The value comes out to be 4. So N factor of O2 is 4. Perfect. We have to calculate the volume of O2 produced at anode. We have to calculate volume of O2 produced at anode. So first of all, volume of O2 produced at STP will be equal to moles of O2 produced multiplied by 22.4 liters. This is how you calculate volume. So we need to know the moles of O2 produced first. We need to know moles of O2 produced. So I can say moles of O2 produced will be equal to I multiplied by T divided by N factor of O2 multiplied by 96500. What is I? I is 2 amperes. Time is 8 minutes. So multiplied by 60 comes out to be seconds. N factor of O2 is 4 multiplied by 96500. So from here you can calculate the number of moles of O2 which are produced at anode. But as per the question, do I need to calculate moles of O2 or volume of O2? I need to calculate volume of O2. Did we calculate moles of O2? Yes, we calculate moles of O2. Multiplying it with 22.4 liters, you'll be getting the volume of O2 gas produced at STP. Right? Yes? Perfect. Similarly, look at a few more questions. Look at a few more questions. Look at this question, guys. Look at this question. A current of 96.5 amperes. A current of 96.5 amperes is passed. A current of 96.5 amperes is passed for 10 seconds through a 1 liter solution of 0.5 molar aqueous copper sulfate. Calculate the pH of the solution. So again, we are doing the electrolysis of aqueous copper sulfate. Again, we are doing the electrolysis of aqueous copper sulfate. Let's say this is your cathode. Let's say this is your anode. We already know this is the reaction that takes place at cathode, and at cathode copper gets deposited. We saw that already. And at anode, what's happening? At anode, O2 gas is produced as well as H positives are formed. At anode, O2 gas is produced as well as H positive ions are formed. So basically, if you think logically, at cathode, what is happening only? At cathode, copper dipositive is getting 2 electrons, getting converted into copper. And that copper is deposited here. That copper gets deposited here. Correct? That copper gets deposited here. Now, what is happening at anode? At anode, water is undergoing oxidation. First of all, O2 gas is being produced. At the same time, H positives are generated. Where those H positives will go? Those H positives will go into the solution. Those H positives will go into the solution. Right? Those H positives will go into the solution. So, pH of the solution will be decided by which reaction? Cathodic reaction or anodic reaction? Tell me that. pH of the solution will be decided by which reaction? Cathodic reaction or anodic reaction? Quickly. pH of the solution will be decided by which reaction? Cathodic or anodic? pH here will be decided by anodic reaction. Because at anode, H positives are generated and those H positives will be going into the solution. Okay? What do we have to calculate? We have to calculate pH of the solution. What is pH? P stands for minus log. So it is basically minus log of H positive concentration. So in order to calculate pH, we need H positive concentration. H positive concentration means nothing but number of moles of H positive divided by volume of the container in liters. Concentration is moles divided by volume. Moles divided by volume, right? So in order to calculate H positive concentration, we need to know the number of moles of H positive that are liberated in the solution divided by volume of the container in liters. That will give me H positive concentration. Now the point is, how many moles of H positive got liberated at anode? It will be equal to I multiplied by T divided by N factor of H positive multiplied by 96500. What is the value of I? I value is how much? Current of 96.5 amperes. Time is 10 seconds. Divided by N factor of H positive. What is the N factor of H positive? 2 divided by 2. That's 1. Multiplied by 96500. This value comes out to be 10 raised per minus 2. So these are the moles. These are the moles of H positive. These are the moles of H positive that are generated at anode. So finally, I would say these many moles of H positive would have entered into the solution. These many moles of H positive would have entered into the solution. Right? These many moles of H positive would have entered into the solution. So in the solution, finally, there would be these many moles of H positive present. So therefore, what would be the concentration of H positive present in the final solution? Number of moles of H positive in the solution divided by volume of solution in liters. So it is 10 raised per minus 2. Volume of solution in liters is how much? That's 1. So concentration of H positive is 10 raised per minus 2 molar. If the concentration of H positive is 10 raised per minus 2 molar, so how do I calculate pH? P stands for minus log of H positive concentration in the solution. So it is minus log of 10 raised per minus 2. The value comes out to be 2. So pH of the solution is nothing but 2. pH of the solution is nothing but 2. I hope this is clear to everyone. Yes? I hope this is clear to everyone. Right, people? Now, what does Faraday's second law state? What is Faraday's second law all about? It's more questions will be done in the tomorrow session, okay? It's more questions will be done in the tomorrow session. It's more questions will be done in the tomorrow session. Tomorrow's 8 p.m. session. What is Faraday's second law all about? See, simple. For example, you have got, let's say, 2 electrolytic cells. You have got 2 electrolytic cells containing 2 different electrolytes. Let's say the electrolyte present is AB here. Let's say the electrolyte present here is CD. Okay. We have got 2 electrolytic cells containing 2 different electrolytes, AB and CD. Fine. Now, I'm connecting these electrolytic cells with an external battery. Connecting them with external battery. Now, I would say these cells are connected in series. These cells are connected in series. So if these cells are connected in series, that means whatever current will be going into this particular solution, same current will be going into this particular solution, because in the series connection, current remains same, you know that. Right? In the series connection, current remains same. So whatever current will be going in the solution, same current will be going in the solution. See, for example, this is negative end. So this will get negative. If this gets negative, this is positive. If this is positive, this is negative. This is positive, right? So this is basically your cathode. This is your anode. This is your cathode and this is your anode. Perfect. Now, for example, here A is being deposited. For example, here B is produced. B is liberated. For example, here C is deposited. Here D is produced. For example, this is something I'm assuming. Faraday's second law says that whenever you have two or more than two electrolytic cells connected in series, gram equivalents deposited or liberated at every electrode will be the same. So whatever gram equivalents of A are deposited at the first electrode, same gram equivalents of B would be liberated at the second electrode. Same gram equivalents of C would be deposited at the third electrode. Same gram equivalents of D would be liberated at the last electrode. This is the simplest statement of what? Faraday's second law of electrolysis. Gram equivalents deposited or liberated at every electrode will be the same. Gram equivalents deposited or liberated at every electrode will be the same. Yeah? Right? Perfect? Perfect, guys? So remember, whenever you see two or more than two electrolytic cells connected in series, that too containing different electrolytes, gram equivalents deposited or liberated at every single electrode will be the same. Okay? I believe this is clear. Now, guys, we are left with one last part of the chapter. Or let's try to do one question first so that you get the understanding of what it's all about. Okay? Let's try to see first of all the questions. During the electrolysis of aqueous copper sulfate, the mass of the metal deposited is equal to 63.5 grams. Calculate the mass of the gas released. See, before solving this particular question, guys, I hope you would have studied sometimes back how to calculate gram equivalents. How do you calculate gram equivalents of the substance? Gram equivalents of the substance is equal to mass of the substance divided by equivalent mass of the substance. Like, you know, given mass divided by molar mass, that gives me number of moles. Similarly, given mass divided by equivalent mass, that gives me number of gram equivalents. Right? Yes? So, I can say gram equivalents of A deposited at the first electrode, that will be equal to mass of A deposited divided by equivalent mass of A is equal to gram equivalents of B. Gram equivalents of B would be mass of B produced divided by equivalent mass of B is equal to, this would be mass of C divided by equivalent mass of C. This would be mass of D divided by equivalent mass of D. Right? This is the simple way of writing your Faraday's second law. Now, if you got it, so then we can easily solve this particular question. The question is, we are doing the electrolysis of aqueous copper sulfate. And when you do the electrolysis of aqueous copper sulfate, what happens at cathode? At cathode, copper gets deposited. You know that. And at anode, O2 gas is produced. We know that too. At anode, O2 gas is produced. Now, Faraday's second law says that gram equivalents deposited here will be equal to gram equivalents released here. So I can say gram equivalents of copper deposited will be equal to gram equivalents of O2 produced. Right? Now, gram equivalents of copper deposited will be equal to mass of copper deposited divided by equivalent mass of copper deposited. This will be gram equivalents of O2 produced, mass of O2 produced divided by equivalent mass of O2. Correct? Now, as per the question, what is the mass of copper deposited? Mass of copper deposited is given to me in the question, 63.5 grams divided by equivalent mass of copper would be molar mass of copper divided by n factor of copper. N factor of copper is 2 divided by 1, that's 2, is equal to mass of O2 produced divided by equivalent mass of O2 would be molar mass of O2 divided by n factor of O2. What is the n factor of O2? 2 divided by 1 by 2. That's 4. Perfect. So when you solve this, mass of O2 produced would be equal to 16 grams. Right? This is 4148. 8 2s are 16. Mass of O2 is equal to 16 grams. So this is the mass of O2 produced at this particular electrode. At the same time, what are we supposed to calculate? Volume of the gas released. You calculated mass of O2 produced. Therefore, moles of O2 produced will be mass of O2 produced divided by molar mass of O2. So 0.5 moles of O2 have produced. Therefore, volume of O2 produced at STP will be moles multiplied by 22.4 liters. The value will be 11.2 liters. So 11.2 liters of O2 would be produced here. Right? Perfect. So before moving into the last part of the chapter, that is the conductance part, let's take a dinner break. After this, it's going to take 1.5 hours more. Okay. So we'll be again meeting exactly at all right. I would want every one of you to be back on time. Huh? Okay. Let's take a dinner break till 8:45, but be back exactly at 8:45. It's not going to take more than 1.5 hours. Okay. Chalo. I'll see you after the break. You can have your dinner. I'll have my dinner too. Guys, can you hear me? Yes, yes, time is up. Time is up, time is up. Is everyone back? Is everyone back? All right, guys, let's move on to the last part of this particular chapter. Let's go to the last part of this particular chapter. What is that? That is terminologies related to electrolytic conductance. Terminologies related to electrolytic conductance. So let's try to understand different terminologies which are related to electrolytic conductance. Okay, let's try to understand. See, guys, first of all, for example, this is a container which I have. And in this particular container, you are keeping an electrolytic solution. You are keeping an electrolytic solution. You have got an electrolytic solution present in this container. Okay. Now, my dear students, for example, this is one plate, one electrode. This is, for example, one more electrode here. This is one more electrode. So I've taken two rectangular plates here, two rectangular electrodes I've taken. Now, for example, I'm connecting these electrodes to the external battery. This is the negative terminal of the battery. So this particular plate will be getting the negative charge. This particular plate will be getting the positive charge. Perfect. Now, what's going to happen? First of all, if I talk about this particular part of the plate, can I say this particular part of the plate is inside the solution? Absolutely. Even this particular part of the plate is also inside the solution. So this is the shaded part of the metal plate. This is the shaded part of the electrode that is in contact with the solution. Even this is the shaded part of the electrode. Even that is in contact with the solution. Okay. Now understand, see what I'll be doing. See what I'll be doing, guys. For example, if I join this and this, this and this. If I join this and this and this and this. Can you check what kind of geometric figure I got here? Can you check what kind of geometric figure I got here? I got a cube. I got a cube. If I take this cube out of here, if I make this cube separately like this, I'm making this cube separately now. This cube I'm making separately. Basically, this is the part of the metal plate which is in contact with the solution. Even this is the part of the metal plate which is in contact with the solution, right? This metal plate is carrying negative charge. This metal plate is carrying positive charge, right? Now, between these two metal plates, what do we have? We have got a solution containing an electrolyte. There is a solution containing an electrolyte. So this is electrolytic solution present in between them. My dear students, first of all, this particular cell is what you call as the conductivity cell. You call this particular cell as the conductivity cell. Number one. Number two, let's assume the distance between these plates I'm representing with L centimeter. Let's say the area of cross section of this plate right now is A centimeter square. It is A centimeter square. Okay. Distance between these two plates is L centimeter and area of cross section of this particular plate is A centimeter square. Perfect. Now, my dear students, between these plates, what do we have? We have got an electrolytic solution. Let's say we have got an electrolytic solution of an electrolyte AB. So I had kept AB electrolyte here. If there was AB electrolyte in the solution, that means in the solution you will find A positive ions and B negative ions. you will find A positive ions and B negative ions in the solution. I say this A positive will be attracted by this plate and B negative will be attracted towards this plate, right? Since this plate carries negative charge, so A positive will be attracted by this, and this plate carries positive charge, so B negative will be attracted by this. Now, first of all, my dear students, when these ions will be moving towards the respective plates, will there be any obstruction in the movement of ions? Will there be any obstruction in the movement of ions? That is my question to you. See, this is A positive. When this A positive will be moving, at the same time, other B negatives in the solution, they'll be attracting this A positive towards itself. So there will be obstruction in the moment of A positive. When this B negative will be going towards this plate, at the same time, there will be A positives which will be attracting this B negative towards itself. So again, I would say there is obstruction in the moment of ions. And this obstruction towards the moment of ions is something which defines resistance of this particular cell. So the first terminology which we have, that is a resistance of this particular cell, which I'm representing with R. This resistance of the conductivity cell, it arises due to what? It arises due to the interionic force of attractions between the ions. Okay? Now, my dear students, try to understand. How do we calculate resistance here? There's a formula. You know it already. It's rho L divided by A. Rho L divided by A. And its units are going to be simply ohm. So this is the first parameter which you are going to remember. Resistance of this particular cell, R is equal to rho L divided by A. Point number one. The second terminology which we have here, that is conductance. And conductance we represent with G. How do we define conductance? Conductance is nothing but inverse of resistance. Conductance is nothing but inverse of resistance. Okay? Conductance is nothing but inverse of resistance. Or before discussing conductance, let's discuss one more thing first. That is this rho. What is rho? Rho is called as resistivity. Rho is called as resistivity. Can I say rho will be equal to RA divided by L? Absolutely, rho will be equal to RA divided by L. Now, first of all, if I have to define this rho, how do I define it? See guys, try to understand. See how am I going to define this resistivity? First of all, if A is equal to 1 centimeter square, if A is equal to 1 centimeter square, L is equal to 1 centimeter. That means if the distance between the electrodes is 1 centimeter and area of cross section of this plate is 1 centimeter square. So first of all, can you tell me what will be the volume of the cube at that time? Volume of the cube will be area of cross section multiplied by distance. It will be 1 centimeter cube. Volume of this particular cube will be 1 centimeter cube. And whatever will be the volume of the cube, same is going to be the volume of the solution here. Because you know, solution occupies the volume of container in which it is kept. So I would say this 1 centimeter cube is basically the volume of electrolytic solution. It is the volume of electrolytic solution. And my dear students, if A is equal to 1, L is equal to 1, I would say at that point of time, rho is equal to R. So what is rho? What is resistivity? Resistivity is basically the resistance. Resistivity is the resistance. It is the resistance shown by 1 centimeter cube of the electrolytic solution. So whatever resistance is shown by 1 centimeter cube of electrolytic solution, that is what you call as the resistivity. I believe it's clear. Yes, I believe it's clear. If I ask you what are going to be the units of resistivity, say this is R A by L. R units are ohm. A will be centimeter square, this will be centimeter, so it is ohm centimeter. This is the unit of resistivity first of all. Okay, so resistivity is nothing but it is the resistance shown by 1 centimeter cube of the electrolytic solution. Yeah. Now, my dear students, there is a term called as conductance. There is a term called as conductance, and this conductance I'm representing by G. And conductance is nothing but inverse of resistance. So if conductance is inverse of resistance, what are going to be its units? Units are going to be ohm inverse, or you call it as mho. Ohm inverse, or you call it as mho, or you call it as Simon, or you call it as Simon. These are the units of this conductance G. Now, if you want to make its result, so G will be equal to 1 divided by R is nothing but rho L divided by A. A comes up, right? Perfect. So this is how you define your conductance. G is equal to 1 by rho into A by L. Perfect. Now, my dear students, this 1 by rho is something which you call as conductivity. Conductivity, which we represent with kappa. Conductivity is nothing but its inverse of resistivity. It's inverse of resistivity. Conductivity is nothing but inverse of resistivity. So, if you want to make its proper result, I'll say kappa is equal to 1 divided by rho. Rho is equal to R A divided by L. That L comes up. So, I can say kappa is equal to 1 by R multiplied by L by A. This is one of the results which is frequently used in the questions. Kappa is equal to 1 by R into L by A. And my dear students, you already know 1 by R is what we call as G, conductance, and this L by A combinedly is called as cell constant. L by A is combinedly called as cell constant. It is combinedly called as cell constant. What is G? G is conductance. G is conductance. And what is this kappa here? Kappa is conductivity. So can I say conductivity is nothing but conductivity is equal to conductance multiplied by cell constant? Simple. I can say conductivity is equal to conductance multiplied by cell constant. I believe this is clear to everyone. Now, my dear students, you can make its units as well. You can make its units as well. If you look carefully, conductivity is equal to conductance multiplied by cell constant. What are the units of conductance? Simon, cell constant. L is centimeter. This is centimeter square. So it becomes centimeter inverse. So it's one of the unit is Simon centimeter inverse. Its another units will be mho centimeter inverse. Its another unit will be ohm inverse centimeter inverse. These are the units of your conductivity kappa. These are the units of your conductivity which is represented by kappa. Right? Perfect. The point is, how do we define this conductivity? So I told you kappa is nothing but, let me write it over here. I told you kappa is nothing but, kappa is 1 divided by R into L by A. Correct? Now, my dear students, imagine if L is equal to 1 centimeter, A is equal to 1 centimeter square. That means what is going to be the volume of the cube? Volume of the cube is going to be 1 centimeter cube. And the solution which is present in this 1 centimeter cube volume will have the same volume. If the volume of the cube is 1 centimeter cube, that means the solution which is there in the cube, it will have again the same volume 1 centimeter cube. So if L is equal to 1, A is equal to 1 centimeter square, kappa will be equal to 1 by R. 1 by R is nothing but G. So how do I define kappa now? Kappa is defined as, I would say conductivity is defined as the conductance. It is defined as the conductance shown by 1 centimeter cube of the electrolytic solution. So whenever you have 1 centimeter cube of the electrolytic solution, whatever conductance it's going to show, that's what I call as conductivity. So conductivity is nothing but, conductivity is the conductance shown by 1 centimeter cube of the electrolytic solution. I believe that's clear. So conductivity is the conductance shown by 1 centimeter cube of the electrolytic solution. Now comes one more point. What is one more point? One more point is one more terminology, which is what you call as molar conductance. Molar conductance. How do we exactly define molar conductance, which we represent with lambda m? My dear students, molar conductance is nothing but, it is defined as the conductance. The conductance shown by all the ions. The conductance shown by all the ions when 1 mole of electrolyte is present in is present in a given volume of solution. Whenever you have 1 mole of electrolyte present in a given volume of solution, whatever conductance will be shown by the ions at that point of time, that conductance shown by the ions is what you call as molar conductance. What does that mean? What does that mean? For example, let me make you understand like this. For example, this is your conductivity cell. This is your conductivity cell, for example, right? This is your conductivity cell. Now, let's say in this conductivity cell, there is a solution. There is a solution of an electrolyte. Let's say volume of this particular solution is anything. I'm writing V centimeter cube. It can be 10, 20, 30, 40, 50, whatever, right? I'm assuming volume of this particular electrolytic solution is V centimeter cube. So what is V centimeter cube? It is the volume of the solution, volume of the electrolytic solution. Volume of the electrolytic solution. Okay. Let's say there is 1 mole of electrolyte. Let's say there is 1 mole of electrolyte present in this solution. Let's say there is 1 mole of electrolyte present in this particular solution. My dear students, whenever 1 mole of electrolyte is present in a given volume of solution, whatever conductance will be shown by this particular solution at that point of time, something which I call as molar conductance. Molar conductance is nothing but, it is the conductance shown by all the ions when 1 mole of electrolyte is present in a given volume of solution. Now let me tell you, this molar conductance, there is a direct result to that. Molar conductance is equal to kappa multiplied by 1000 divided by molarity. Kappa multiplied by 1000 divided by molarity, right? There is one more result to it, that is lambda m is equal to kappa divided by 1000 multiplied by molarity. There is one more result to it, lambda m is equal to kappa divided by molarity. So there are 3 results. Now which result to use and when? Which result to use and when? Which result to use and when? My dear students, first of all, when molar conductance is to be calculated in Simon centimeter square per mole, just a second. When molar conductance is to be calculated in Simon centimeter square per mole and kappa value is given in Simon centimeter inverse, at that point of time, this is the formula which you are going to use. Number 1. Number 2, when molar conductance is to be calculated in Simon meter square per mole and kappa is given in Simon centimeter inverse, this is the formula you are going to use. And if molar conductance is to be calculated in Simon centimeter square per mole and kappa is given in Simon meter inverse, this is the result which you are going to use. This is the result which you are going to use. Okay? Perfect. I believe I'm clear with this. Now, similarly, guys, there is one more term called as equivalent conductance. There is one more term called as equivalent conductance. There is one more term called as equivalent conductance. And let me tell you, equivalent conductance is basically represented by lambda EQ. And what is equivalent conductance? It's pretty much simple. Equivalent conductance is nothing but, it is basically the conductance. It is the conductance shown by all the ions. Conductance shown by all the ions when 1 gram equivalent, when 1 gram equivalent of an electrolyte, when 1 gram equivalent of an electrolyte is present in a given volume of solution. Is present in a given volume of solution. So earlier I had 1 mole of an electrolyte present in a given volume of solution when I defined molar conductance. Now in order to define equivalent conductance, I will be talking in terms of 1 gram equivalent. So whenever you see 1 gram equivalent of an electrolyte present in a given volume of solution, whatever conductance is shown by the solution at that point of time, that's called as lambda EQ. Now to calculate lambda EQ, again you have got 3 results. To calculate lambda EQ, again you have got 3 results. First one, kappa multiplied by 1000 divided by normality. Second, kappa divided by 1000 multiplied by normality. The third one is simply kappa divided by normality. When to use which result? That's something which you need to know. See, when equivalent conductance is to be calculated in Simon centimeter square per equivalent and kappa is given in Simon centimeter inverse, the first result you are going to use. When this is to be calculated in Simon meter square per equivalent and this is again given in Simon centimeter inverse only, right? This is the result which you are going to use. When this is to be calculated in Simon meter square per equivalent and this is also given in Simon meter inverse, this is the result which you are going to use. That's all. Okay? That's all. Am I clear with this? Now there is one general result between lambda m and lambda eq as well. So let's talk about that general result. Since you know lambda eq, one of the result is which I frequently use, kappa multiplied by 1000 divided by normality, correct? So I can write lambda eq is equal to kappa multiplied by 1000 divided by normality is nothing but molarity multiplied by n factor, right? What about this particular term? I can say lambda eq is equal to this particular term I call as lambda m divided by n factor. So molar conductance, equivalent conductance is nothing but it can be written as molar conductance divided by n factor. Equivalent conductance can be written as molar conductance divided by n factor. Yeah? Perfect? Perfect, people? Now, some basic questions which you can solve out of all this. Let's talk about them. Anyways, the actual questions which we are going to do, that's tomorrow. Tomorrow we are going to do a lot of questions on this physical chemistry class 12th. See, this is one of the questions. The specific conductance. Specific conductance means kappa. Specific conductance means kappa. Of the solution is given to me as 0.009. Simon centimeter inverse. Right? Molarity of the solution is given to me as 0.1. Perfect. Cell electrodes of 1.5 centimeter square area. Area of cross section is 1.5 centimeter square. Right? Place 0.5 centimeters apart. L is equal to 0.5 centimeter. How much current should flow if the potential difference between the electrodes is 5 volt? V is equal to 5 volt. We are supposed to calculate current, I. You can use Ohm's law directly. V is equal to IR. So I is equal to V divided by R. Since potential difference is given as 5 volt, so R I have to calculate. How do I calculate R? There is a formula to calculate R. I told you a few minutes back only. Kappa is equal to 1 divided by R multiplied by L by A. So I can say R will be equal to 1 divided by kappa multiplied by L by A. Correct? Is the value of kappa given to me? Yes. Right? Is the value of L given to me? Yes. Is the value of A given to me? Yes. So you can calculate R from here. Once you get R, put the value of R here and you'll be getting the current here. You'll be getting the current here. Yes? This sort of a question, you should be in a position to solve easily if it comes. Okay, similarly, look at this particular question. Look at this particular question. Resistance of a 0.01 normal. So normality of the solution is given to me as 0.01. Resistance of this particular solution is given to me as 210 ohms. Cell constant L by A is given to me as 0.88 centimeter inverse. Calculate conductivity kappa and lambda EQ. Okay, and there should be units also given here. We have to calculate lambda EQ in Simon centimeter square per equivalent. Well, that's missed in the question, but I'm telling you. We have to calculate lambda EQ in Simon centimeter square per equivalent. Now, how do we do this? How do we solve this? First of all, it's a simple question, guys. You know, your lambda EQ is equal to kappa multiplied by 1000 divided by normality. Correct? So, in order to calculate lambda EQ, you need kappa. How do I calculate kappa? You know, kappa is equal to 1 divided by R multiplied by L by A. Perfect. So, kappa will be equal to 1 divided by R value is 210. L by A value is given to me as 0.88 and its units will be in, this will be in Simon, this is centimeter inverse. Perfect. So, you got kappa. Now, put the value of kappa here. N value is already given. Now, you have to just put the values and get the value of lambda EQ. Again, simple basic question. Again, simple and basic question. Okay. Again, simple and basic question. Even you can solve this sort of a question as well. Equivalent conductivity of 0.1 normal. So, normality of the solution is 0.1. Lambda EQ is given to me as 100. and its units are basically Simon centimeter square per equivalent, which is skipped in the question, but I know it's Simon centimeter square per equivalent, right? Now, my dear students, cell constant L by A is given to me as 0.25 centimeter inverse. The question is how much current will flow when the potential difference between the electrodes is 5 volt. So I have to calculate current. I is equal to V by R. I is equal to V by R. Potential difference is 5 volt. So I need to calculate R. How do I calculate the R? How do I calculate R? There is one formula by means of which I calculate R, that is kappa is equal to 1 divided by R multiplied by L by A. Okay, so I can say R is equal to 1 divided by kappa multiplied by L by A. What is L by A? Cell constant. It is given to me in the question. In order to calculate R, what do I need? I need kappa. Kappa is not given to me. So I need to calculate kappa first. I need to calculate kappa first. How do I calculate kappa? With the help of this formula. You know, lambda EQ is equal to kappa multiplied by 1000 divided by normality. So lambda EQ is given, normality is given, so we can calculate kappa. Once you calculate kappa, put it here, right? Put it here. L by is already given. You'll get the R. Once you get the value of R, put it here. You'll be getting the I. Just the manipulation of the formulas, nothing else. Just the manipulation of the formulas, nothing else, right? Okay. I hope this is clear. And my dear students, if this is clear, I hope you got to know. With the help of this particular formula, you will be calculating kappa. Once you calculate kappa, put it here, get the value of R. Once you get the value of R, put it there, get the value of I. Okay. Now, there are few things which you need to know. What is that? I'm writing effect of dilution. Effect of dilution on molar conductance, equivalent conductance, and conductivity, kappa. Effect of dilution on lambda m, lambda EQ, and kappa. Okay? Try to understand, guys. Try to understand. See, for example, let's say this is an electrolytic cell. This is positive. This is negative. And this is your electrolytic solution here. Okay, this is your electrolytic solution here. Now, first of all, in case of strong electrolyte, for example, imagine that we have got strong electrolyte present in the container. We have got strong electrolyte present in the container. Now, what if we do the dilution in case of the strong electrolyte present? So, first of all, if we do the dilution, the distance between positive and negatively charged ions will increase, since there is A positive and B negative here in the solution, right? If you do the dilution, if you put some extra solvent here, the distance between the ions will increase. And when the distance increases, I would say force of attraction between the ions will decrease. And if the force of attraction between the ions decreases, that means ions can now start moving freely. And if the ions start moving comparatively freely, that means the molar conductance automatically what? The molar conductance automatically increases. The molar conductance automatically increases. Okay? Molar conductance automatically increases. So with dilution, if you keep on doing the dilution, molar conductance will keep on increasing. Molar conductance will keep on increasing. There will be a time when molar conductance will attain its maximum value. During continuous dilution, ions are going far. Molar conductance of the solution is increasing. It's increasing. There will be a time when molar conductance will get its maximum value, which is called as lambda naught m. Lambda naught m is particularly called as molar conductance at infinite dilution. Molar conductance at infinite dilution. So if you want to understand this a bit in better way, so let's try to understand it like this. See, guys. For example, I'm making the conductivity cell. This is a conductivity cell, right? This is a conductivity cell. This part of the electrode is in contact with the solution. Even this part of the electrode is in contact with the solution. Now, basically, the electrode is somewhat like this. This is your complete electrode, for example. Even this is your complete electrode, for example. This is complete electrode, this complete electrode. But this part is in contact with the solution. I'm assuming that volume of this electrolytic solution is V centimeter cube. In this V centimeter cube of solution, there is 1 mole of electrolyte present. 1 mole of electrolyte AB present. And this electrolyte is, for example, strong. This electrolyte is strong. So there would be A positive ions and B negative ions present here. Now, if you do on dilution, if you keep on adding solvent, the volume of the solution will increase. The ions will keep on going far. The distance between the ions will increase. Force of attraction between the ions will decrease, right? If the force of attraction between the ions will decrease, the ions will start comparatively moving freely. So that means conductance of this particular solution will increase. And conductance of this particular solution is called as molar conductance, basically, because we have kept 1 mole of electrolyte in a given volume of solution, right? So molar conductance of the solution will increase. And if I keep on doing the dilution, there will come a time when the molar conductance will attain its maximum value, which is represented by lambda naught m, which is called as molar conductance at infinite dilution, right? And when molar conductance attains its maximum value, the dilution at that point of time is called as the infinite dilution. So I would say at infinite dilution, what's going to happen? At infinite dilution, molar conductance of the solution is going to be maximum, right? Molar conductance of the solution is going to be maximum, which is represented by lambda naught m. Perfect. Now here, if I do one thing, if I plot a graph, the graph is between lambda m versus root c. Lambda m versus root c. What is c? C is the concentration. How do you define concentration? Number of moles divided by volume. Number of moles divided by volume. This is how you define concentration. Now, first of all, the graph for the strong electrolyte comes out to be like this. The graph for the strong electrolyte comes out to be like this. And when you extrapolate it, first of all, if you look carefully, this point, at this particular point, root c value is 0. If root c is 0, that means c is 0. When can be c 0? C will be 0 when volume of the solution would be infinite. Volume of the solution infinite means we have done infinite dilution. At infinite dilution, molar conductance of the solution will be maximum. That is represented by lambda naught m. And if you extrapolate it, it will touch here. This point will represent lambda naught m here. So basically, from the graph, when you make lambda m versus root c graph for the strong electrolyte, from the graph, you can calculate molar conductance at infinite dilution, okay, for a strong electrolyte. Perfect. Same goes with lambda EQ as well, right? Same goes with lambda EQ as well. With dilution, lambda EQ also increases. Okay? And finally, lambda EQ attains its maximum value. That's called as lambda naught EQ at infinite dilution. Remember that. I'm just showing you lambda m versus root c. Same will be for lambda EQ versus root c as well. Now, my dear students, if you have the weak electrolyte, in case of weak electrolytes, again the same thing happens, but the explanation is comparatively different. For example, the electrolyte was weak. For example, the electrolyte was not strong, electrolyte was weak. First of all, with dilution, what happens? With the dilution, degree of dissociation of a weak electrolyte that increases, due to which number of ions in the solution will increase. And due to the increase in the number of ions, molar conductance as well as equivalent conductance. They both will increase. So with dilution, molar conductance as well as equivalent conductance of a weak electrode also increases. But the reason here is different. What is the reason here? The reason is number of ions in the solution increases. Why is that? Because when we do the dilution, in case of the weak electrolyte, its degree of dissociation increases as per your Ostwald's dilution law, right? Okay, perfect. And if you want to plot a graph between lambda m and root c for a weak electrolyte, the graph comes out to be like this. For a weak electrolyte. Now, if I ask you one thing, this particular point represents infinite dilution. See, the curve is coming somewhere from infinity, right? If I extrapolate it, where can I get the lambda naught m value here from the graph? I cannot get lambda naught m value from the graph here. So in case of strong electrolytes, lambda naught m can be calculated from the graph. In case of weak electrolytes, lambda naught m cannot be calculated from the graph. So how do we calculate lambda naught m for the weak electrolytes? Lambda naught m, molar conductance at infinite dilution, for a weak electrolyte is calculated with the help of a law called as Kohlrausch Law. Molar conductance of a strong electrolyte at infinite dilution can be calculated with the help of this graph which I've shown you, right? Yes, but remember, molar conductance of a weak electrolyte at infinite dilution cannot be calculated with the help of graph. Okay, it is calculated with the help of a law called as Kohlrausch Law. Now, in few minutes, we are going to discuss Kohlrausch Law. But before that, remember one more point. I told you with dilution, lambda m as well as lambda eq for both weak electrolyte and strong electrolyte. What happens to it? Increases. The reason for the increase in both is different. We talk in terms of, in case of strong electrolyte, we talk in terms of the attraction between the ions. In case of weak electrolytes, we talk in terms of degree of dissociation. Okay? But remember guys, remember one more thing. With dilution, kappa value, conductivity, that decreases. With dilution, kappa value decreases. Kappa value decreases means C. Imagine that volume of this particular solution is 1 centimeter cube. Imagine that volume of this particular solution now is 1 centimeter cube, right? And in this 1 centimeter cube solution, there is 1 mole of electrolyte present. Or let's assume it like this. In this 1 centimeter cube solution, there are 100 ions present. So first of all, the conductance shown by 1 centimeter cube of the solution is called as conductivity kappa. Perfect. Now when we do the dilution, what will happen? When we add more solvent, the number of ions in 1 centimeter cube of solution, that will decrease. If number of ions in 1 centimeter cube of the solution decreases, that means conductivity kappa automatically decreases, right? So remember, with dilution, kappa value decreases because number of ions per unit volume, they decrease. Okay, remember this particular point as well. This again important. Yeah, right people? I believe this is clear. Now there is one more part that is left. What is that? That is your Kohlrausch Law. That's your Kohlrausch Law. So first of all, what this Kohlrausch Law states? Kohlrausch Law states that the equivalent conductance of an electrolyte at infinite dilution is the sum of equivalent ionic conductivities of cation and anion given by the electrolytes at infinite dilution. So in short, if I have to make you understand this, see how do you interpret this basically. For example, you have got a solution of NaCl. First of all, how NaCl would have got dissociated? Na positive and Cl negative. This is how it would have got dissociated in the conductivity cell, right? Now, my dear students, one thing. If I want to know the equivalent conductance of NaCl at infinite dilution, how it is written? It is simply written as lambda naught EQ of Na positive plus lambda naught EQ of Cl negative. Nothing to do with the stoichiometric coefficients here. But if you want to write molar conductance at infinite dilution of NaCl, you will be starting with the stoichiometric coefficient here. It will be 1 multiplied by molar conductance of Na positive plus 1 multiplied by molar conductance of Cl negative at infinite dilution. Now let's try to understand this a bit more in detail. Let's try to know how to write it a bit more in detail. For example, you have got BaCl2, right? You are taking this electrolyte in the solution, in the conductivity cell. How will it dissociate? It dissociates as, for example, Ba di positive plus 2 times Cl negative. Now, if you want to write equivalent conductance of BaCl2 at infinite dilution, It would be equal. You have got nothing to do. You have got nothing to do with the stoichiometric coefficients. You'll directly write lambda naught EQ of BADI positive plus lambda naught EQ of Cl negative. But when you write molar conductance at infinite dilution of BaCl2, when you write molar conductance of BaCl2 at infinite dilution, you have to take into consideration the stoichiometric coefficient. So I'll start with 1, then I'll write molar conductance at infinite dilution of BaDi positive plus I'll start with 2, then it's going to be molar conductance at infinite dilution of Cl negative. Okay? So one thing which you need to remember here, whenever equivalent conductance is to be written in terms of equivalent conductance, you have got nothing to do with the stoichiometric coefficients. But when molar conductance is to be written in terms of molar conductance, you have to take care of the stoichiometric coefficients as well. This is one important thing, guys, which you have to understand and remember. Yeah? This is one important thing, my dear students, which you have to remember over here. I believe this is clear to everyone. Do you want me to take one more example for it? Should I be taking one more example for it? For example, you have got Al2SO4 whole thrice. You have got Al2SO4 whole thrice. How will it undergo dissociation? So first of all, this is going to be 3 positive. This 2 will go here. 2 negative. How many Al here? 2. So 2 times Al tripositive plus it's going to be 3 times SO4 dinegative. This is how it will undergo dissociation. Correct? This is how it will undergo dissociation. Now, my dear students, if I write equivalent conductance at infinite dilution for Al2SO4 whole thrice, it is going to be equal to lambda naught EQ of Al tripositive plus lambda naught EQ of SO4 dinegative. And when you write molar conductance in terms of molar conductance, you have to take care of your stoichiometric coefficients as well. Okay? Now, my dear students, the point is, there are a few applications of this Kohlrausch law. For example, to calculate the conductance of the weak electrolyte. See, we could not calculate the conductance of weak electrolyte at infinite dilution through the graph, right? Now, this is the way by means of which we are going to calculate the conductance of the weak electrolyte at infinite dilution with the help of Kohlrausch law. How exactly? Try to understand. For example, look at this particular question. See, molar conductance at infinite dilution for HCl is given. Molar conductance at infinite dilution for NaCl is also given. Molar conductance of CH3CONa at infinite dilution is also given. We need to calculate molar conductance of CH3COH from this particular data. Some data is given. This is to be calculated, right? This is to be calculated. Now think over it. Think over it, guys. First of all, lambda naught M of HCl means lambda naught M of H positive plus lambda naught M of Cl negative, right? This is given to me as 428. Call this equation number 1. Lambda naught M of NaCl, which is going to be lambda naught M of Na positive plus lambda naught M of Cl negative. This is given to me as 126. Call this equation number 2. And lambda naught M of CH3CO negative plus lambda naught M of Na positive. This is given to me as 91. This equation number 3. How do we write this Kohlrausch law for CH3COH? It's going to be lambda naught M of CH3COO negative plus lambda naught M of H positive. This is to be calculated. This is to be calculated. How can we create this out of all this? How can we create this out of all this? My dear students, just think logically. Think logically. What can we do exactly? What can we do exactly? Tell me once. Tell me once. What can we do as per you? Quickly. You have already started giving the correct answers. That's great. But still, I'm asking you, what can we do to get this out of all this? See, simple way. What do we need? We need CH3CO negative and H positive. Is H positive here? Yes. Is H positive here? No. Is H positive here? No. But CH3CO negative is here. What do we need? We need CH3CO negative plus H positive. So add these two and subtract this. So add 1 and 3 and subtract 2. If you add 1 and 3 and subtract 2, if you add 1 and 3 and subtract 2 out of it, So Na positive gets cancelled out. Cl negative gets cancelled out. So I'll be left with CH3CO negative plus H positive. CH3CO negative plus H positive means molar conductance at infinite dilution for the CH3COH. And whatever operation you are doing with the reaction, same operation you have to do there with their lambda naught m values. So equation 1, that is 426. Third one was 91. Second one is 126. Right? Solve it, get the answer. Did you understand how I did it? Okay. Did you understand? I just want to get CH3CO negative and H positive. CH3CO negative is here, H positive is here. Just add these two and subtract this one. That's all. See, the application of Kohlrausch Law is calculation of molar and equivalent conductance of weak electrolytes. That is the application. That's the application. This is the application of Kohlrausch Law. But Kohlrausch Law is applicable for strong electrolytes. Okay? This is its one of the applications. Absolutely, it's going to be. It is 391, right? Okay, the answer is going to be 391 when you solve it. All right, I believe this is clear. There is one more application of this Kohlrausch Law. What is that? That is calculation of degree of dissociation of weak electrolyte. Calculation of degree of dissociation of weak electrolyte. And there is one direct formula which you are going to remember directly. There is derivation of it as well, but no need to go for the derivation. So, degree of dissociation is always equal to molar conductance of the electrolyte of a weak electrolyte at a given concentration divided by molar conductance of the same electrolyte at infinite dilution. What does that mean? For example, I've got CH3COH in the conductivity cell. I've got CH3COH in the conductivity cell. It's a weak electrolyte. So when its concentration is, for example, 0.1 molar, let's say its molar conductance at that time is 3.907. Now, at infinite dilution, its molar conductance is 390.7. 390.7. This is what I call as molar conductance of the weak electrolyte at a given concentration. This is what I call as molar conductance of the weak electrolyte at infinite dilution. If you know both of them, then alpha for a weak electrolyte can be easily calculated. Molar conductance of the electrolyte at a given concentration divided by molar conductance of the electrolyte at infinite dilution. Yeah? Right? Remember this particular thing as well. Now, if you know how to calculate alpha, then you can calculate the ionization constant of a weak electrolyte as well. And ionization constant of a weak electrolyte is represented by Ki. Ionization of a weak electrolyte is represented by Ki. Now, my dear students, try to understand. If you have the weak electrolyte like this, AB, if it is weak, it is going to remain in equilibrium with its ions. Ions are going to be A positive aqueous and B negative aqueous. Because you know, weak electrolyte, it does not undergo 100% ionization. It remains in equilibrium with its ions, right? Let's say in the beginning, its concentration is C. This is 0, this is 0. I'm sure you would have studied somewhere in equilibrium that at equilibrium, the concentration of AB means C minus C alpha. This is going to be C alpha, this is going to be C alpha. Now, if you want to write the expression for ionization constant Ki, Ki expression is written in the similar way as you write equilibrium constant expression. So I'll write concentration of A positive, which is C alpha, multiplied by concentration of B negative, which is C alpha, divided by reactants. Concentration of AB, which is C minus C alpha. So if you take C common, 1C gets cancelled out. It's going to be C alpha square divided by 1 minus alpha. Now, already we know for the weak electrolyte, how do we calculate alpha? Alpha is molar conductance of the weak electrolyte at a given concentration divided by molar conductance at infinite dilution, ka square, divided by 1 minus molar conductance of the weak electrolyte at a given concentration divided by molar conductance of the weak electrolyte at infinite dilution. Right? So, this is going to be lambda naught m minus lambda mc divided by lambda naught m. 1 lambda naught m cancels out. So, it's going to be C lambda mc ka square divided by, it's going to be lambda naught m multiplied by lambda naught m minus lambda mc. This is the direct result with the help of which you can calculate ionization constant of the weak electrolyte. Now, Weak electrolytes are basically, weak electrolyte can be your weak acid. Weak acid can be your weak electrolyte, or you can say weak base. Weak acids, weak bases, they are the examples of weak electrolytes. Weak acids, weak bases, they are the examples of what? Weak electrolytes. If I write weak electrolyte in general, for weak electrolyte, we use the term Ki. If the weak electrolyte is particularly your weak acid, we use the term Ka. If the weak electrolyte is particularly your weak base, we use the term as Kb instead of Ki. So you can say Ki is the general expression. Ki is the general term for a weak electrolyte. But if the weak electrolyte is weak acid, then instead of Ki, you are going to write Ka. If the weak electrolyte is your weak base, then instead of Ki, you are going to write Kb. Perfect. This is something which you need to know. Now, the third and the last application of this, what is that? That is calculation of solubility and solubility product for a sparingly soluble salt. Directly we have to remember one expression, guys. Molar conductance at infinite dilution of a sparingly soluble salt is equal to kappa multiplied by 1000 divided by molarity, or you can write solubility. Instead of solubility, you can write molarity as well. Because you know, solubility of a saturated solution is always equal to molarity, basically. Right? Molarity of a saturated solution is always equal to solubility. How do you find solubility? What is solubility? Solubility is nothing but molarity of the saturated solution. So either you write molarity here or solubility, one and the same thing. Right? Molarity of the saturated solution is equal to solubility. So either you write solubility or molarity, choice is all yours. So basically, molar conductance at infinite dilution of a sparingly soluble salt is always equal to kappa into 1000 divided by solubility or molarity. Let me write it completely, or molarity. Okay. Do you know how do you write the KSP solubility product expressions? Do you know? For example, you have got the salt of this type, AB solid. How it undergoes dissociation. A positive aqueous plus B negative aqueous. Anyways, this is something which I'll teach you in equilibrium in detail. Let's say its solubility is S, this is also S, this is also going to be S because stoichiometry is 1:1. How do you write the KSP expression? KSP's expression is written as concentration of A positive at equilibrium raised power 1, concentration of B negative at equilibrium raised power 1. Concentration of A positive here is S, this also S, so this becomes S square. How do you get S basically? S you get from this particular result. Once you get S, take the square of it, get the KSP for this salt which is of the type AB. For example, you have got the salt of the type AB2. For example, how this AB2 will undergo dissociation? AB2 will undergo dissociation as, see, this is basically A plus 2, this is minus 1. How many A we have? 1. A is in the form of di-positive. How many B we have? 2, in the form of minus 1. If the solubility of this is S, this is going to be S, this is going to be 2 times S. If you want to write the KSP expression is concentration of A di-positive raised power 1, that is S raised power 1. Concentration of B negative raised power 2, that is 2S raised power 2. The value comes out to be simply 4S cubed. Perfect. So this S you will be calculating from this result. Perfect. And multiplied by 4 raised power 3. That will give you the solubility product of this particular type of the salt. Okay. So, for example, there's a question, a simple question. Can you solve this one? If the limiting molar conductivity means molar conductance at infinite dilution. Okay. If the limiting molar conductance of Ca di positive and Cl negative are this and this, the value of limiting molar conductance of CaCl2. First of all, CaCl2 is nothing but Ca di positive plus 2 times Cl negative. So we have to calculate molar conductance of CaCl2 at infinite dilution. It is going to be equal to 1 into molar conductance of Ca di positive plus 2 into molar conductance of Cl negative. Correct? These values are given in the question. This is 119, I think, plus 2 times something 76.3. Solve this, you'll get the answer. Solve this, you'll get the answer. Okay, similar sort of question. Molar conductance of Al2SO4 whole thrice is given. First of all, how do you dissociate Al2SO4 whole thrice? It's going to dissociate as 2 times Al tri-positive plus 3 times SO4 di-negative. Now, molar conductance of Al2SO4 whole thrice at infinite dilution will be equal to 2 times molar conductance of Al tri-positive at infinite dilution plus 3 times molar conductance of SO4 dinegative at infinite dilution. Now, this term is given to me in the question. This term is given to me. Okay. This term is also given to me. I just need this particular term. So everything is given. One term is to be calculated. That's all. Okay. That's all. Okay. One last question. Molar conductance of 0.1 molar aqueous solution of ammonium hydroxide is 9.54. So when the concentration of ammonium hydroxide is 0.1 molar, at that point of time, molar conductance at a given concentration is given to me as 9.54 Simon centimeter square per mole. Okay. And at infinite dilution, molar conductance is also given to me as 238 ohm inverse. That means Simon centimeter square per mole. What do I need to calculate? The degree of dissociation, alpha. Few minutes back, I told you alpha is equal to molar conductance at the given concentration, molar conductance at infinite dilution. This will be 9.54 divided by 238, right? This is going to be degree of dissociation, but they have given the answer in terms of percentage. Remember, whatever value you get from here, remember percentage dissociation is equal degree of dissociation multiplied by 100. Okay, multiplied by 100. I think this value from here comes out to be 0.04. 0.04. So that means your percentage dissociation is alpha into 100, this into 100, that comes out to be 4%. So this should be the correct answer of the question. Okay. So my dear students, with this, your electrochemistry is also done and dusted. With this, your electrochemistry is also done and dusted. Now there is one sheet which I need to share with you that is going to be in the Telegram. Okay, tell me, what do we do with the solutions now? See, the time is already up. We could only complete 2 chapters. 1 chapter is left. That is solution. Should I provide the solution right now in the recorded format, so that you will complete it by tomorrow 4-5 p.m. and in the evening we are going to do again 300 questions. See, our tomorrow's schedule is listen to me first. Listen to me, guys. It is for your benefit. Okay, it's whatever I'm doing. It's for you. I'm getting nothing out of it. So listen to me very carefully. What I'm trying to say. If I give you, like, I'll post a link of the solution chapter in the comment section of this video. In the comment section of this video, I'll post a link of the solution. Okay, so that is going to be recorded basically. So tomorrow from 8 a.m. morning to 12 to 1 p.m. If you watch it at 1.25x, you'll complete this, or 1.5x, you'll complete this. And evening 8 p.m, we have got one live session tomorrow. That is top 300 questions of class 12 physical chemistry. If you do this, then our schedule remains unaltered. Okay, then our schedule is unaltered. Otherwise, I have to change the schedule a bit, which I already gave you. Not Premiere. When I end this particular video, in the comment section of this particular video only, I'll pin a comment with a link. That link, you have to click on that link. It will take you to the solution chapter. And see, listen to me first. Solution chapter in one of the video I have covered in 3 hours complete. So you just have to do a 3-hour video. It's not like that 9-hour video I'm going to send you of solution. No, 3-hour video of solution is enough. Okay. Who is this nonsense aspirant? You can get the hell out of this class, bro. This place is not for you. Guys, I cannot take live tomorrow because tomorrow I have the offline classes scheduled. Tomorrow In the daytime, I have got offline class schedule, and in the evening, I have got one more marathon with you only. That top 300 questions of class 12 physical. So that's why I'm telling you, do one thing. I'll post one 3-hour video in the comment section of this particular one, right? You just click on that link. Just 3-hour session you have to watch. If you watch at 1.5x, you'll complete in 1.5 hours. So like that, our session, our schedule does not change. Okay? Like that, our schedule does not change. Okay? PDF I'll send you right now. Do you understand what I'm trying to say? Wait, let me get the chair. I cannot stand also now. What time did we start today? 10, no? So it's 11 hours and 30 minutes. In 11 hours and 30 minutes, we completed 2 chapters, but in very much depth. See guys, wait. I'll post the link here only. Just a second. I'll post the link in the chat box only. Just be like this. Just be like this. I'll tell you which video I'm talking about. It is just a 3-hour part, guys. You cannot, I mean, don't be so shrived. Just a second. It's not in 3 hours. It's a 2-hour 20 minutes video. It's a 2-hour 20 minutes video. Okay? It's a 2-hour 20 minutes video. This is the link. Do you see this link? I'm pinning it. Do you see the link pinned? Once you click on the link, I'll give you the timestamps as well, from 9 to 11 at the end. 9 to 11. 9 hours to 11 hour 20 minutes is your solution chapter complete. Okay? बासित वो नहीं हो सकता है, उससे पूरा स्केड्यूल चेंज हो जाएगा. उससे पूरा स्केड्यूल चेंज हो जाएगा. तो आप इतना प्लीज मत करो. Yes, that recorded is from basics as well. You don't worry about that. You don't worry about that. Okay? It is enough. It is enough. It is enough. Anyways, I'm going to post the same link in the comment section of this video as well, once we end the today's session. Okay, once we end the today's session, I'll post it in the comment section of this video as well. Tomorrow we'll have the 500 question session of all the 3, solution kinetics as well as your electrochemistry. And that session is going to be live tomorrow at 8 p.m. And that's going to be 4 to 5 hour session. So right after today's session, what you have to do, you have to click on the link which I have sent you already in the stats. I'll pin the same in the comment section of this video as well. And when you click on that link, the timestamps are 9 hours to 11 hours 20 minutes. 2 hour 2 minutes, 2 hour 20 minutes video, right? The remaining part will be done. And one sheet I'll be posting in the Telegram, okay? That will include that table which I told you already, and that will include one more theoretical question, that is the batteries, which you have to remember, from which memory-based questions are asked. Okay? Got it, got it, got it? I'll send today's notes in the Telegram, don't worry. I'll send today's notes in the Telegram. Perfect. So tomorrow we'll have the session, guys, now. Okay, let me quickly tell you all the things again. Tomorrow at 8 p.m. it's going to be top 500 question session. I'll be doing all the 3 chapters, kinetics, electrochemistry as well as solution. Okay, all the questions of your NCRT, exercise, NCRT in-text, NEET PYQs, JEE PYQs, everything. Okay, that will be happening tomorrow at 8 p.m. But before that, you have to watch this 2 hour 20 minutes recording on your own. Okay, so it's not like some 9-hour video or 10-hour video. No, 2 hour 20 minutes enough, more than sufficient to solve the tomorrow's questions. Okay. Okay, and do let me know in the comment section how you liked the session. Do you want all the other lectures like this only in the detailed form? Yeah? Chalo. No need to study NCRT in my subject in this physical part. Just follow the sessions.